Ok.
Also, ja. Okay, very good. Very good. Very good. I'll take another coffee in order to be in good shape. Ça va? Salut. Comment ça va? Ça va bien? Oui, oui. Oui, ça fait plaisir de te voir. En fait, ça fait très longtemps que je ne t'ai pas vu. Je vois ton nom parce que tu es superstar maintenant. Je vois ton nom partout. Ouais. On t'entend partout dans l'enfant. Ah merde, c'est vrai? Ah merde. Là, t'as raison que je dise pas trop de conneries. Non, mais tu as raison. Ça va être ça va, ouais. In fact, I know very well the guy because he was in Orsay 8 years ago. The guy who showed me the. Yeah, I know him very, very well. Yeah, we'll go with Pierre. Alors attends, tu es où maintenant? Tu es à Lyon? Ah ouais. Oui, non, mais j'avais, comment dire, intégré ça dans les différents mails que j'ai reçus. Ouais, ouais. Ouais, ouais. Je prends des photos parce que Pierre, tu connais Pierre Salati? Ouais, alors. D'accord. Et alors, c'est marrant parce qu'on était, il y a 39 ans, ensemble à une école d'été à Etché. J'ai retrouvé il y a peu de temps, j'ai regardé les vieilles photos, une photo de lui, sa femme, là-bas. Oui, moi j'ai un problème aussi. Ouais, ouais. Je sais pas où j'ai mis le. Yeah, I should have it somewhere, but I know I put it as this. But not this one.
Okay, good morning, everybody. So I think we can start the first session of the day. So we have our first speaker is Luis Bayard, and he's going to tell us about BEH Higgs boson searches between 1964 and 2012. Please start.
Hey, thank you. So first, I thank the organizer for having invited me. Pourquoi est ce truc là-haut? What is this? Okay. To give a short historical talk at the occasion of the 10th anniversary of the Higgs boson discovery, with an emphasis on the LHC, where the discovery happened. I will discuss briefly theory, experimental developments, including detectors, magnets, searches pre the discovery and the discovery. And with the emphasis will be on experiments and machines. And I very often start by this quotation for a very famous French thinker: nothing is believed more strongly than which we know the least. Which means that for things where I'm not expert, you should not believe me, because very often I will say things like if it was granted, and it's not the case. Giving an historical talk is always difficult. I have another quotation from Newton: if I've seen further, it is by standing on the shoulders of giants. And this applies obviously to theorists, you know, that Higgs and Englert were on the shoulders of Anderson, Goldstone, and Ginzburg, but also for the machine and the experiments. People should realize that the building of the LHC machine, which I will describe, which is probably one of the most difficult things which happened, would not have been possible if CERN would not have built the SPP bar collider. And the SPP bar collider would not have been possible if CERN would not have built the ISR before, which was the first proton colliding ring. So if you want to learn more, you can have a look at historical talks at the Higgs hunting workshop, where here you see all the speakers which were giving historical talks at the Higgs hunting workshop. You see all them. I didn't put the names. It's a sort of a game to realize, to know if you are able to find all the names in these pictures. All people in these pictures are very well known people which contribute to the field. And I make a publicity for the next workshop, which is in a few days from now, where at the occasion of the 10th anniversary of the discovery of the boson, there will be 2 talks. Now I give the names by Peter Yeni and Jim Verdi, who were among the pushers of the start of Atlas for Peter and CMS for Jim. You can also see the various jamborees. It's very interesting to listen to these talks, because you realize that the same thing seen by 2 very intelligent people is not seen at all in the same way. So now I will show a dense transparency which will follow, where I will try to discuss spontaneous symmetry breaking. I remember that it's a term which was coined in the beginning of the 60s by Baker and Glashow. The electroweak theory, it's a term which was coined by Salam at the end of the 60s. The broad angular Higgs mechanism, the LHC, all in a nutshell. So I start by the Ginzburg-Landau phenomenological theory in a paper of 1950, where in fact in this paper you have the so-called Higgs potential, which is already written. So this explains the Meissner effect. In fact, the Meissner effect was explained before by London and maybe also by others. And you see that there is analogy. It's very well known, and between superconductivity and high energy physics. In some sense, W mass is the equivalent of the London penetration length, and the X mass of the p-part coherent length. All this in superconductivity is related to a sort of Anderson-Brute-Engler-X mechanism. And now I continue. Nambu introduced spontaneous symmetry breaking to high-energy physics at the end of the 50s, and there was the following papers by Goldstone, Gell-Mann, Levy, and other people which are there, culminating with Phil Anderson, where in fact it's rather well clear in the paper of Phil Anderson that the Goldstone modes disappear and the mass is given to the photon. It's a sort why some people call the mechanism Anderson and company mechanism. So this is a prehistory. In fact, all these papers, I tried to read them, but since I'm an experimentalist, I must confess that I failed miserably on all of them because they are too complicated for me. They are also different notations. The one which I prefer, the only one which I had the impression that I understand something, is the one of Goldstone. Probably not because I understand the paper, but because at least there is a drawing and a formula which I happen to know. This drawing is Mexicanate potential, and the formula is the famous X mass. So this caused Keeble to say that, as we all know, the Higgs boson should be called the Nambu boson, but the Goldstone boson should be called the Nambu boson, but the Higgs boson should be called the Goldstone boson in this. So after this, which I would say is prehistory, I go now to history, which is 1964, the four papers of Brute, Englert, Higgs, Guralnik, Hagen, and Keeble, where in fact the model is, the mechanism is rather well described. Going from Anderson to this paper is going from an awesome theory, which is very impressive, of superconductivity to a sort of magic, which is still magic for me, which is superconductivity in the vacuum. And then after, in all these people who are seeking to strong interactions, and the first one who really described, let's say, a model, a viable model, is Steven Weinberg for weak interaction, where you have SU2 cross 1 in 67, and you have all these other papers. So far for the theory. Now I go to the experiments. In 1973, the neutral currents were discovered in Gargamel, which was a very important thing for two reasons. First one, that CERN, it was the first time that CERN made a first class, let's say, Nobel Prize equivalent discovery. And the second thing, it was really the confirmation of the Weinberg-Salam model. And then after, in 1983, under the leadership of the genius leadership of Carlo Rubbia, there was a discovery of W and Z at CERN on the SPT-bar collider. This is very important because without the SPT-bar collider, probably the LHC would not have worked as well. In 1984, we'll come back later, there is a Lausanne workshop, which is, this is almost 40 years ago, 38 years ago, which people very often say the start of the LHC. And then after, in August 89, operation of LEPS starts, and in 89, it's the beginning of the research and development of the LHC experiments. So this is an extract of the cover of the Lausanne workshop in 84. At this time, now I am unfortunately one of the oldest in all the conference I'm going, but at this time I was one of the youngest to this workshop. It's interesting. This thing is interesting for two reasons. You see that already you have the 2-in-1 magnet design of the LHC. Also at this time, it was not a real design. And the second thing is that LHC and LEP are in the same tunnel. This obviously is a big joke, and I think people who proposed this knew it was not serious, but it was a sort of political way to have this, to have the work continues. The two machines in the same tunnel, it stayed, I think, until 1995, when Chris Levin-Smith decided to throw away this, this thing. So now after this, I continue to what is, let's say, recent history. You have the beginning, I said you had the beginning of the research and development of LHC experiments, which is a start for a lot of people. There are some people which are working on LHC, let's say, each day since 33 years. Then you have the, I will come back, the letter of intent of the large experiment, the cancellation of the SSC in 1993. Also, I will come back later. There is a discovery of top by CDF and D0 in 1995, following the evidence by CDF in 1994, and the approval of LHC in December 1994, just after the cancellation of the SSC. It's obviously, there is some correlation. The approval of LHC was a very strange approval. Also for political reasons, people decided to approve the LHC in a two-step way. The first step would have been you put only one magnet of the three magnets over three. This was obviously a big joke too, but it was a way to force the approval. Thanks to the cancellation of the LSC, several countries like US and Japan and so on contributed to the LHC. And then in 1996, you had the approval of the LHC in one step. And then after, you have the approval of the four experiments. It starts at, I will come back, at 7 TeV center of mass in 2010. And the discovery is in 2012, just after Tevatron data ended. And the boson-like properties were let's say, well described in 2013, and the Nobel Prize was given to Englert and Higgs. Also, it was clear already at the discovery that most probably the boson was spin zero due to its decay in gamma-gamma, and that most probably it was a CP event due to its decay in a pair of vector bosons. So now we'll make some view on this part in the next transparency. So this, I remind that thing was very important just before the approval of the LHC in first approval of the LHC in 1994 was the fact that the 10-meter long prototype had reached a field of 8.7 Tesla. So now I continue rapidly. In 2008, the first beams were in the LHC. Unfortunately, 9 days after, there was an incident which caused almost 1.5 years of delay. And then it started more or less in 2010 with the 7 TeV center of mass way of working. And then it continued. In 2011, you had 5 inverse femtobarn and integrated luminosity. There was a first signal which was presented in the CERN seminar at CERN at the end of 2011. And in 2012, it was presented in a CERN seminar and evidence for new boson. And this is me in the 4th of July, sleeping in front of the CERN auditorium in order to have some, to find some place to listen to the seminar. So now it's a very, this is a reminder of the plan of the LHC. The discovery was 10 years ago, the Nobel Prize 1 year after. We are now, and we still have 20 years of work in front of us in the LHC, which is a thing you have to remind when we'll discuss things. So I discuss very rapidly the theory. I will be very happy. I will put only papers which I think had some importance on me. I always start by, it's not really the first paper on phenomenology, but at least it's one of the first one with John Marike and Dimitri Anopoulos in 1975, where they claim first, we do not want to encourage big experimental search of the Higgs boson, and they say we have no idea what is the mass of the Higgs boson. 1 year after, there's a paper, an important paper by Chris Quick, Bentley, and Thacker. We are looking at a Gedanken experiment, WW scattering. They realized that either the Higgs mass was below 800 GeV or perturbative unitarity was violated around several TeV. This gives the idea of a nullus theorem. It was very important for people working in the LHC because we had the impression that we were working for something which we will be sure to find. It's always it's like in God, it depends how you want to believe it. Then an important thing is that a lot of theorists, in particular these ones, realize that in SUSY, the Higgs should be low mass and most probably less than 130 GeV. So it's very important for me. It was working in a diphoton decay, which is a thing which is important at low mass. And also at this time, people were expecting that we would find supersymmetry before the Higgs boson, which has proven to be wrong. Now I want to make, I think I cannot discuss the theory without having an homage to the people who are doing complicated computations. This is the evolution of the computation of the Higgs cross-section going from leading order to N3 LO. And it took a lot of time, a lot of work, and it's, for me, it's one of the most important achievements. It culminated in this N3 LO computation, which was done by a bunch of very bright theorists under the guidance of Davis Anastasiou. With this cross-section, you can also look at a plot of signal strength, which is a ratio of the measured cross-section with the standard model cross-section, where you see, it looks, where you see also the various state of the computation and the measure. This is the actual measure. But you see that even if I go to the old papers of discovery paper of Atlas and of CMS, that with this next to leading order computation, we are finding a cross-section in agreement with the standard model. This was also very important to convince us that we were doing right things. How many times do I have? Okay, so I will be now very fast because I have lost some time. I will discuss experimental developments. The construction of the machine and of the experiments went very well, but not without problems. I think we should remember that this thing started at LEP. So already in 78, Nino Zikiki suggested to have a large tunnel in order to have a proton collider in this tunnel. As I told you in the beginning, people thought we could have at the same time proton and electrons. In fact, it goes even before 78, because John Adams, who was one of the big shots of the accelerators at CERN, and who did not like electron colliders, insisted that the LEP, if we would have built LEP, we would have built LEP with a tunnel which would allow to have proton collisions. The SSC was approved in 88, cancelled in 93 for a lot of reasons we could describe. I will not describe them. After the cancellation of Isabelle, it was really a sort of decline, start of decline of the high energy physics in the US. But countries that contributed to the SSC will contribute to the LHC. Then I go rapidly in this transparency, which starts in 84. There are two important things. It was still considered to install, as I said, LEP and LHC in the tunnel, which was clearly not a good idea. And Chris Levin-Smith stopped this in 1995. finally, at this time, thanks to the competition with the SSC, the dogma came from standard luminosity of 10 to the 33, where you had more or less one collision per bunch crossing, to a very high luminosity of 10 to the 34, which was a thing which was pushed in particular by Carlo Rubbia. So I will now show one transparency on the dipoles. Dipoles, the niobium, titanium dipoles of the LHC are one of the marvels of technology and of this accelerator. These are 15-meter long niobium titanium dipoles, and you see that in order to increase the magnetic field and go to 8.3 Tesla, one had to decrease the temperature of helium from 4 to roughly 2 kelvins. And this was very useful, not only because it increased the field, but at this time you have superfluid helium which permeates through the conductor, and it has a very large equivalent thermal conductivity, and it makes a very good thermal stability of the machine. It is one of the reasons why the LHC is working so well. I have just one transparency on 1992 where the experiments were chosen. There were 4 experiments which were presented at Evian, and then it was soon seen that 2 experiments should merge. Atlas, which there was a merge of Eagle and Ascot, and there was CMS and L3P, and then it was chosen 1 year after. Atlas and CMS were chosen. So now I go very, very rapidly on the rest. I will not describe the crisis of LEP. You remember that the end of LEP, some signal was supposed to be found. It was a big mess because LEP people wanted to continue 1 year, but it would have delayed the LHC by 1 year, because just the time where the engineering of the LHC should have entered the tunnel. So then it was decided by the CERN Council on the advice of Mayani to close LEP. Okay, so I will not describe the experiments, which are very, very. I just show here. Yeah, I will not describe the experiments since I'm the end. I will just go. You see that you have high quality control, where the CERN DG, which was Robert Aymar, and the spokesperson of CMS, Michel Delanegra, tried to convince the French president, Jacques Chirac, that things is going well. And he seems to realize that things will not be that easy. He was obviously correct, but things went quite well. Things at the end went quite well. So I will continue. I don't have time to describe Atlas. I will just tell that there were 2 delays at the end. One which was due to the cryogenic distribution problems, which was 1.5 year delay, and one which was due to to a fault occurring in the electric bus connection, which was a big mess. It resulted in a mechanical damage, so 1.5 year delay. So there was 3 years delay. I will not describe the searchers. I will not describe the searchers pre-LHC. They were obviously important contributions from LEP on the Tevatron. Without LEP and without the Tevatron, people at the LHC would have worked much. The analysis would have developed much less. Also, LEP. Okay, I just now end by just showing a few plots on the discovery. This is a plot from Atlas that a lot of people have seen, but you see without sophisticated statistical analysis, you see the gamma peak evolving over the background. So at this time, it was clear there was a signal. Here I'm cheating a little bit because this plot is a bit posterior to the discovery. And obviously the same thing in the Higgs into 4 lepton channel, where if you wait a little bit, you clearly see the signal which appears at 125 GV. So finally, that's this was nice times for people like me. And finally, I show the evolution of the excess with time. It's my last transparency, where you see this is in fact the probability that the background fluctuates more than the observed data. If you have something at 5 sigma, it means either you go to Stockholm or you send Higgs and Engler to Stockholm, which was unfortunately the second case. And this was at the CERN seminar in December 2011, where you see that you have 125 GV thing. Unfortunately, this is for Atlas, with the same from TMS. In the spring 2012, the signal was a little bit less. So it was a bad thing. However, for the 4th of July, we were above 5 sigma, and then in the published paper, which came almost 2 months after, it was even better. And then now it's even better. So now, thank you for your attention. So I think all the technicians, engineers, and physicists can do the machine during 40 years, and I said maybe we should go to even more than 40 years, because I said the LHC would not have worked well without a lot of things. Have to be contributed. Obviously, I do not forget the theorists here. I know there are a lot of theorists. And after 2012, but this is another story, precision physics with Higgs boson of LHC will occur, and you have the following talks in this conference. So thank you.
Okay, thank you very much. We can take a couple of questions.
Thank you very much for your talk. In your theoretical introduction,
as I said, you see the quotation from Montaigne. Okay. I'm not a theorist, so I will not.
No. I something what when I'm talking with solid colleagues, they are always mentioning superconductivity and this origin of ideas coming from that, and trying to underestimate all these efforts. How would you usually answer to such?
I have, I was not present at this time. I have only the answer for me is that going from Anderson, which is probably the last important paper in superconductivity before the Brute-Engler Higgs Gorlnik-Hagen paper to this paper, is going from something, you have a mechanism in a superconductor which gives mass to the photons, and then you go to a sort of superconductivity of the vacuum. For me, it seems to be really a step further. But I think we should not. I know that Phil Anderson. I've never seen him. But I know that he was thinking that the people which are quoted, which really are quoted for the 64 paper, owes a lot to him. But this I'm not an expert. I think Jean-Marie. Jean-Marie with from Brussels and from the Brute-Engler community can give his opinion.
Sorry, I was going to ask a question before that, and definitely not on history, because I'm a bit tired of history and, trying, okay. Actually, you started with the Goldstone potential, which is indeed explicitly in the Goldstone paper, explicitly in the notation, and explicitly foresees not only the Goldstone bosons, or whatever you want to call them, but also a scalar particle.
Yes.
Of course, the Goldstone model was not gauged, and it had those Goldstone bosons. Now, it gives a precise prediction for the mass of the scalar, and not only for the mass, but also for the existence. Because in fact, we don't know the potential. And if you take precisely the analogy from superconductivity, it's very difficult to find the analogies of the massive scalar boson in superconductivity.
Yeah, it's not trivial. Yeah.
You have the Cooper pairs. There were some hints very lately, but I mean in the early 2000s or 2010, something like that. I had discussions with Higgs on that. And actually, this is the part of the physics which is not tested and which is maybe most interesting to test. Of course, we have found a scalar particle. The fact that the scalar exists is a good hint that we are in the good direction with the Goldstone potential. And Goldstone potential is unique in being renormalizable. Now, we may question whether renormalizability is the most important point or gauge invariance. I would think for the second. But it still needs to be tested. And you might have all kinds of dynamical mechanisms which generate the scalar excitation. So I think this is a very important point of research.
No, but I think some people in this workshop will discuss, I imagine, the Higgs boson search, and it's clearly one of the most important things to do. However, we should not think it will, theorists should not think that in 2 years from now, you will have.
No, but we shouldn't take the exact form of the lambda phi 4 potential for granted. No, just to give a very quick answer to the previous question. Also, I came late in the game. I was there in 70 something. And of course, it was 10 years after. But if you go back in those papers, we realize that first of all, obviously the Meissner effect was there in full sight, and it was barely hidden in full sights. People should have known. Now you should realize what the community was in 64. People were not interested in gauge theories. They had tried that, it didn't work, was not renormalizable, and they'd basically thrown it away. And Glashow made a model, but okay. And what they were concerned was strong interactions. The only thing they knew about was Goldstone bosons, and the idea was Goldstone bosons were nuisance because they were not seen. They were massless and they were not seen. So a lot of the work went, in fact, in avoiding the Goldstone bosons. And that's a big difference between the approach of Peter Higgs and that of François Englert. They are completely separate approaches. The first paper of Higgs essentially explains that you get rid of the Goldstone bosons. He doesn't notice that the gauge boson gets a mass. He doesn't pay attention to that. And that's probably why people were concerned with that.
We really don't have time, so maybe you can discuss.
But yeah, also I must say, Prof. Englert and Prof. Higgs, I'm not sure, they were coming from condensed matter physics, so they were extremely well aware of superconductivity.
Yes.
Okay, so let's speak again.
Okay, thank you. I give you this.
Okay, so next speaker is Marcus Christiani, and he's going to talk about recent results from Atlas.
Can you hear me okay? Can we start with slide 1? Oh yeah, okay. All right, so let me thank the organizers for organizing conferences is a very beautiful place. And the Atlas Speakers Committee for selecting me and giving you this overview talk for Atlas. Can you, in the corner there, can you switch that part off? Thank you. So you already heard a little bit about the Higgs boson, Atlas, and CMS. Atlas is one of the multi-purpose detectors. This is not just, where's the receiver? The batteries maybe is a bit empty or what? Okay, so this is so I have 50 minutes from now, right? So yeah, I'm glad to see you all again after this long time of all Zoom meetings. We are all fed up, I think. Yeah, Atlas is one of these multi-purpose experiments. It's a very vast and rich physics program. It's, of course, Higgs boson is very important, but there's lots of other things, the standard model, searches, also going here to look at dark matter, and feeble interactions, weakly interacting particle, dark sector, and so on and so forth. One of the very important parts really is also the precise measurements of all these things. It's not just searches at high energies. It's the standard model physics, which for which we can learn lots of things as well as quark gluon plasma, because we are also accelerating and colliding several ions. Overall, we have a fantastic data set of 140 inverse femtobarn to analyze. Run 2 concluded in 2018, which gave us the time to understand this data quite well. In total, we have about 1,079 papers, or there's one more that has been added. So as I mentioned, Run 2 is very well understood. We compare with simulation and calibrate this in several things. For instance, what I show you here is the trigger efficiency, electron and photon trigger, very important from a very large range from 5 GeV to several TeV. And the instant luminosity has increased in Run 2 by a factor of 4, and still we can still trigger in a quite good efficiency as shown here in different years. Also, muon I identified and compared with data in our standard channels, J psi to mu mu or Z to mu mu, for instance. Other things include here the electron identification versus pileup. In the TDR that was mentioned by Louis in the previous talk, we were talking about 35 typical interactions, whereas we have very good efficiency also at what we then measured at 60 interactions, pileup interactions. This plot here in the middle shows the complicated procedure to calibrate the hadronic energy, the calorimeter, that we quite understood quite well, or understand quite well. Or also we can do flavor tagging, identifying whether a jet comes from a B quark up with a sample of top quarks up to a level of 1 TeV or so. Okay, so this is the summary that summarizes it all. This is a comparison at the different energies, 7, 8, and 13 TeV for the different processes that Atlas measures. It's a very busy plot. But you can see here that it goes from really lots of orders of magnitudes here, the elastic cross-section at 10 to the 11 down to very rare processes, vector boson scattering, for instance. And what you can appreciate here is the measurement. It's the colorful thing that shows you the uncertainty compared to the theory, which is the gray boxes. And all over the place, there is not really any discrepancy or significance discrepancy that you can observe. So all these calculations that have been improved also, as we showed in Higgs, for instance, at the next to leading order, are really doing a great job, and all the measurements are also sitting atop. Okay, so I only have 50 minutes in total, so I have to make a very small selection of all the recent Atlas results. So I try to touch upon a little bit of all the different parts and concentrate on those that I think are the most interesting in the last year or so. For instance, Atlas has measured the total elastic cross-section. This was interesting because Totem had measured elastic cross-section was a bit lower than expected, this rho parameter. So looking at the differential in the Mandelstam variable T of the proton-proton elastic cross-section, how do we do that? We have low angle far away detectors, the so-called Roman pot detectors, which are housing tracking detectors, which can be put very close to the beam pipe. There are a number of quadrupole and dipole magnets to steer the beam and the particles. And we measure this as a function of minus t, this Mandelstam variable, and compare it to theory. And so what we find is, so this is quantified in the parameter rho, which is the ratio of the real and imaginary part of the elastic amplitude. We find this number here, and also we measure the total cross-section with quite a small uncertainty of about 1%. So this is the most accurate measurement of elastic cross-section at high energies. And these plots here show a comparison of the Atlas measurements, but also with lots of other measurements in a wide range of center of mass energy. And what we can say is that the common models that are on the market cannot really accommodate both measurements of rho and of the total cross-section at the same time. So this is an interesting thing to be followed up. Interesting measurement in the standard model is that Atlas now measured the joint polarization of W and Z. So we look at W and Z production at the same time, like in this Feynman diagram, and then look at leptonic decays and look at the polarization longitudinal transverse. You can see here that we categorize this depending on the angle of the leptons that come from the Ws and the Z bosons, and compare this with the sum of the backgrounds and the different options, whether this is transversely or longitudinally polarized, and extract then in the combination, so at these two-dimensional plots, for instance, the factor in front of the double longitudinally polarized here is distinct from zero. This is also what the standard model predicts because of corrections. You can see that all these correlations here, they are within uncertainties match quite well. Another topic of interest, of course, is the digermanium excess seen by LHCb first. So this is a candidate for a tetraquark with 4 charm quarks decaying to 2 J psi, then decaying to 4 muons. This is what LHCb saw. Atlas has inspected that and also added this other channel, J psi psi to S. What is really important in this 4 muon final state is to understand the background. So the background is not just a fit with the polynomial. The background is really a carefully studied sum of all single parton, double parton scattering, the mixture of Monte Carlo and data driven. So this shape here, the blue shape here, is really, I don't have time to show all the details, but it's really very well understood. And we can see then that we observe one peak here and a second peak here, confirming somehow the LHCb experiment finding in the J psi, and also allowing here a new channel to be seen. Coming to top quarks, this one of my favorite topics, of course, is the top quark cross-section measurements. Now it's also done at 5 TeV. So we have really measured the total cross-section, and at 5, at 7, 8, at 30 TeV. And even with a very small data set, only 216 picobarn, the total uncertainty is 4%. So it's as precise as the other cross-section measurements. So it's not just about statistics, it's about how you do the analysis right. What you can learn from here is, for instance, to improve the gluon PDF. You can see here with what you compare here is the blue one is a 5% improvement at x equal 0.1. Which is an important ingredient for gluon-gluon fusion for Higgs boson physics, for instance. We also observed the single top and the photon. This is shown here as a diagram, and measure there the fiducial cross-section when the photon is larger than the 20 GeV, for instance, and that also very well matches prediction. We can see that in the two plots here, this is with 0 forward jets. You expect a forward jet because of the single top topology. You don't see much signal in the neural network. And in the one or more forward jets, you see here appearing the more than 7 sigma significance. And also the background is this TT bar gamma, which was also seen a couple of years ago, is now becoming a background. It's well under control. Another thing seen recently in Atlas is a single top production in the S channel. The S channel is the toughest of the three, unlike at Tevatron. S channel in Atlas or ADHC is difficult because it's quark initiated with the cross section of only prediction of 10 picobarn. And this is the first time using matrix element methods and the per event probabilities. One can see here a TT bar validation region again, and the fit to the signal region where you can barely see the signal, but this is a 3.3 sigma evidence. And I show you here also for completeness all the single top measurements at 7, 8, and 13 TeV compared to theory measured by Atlas. And this is the first measurement at 13 TeV of the S channel. And another analysis was that is interesting is the 4 top production. So we don't only produce 2 tops at a time, but can also produce 4 tops, either in QCD or there are other diagrams involving the Higgs boson. So this is, for instance, is sensitive to the Yukawa coupling. The analysis is split in the number of leptons that are in the final state, 1 lepton or 2 lepton opposite sign, or 2 lepton same sign and 3 lepton. We call this one the multi-lepton channel. And we can see an axis here. We see 4.7 sigma significance with only 2.6 sigma expected. So there's more maybe, or certainly more that we need to understand. Especially if we want to improve our result, we need the better TT bar plus heavy flavor modeling. So TT bar with BB or CC is difficult, or we want to measure this and difficult to understand, as well as TT bar W. And the plot here on the right is taking all the bins in the fit in the different channels. They are reorganized according to their expected signal to background, and then you take the logarithm. So it's a complicated plot in order to show and convince you that there is some signal above the background in the very high significant bit. Okay, I now come to Higgs boson physics. We heard in the introduction already a bit that this is, of course, a key role in Atlas, discovered in run 1, 10th anniversary. We have now about, at the end of run 2, about 30 times more Higgs bosons than we had at the time of discovery. So we can do much more, of course. We can do better measurement of the total and differential cross-section, the couplings, look at new phase spaces, also make searches with the Higgs boson, look at properties, rare decay, and so on. You can see here how the cross-section evolves for gluon-gluon fusion here, factor of 2.3, or for more rarer processes like TT bar Higgs, it's even more convenient. It's an increase of about a factor of 4. And this is what Louis just showed, the discovery of the Higgs boson here at M2 gamma gamma. And this is what our M2 gamma gamma peak looks like now. So we have a Nature paper that came out recently, which summarizes all the run 2 coupling measurements. First of all, the cross-section, to the cross-section is shown here. It's a 1.05. The mu factor is this modifier of the standard model. So mu equal 1 means this is as standard model predicts. This is 5% above with an uncertainty of 6%. So all is under control. These are the diagrams that were probed in run 1. We had gluon-gluon fusion and vector boson scattering. In run 2, what we have also is associate production of Higgs with the vector boson, or also TT Higgs. And this plot here shows how the different production mechanisms and decay mechanisms are disentangled and then compared to their theoretical value here at mu equal 1. We can put this all together in a fancy plot with where we can probe the prediction that they all are on a line. By now, we have seen couplings to the third generation, top, bottom. What only is missing is the tau neutrino. But we also start probing the second generation. We see charm is quite difficult, but muon Higgs to dimuon is practically there. So for the total production cross-section, a recent result is the measurement of Higgs to gamma gamma and Higgs to ZZ. They are fully resolved and also then combined in the total cross-section. And you see they are all compatible and compatible with the theory, as well as a set of differential distributions like a PT of the Higgs, the rapidity, the number of jets, and so on and so forth. We have also delta phi, or for the vector boson fusion, for instance, the two jets. Coming to the Higgs boson mass, this is now known at the level of 1.4 per mil. This is the really incredible how good this can be measured nowadays, and it's also or mostly dominated by statistical uncertainty when you do the combination of everything. And here's the list of systematic uncertainty at the level of 40 MeV, and the peak, convincing you that this is quite well measured. More recently, given the large data set, we can look at the CP structure in the Higgs sector. So we learned from 1.1 that Higgs seems to be the CP even scalar, but of course there's room for an admixture of CP odd components, which are potential for CP violation. So we are interested in looking into that, and there are several ways and several channels we can look into it. The rates can be modified by that, but it's not so obvious. So rather look into interference effects on the shape. So looking at shapes is typically a bit easier. The coupling are a bit different. So for fermions, we would have them already at tree level, would be a modifier here in terms here in cosine and sine phi typically for even and odd parts. For the bosons, these are suppressed. These are dimension 6 operators, which are suppressed by the BSM scale. So if the BSM scale is very large, then we have a hard time to see them. So CP violation is studied in Higgs tau tau. Here you can see the acouplanarity angle between the tau planes. And this is one of the first analysis, or is the first analysis in Atlas actually, that completely takes advantage of the resolved tau decays. So all tau decays are explicitly identified and used, and several neural networks trained in order to get this result. And you end up here in the angle phi, which describes the CP violation, where you are not far away from the expectation of the standard model. There are other CP measurements. I can't go into in detail in all of this. There will be a talk right after mine about Higgs bosons in Atlas and CMS. Just pointing out that we are looking at both the fermion coupling, for instance, in TT Higgs, Higgs to BB, or the bosonic coupling in vector boson fusion, Higgs to gamma gamma. Here in Higgs to BB, you have lots of jets that you need to resolve. The assignment is not so easy. I need to understand the background, and in the end, you have this kind of plots that you can see here the contours as from a measurement and the standard model. And on the other side here in Higgs to gamma gamma, you can also see this d twiddle parameter, as this is constrained by using the gamma gamma or including it also with the tau tau. It was already also commented on during one of the questions. The Higgs pair production is one of the big shiny things that will happen in the hopefully near future, that probes the Higgs boson self-interaction, the Higgs potential. So Higgs bosons, di-Higgs boson produced here are probing several couplings here, the top coupling, for instance, but also the trilinear coupling. When you do this search, it's very difficult because it's only 1/1000th of the cross-section predicted with respect to the Higgs boson. And on top of that, there's also negative interference between the main, the reason is that there is negative interference between the main contributors. So the compromise when you do analysis to look at the two Higgs boson is to have one Higgs boson with high statistics, Higgs to BB, and the other to then give you the possibility to tag. But all of these are looked at: gamma, gamma, tau, tau, and BB. This is a summary of this, and in total we have a mu of a limit of mu smaller than 2.4 observed. When you add also the single Higgs analysis, for instance, also single Higgs boson can be produced like this, and probing the coupling here, we can see that we have some improvement in our overall constraint. This is showing that from going from the blue one to the red one, and then also to the generic case, or this allows us to go to the generic case, which is the green one, not making any assumptions on the couplings. Okay, so let's leave the Higgs sector and go to the searches. There are searches, all sorts of searches. I try to organize them a bit. Here, this is searches for extended scalar sectors. Is a bit motivated by potential excesses in in same sign dilepton events, where you compare same sign minus and same sign plus events. They can be produced for some of these couplings that you can think of, having here same sign top, for instance, or 3 tops, or even 4 tops. Often this is compared to a benchmark scenario. We take 2 Higgs doublet model with 5 states in total, and it puts some limits then on that. So taking this generic model here with different masses from 200 to 10,000 GeV, we see a maximum deviation here at the level of 2.8 sigma for specific values of this row couplings. You can also search for exotic and hypothetical heavy particles Y that decay to other hypothetical and heavy particles X plus a Higgs boson, and look at in the fully hadronic state. So that will produce boosted X and boosted B. So the jets will be all collimated and will be discovered or will be measured as one jet. This has been done for several hypotheses of the Y and X. So this is just a plot, which is an anomaly detection search using the bump hunter software. You can see here for a given X in the range of 75 to 95 GeV, look at the Y mass between 1.5 and 5 TeV. And you see here a small local excess at the level of 1.7 sigma. But if you look at in very many places, then you find something, of course. So nothing so convincing yet. And so we can exclude the mass range as shown here in this 2-dimensional plot. There's also a class of searches that are motivated by dark matter. For instance, a Higgs boson decaying invisibly, that we see that, of course, so you can see here, for instance, Higgs boson in vector boson fusion decaying to 2 neutralinos or whatever. There are backgrounds from Z to neutrinos that need to be taken into account. So overall, we have we put a limit of 14.5% and reinterpret this or put this in this WIMP interpretation. This is the spin-independent WIMP nucleon cross section. These are the limits that improve over existing limits up until the half of the Higgs boson mass. What is shown here also is the neutrino floor and other previous measurements, dedicated measurements. Other searches motivated by dark matters is typical this mono X category, where you have like one particle, be it a top, for instance, and missing transverse energy. And these are some typical non-resonant and resonant cases of such particles that could produce this. We look at in a fully hadronic boosted final state for top specifically, the mass reach here is up to 2.5 TeV. It also uses the non-resonant model. And in total, we can say this is the most restrictive limit on a single production of a singlet vector-like quark. And this is how the data looks like, and quite compatible with our background. Okay, another interesting dark matter search is there's when jets this decay semi-visibly or semi-invisibly, meaning that you have some fantastic coupling here with a hypothetical particle phi, producing you this dark matter particles that then interact into your detector and only leave fraction of their energy as a visible jet. And you would see that in a way that your missing transverse energy would align with one of these jets. So you look at the collinearity between the missing ET and a jet. You have several variables overall here. So the total missing transverse energy, the total scalar energy, the PT balance between the two jets that you're looking at, and you can see here how the different models would look like compared to our background. And so in the end, you can make a plot here, an exclusion up to 5 TeV of this hypothetical exchange particle M phi as a function of the fraction of the non-visible energy that you can, of course, vary between 0 and 100. So the generic search for heavy resonances is summarized here. You're not supposed to read them all. That it's just it's one of these plots that Atlas produces for the summary. What maybe among the heavy resonances, one of the category which is currently quite interesting is the leptoquark, because of, for instance, the flavor anomalies has some revival. Leptoquark decaying to a top quark and an electron, or a top quark and a muon. Here we have a mass reach of the level of 1.6 to 2 TeV. And if you look here at the effective mass, which is, so you cannot really reconstruct easily with all these leptons, neutrinos, the total mass. This is a measure of the total mass, invariant mass, and you see there is no excess here. Here I show a summary for the pair-produced leptoquarks. This is what was done here before with 36 inverse femtobarn by Atlas, excluding leptoquarks of the third generation at the level of 1 TeV. And this is now extended for a wide range of different branching ratios for different measurements. And one more leptoquark measurement I wanted to discuss is here in the B tau tau final state. This is a B producing a tau and the leptoquark, and then the leptoquark again decaying to a B and a tau. So you have a final state with 2 taus and 1 B. This single leptoquark production is somewhat complementary to the pair production. Looking in final states with lepton antidronic or two hadronic decaying taus, and in the final discriminant, you take the scalar sum of the taus and the b's, and see here that yeah, there's no room here for some excess. We can exclude therefore leptoquarks at the level of 1.5 TeV, depending on the U-cover coupling. And you can see that if you add the two channels, you get a significant better result. So this is interesting to pursue. All right, so the last category of searches that I want to touch upon is the long-lived particles. This also have gained some momentum. So we explore signatures in the detector that are, let's say, uncommon. So looking for displaced vertices in the inner tracking detector, or also for lepton which are not consistent coming from the common vertex. We look at decays in the calorimeter and the muon spectrometer and go then point back in time and in the space, as well as looking at the energy deposit, DADX, for particles that may be charged and metastable or also multi-charged. So one of these are the measurements or the search for Higgs and Z that are produced and not coming from the interaction point. What is done here is using the calorimeter information. So we have pointing capabilities, look at the common secondary vertex, and use variables like the transverse and longitudinal distance, put this in a multivariate analysis and search for these things. The interpretation is done in a specific SUSY model as a benchmark, but that's just in order to compare and get some numbers out. We would have here a reach of 350 to 700 GeV for a 2 nanosecond lifetime decay of a Higgs or a Z. Another analysis for long-lived particles is the search for heavy long-lived particles which deposit a large amount of DDX in our inner tracker. Such heavy particles would move significantly slower than the speed of light, therefore have a large transverse momentum and a large DDX. So what is done is this is reconstructed in the pixel layers. We have 4 pixel layers and can be probing up to or typically like 1 nanosecond, or at 1 nanosecond we can exclude masses of 100 GeV to 3 GeV. And the analysis uses several variables. In what is shown here is the PT of the track for different regions of DDX. This is a relatively small DDX. This is very large DDX, and we can see here that the signal for some benchmark here is showing up here. We even see that there are some points here that indicate a little bit of an excess. We have a 3.3 excess in the mass range of 1.4 TeV. But other than the DDX, we can then also look closely and investigate these tracks. These are 7 tracks actually. They show from the timing information that they are all compatible with beta equal 1, and therefore not having a C smaller than 1. So unfortunately, there's nothing new that we see here, or nothing uncommon, and so can put limits in a function as a function of mass and lifetime. What we can also look at is at displaced photons coming from exotic Higgs decays. This would be looking something like this. We have a Higgs boson decaying to the next to least, the lightest supersymmetric particle, and then decaying to 2 photons. Here again, we use the pointing and time resolution capabilities of the liquid argon calorimeter. And for the especially for the timing, we would this is the data, how it would look like for one of these cases, and see that the expectation here would be that you have a tail, and since you don't see this tail, we can put limits as a function of the lifetime and the cross section here. And this is a summary of the exotic Higgs decays to scalar particles, and we can probe cross sections here that are well below 10% in larger units of the decay time, with several analyses done here as summarized here. The interpretation can be also done in terms of effective field theory. This is also gaining momentum in the last couple of years. We don't see anything. We can try to put everything together and put limits on an extension. This is so-called standard model effective field theory. Here we have not only all the Higgs measurements, but also electroweak diboson measurements, and also measurements from LEP and SLD. In total, we have identified 28 Wilson parameters, varying 1 at a time. And you can see they're all compatible with being 0, with larger or small uncertainties. And you can also see where which measurements are participating in the constraint here. So coming to heavy ion physics, I'm not an expert here, but what is quite interesting is a recent measurement in lead-lead collisions of jet quenching. So if you have quark-gluon plasma, you would expect the jet production to be reduced. But this reduction is not universal. It depends on the type of jet. It depends on the nature, whether it's a quark or a gluon. Depends also on the radiation, so how large the jet is. And this is a bit shown here. So where you can see on one hand the BTEC jets, which seems to be, this is the different, the nuclear modification factor, which if it's 1, it says that there's no difference between the expected jet production and the quenching. And here you have a large decrease. So what you can see for the BTECs, for instance, it is relatively large compared to the normal ones. So indicating that this quenching depends on flavor. So flavored jets are less quenched. You can also see that here the gamma tag jets, these are predominantly quarks and not gluons. They are also expected to be less quenched with respect to the normal jets. And finally, also you have two different opening angles. So the amount of radiation also determines whether you have a suppression or not of jet production. And another interesting result in heavy ion is the production of so gamma gamma going to tau tau. So the photons coming from your lead collisions, and this will be or is sensitive to the anomalous G-2 in taus. And this you can see where the measurement is compared with also old results from lab. And here's our combined measurement and with the expectation. So this is quite interesting. And not only Atlas has gamma gamma to tau tau, it is also measurement in 2 electrons or 2 muons. So this is quite interesting. And the event would look like this. So how do you know this is gamma gamma? Is because you don't see anything else in the detector other than your muon coming from one of the tau decays and the 3-pronged tau decay on the other side. So and the rest of the detector is completely empty, at least if you put some threshold of energy. Okay, so in the last 10 minutes or so that I have, I wanted to, of course, advertise or say, like, you know, what are we doing now? So Atlas has prepared for the start of Run 3 with a number of upgrades. Maybe the largest one is the new muon, new small wheels in front of the detectors, which also got a new readout system, as well as an improved electronics for the liquid argon calorimeter, the trigger, new muon chambers, and also forward proton physics. The sheer size, so the project and the number of men or person power, and also the large the size of this project, of course, the new small wheel got the preference. Here are some pictures of how this was put into SR1, the building of Atlas, and then positioned in the detector, and seems to work quite fine. In May, there was first 900 GeV proton-proton collisions taken during stable beam periods. And you can see here an event display where a muon is reconstructed, including also the new small wheel that was inserted there. Run 3 started on July 5th with some media event that you might not have missed. At 13.6 TeV, so it's a small increase of energy, or quite some increase in energy. And here again, you can see one of these collisions at the new energy, where you see a muon reconstructed with a new small wheel, or also a full TT bar event, dilepton candidate with 2 B jets, a muon and an electron. So we can really do physics with this new data sample for sure. You can see some more plots if you're interested here. Okay, so what we looked at also is how does the detector perform? There are many plots that are being looked, of course, assiduously and frantically all the time. These are some of the plots that are already made public. For 900 GeV data, you can see, for instance, in the pixel detectors, the innermost detector, what the cluster charge is measured to be, compared to a Monte Carlo, a simulation with constant, with no change basically, or including the radiation damage that we expect, as well as the track PT resolution. The D0 resolution is the impact parameter resolution. Also for 13.6 TeV data taken only in July, shortly thereafter was these plots here showing the number of pixel hits that are used to reconstruct the track, also quite well described by our simulation, or how the alignment is improved, or how the alignment is improving the local X residuals here in IBL. So the collaboration is facing now a bit of a challenging period, because you're doing all this nice analysis of Run 2 data, which is still ongoing, operating the detector for Run 3, and also preparing for the phase 2 upgrade, which is happening only in a couple of years for the High Lumi LHC. This is the challenging program here, we'll get new muon chambers, upgraded electronics, a high granularity timing detector with LGATs, some other upgrades, and probably the largest one is the new inner tracking system, the ITK, which will have an all silicon detector up to the forward region of eta equal 4. So I cannot go in any detail. There will be also a dedicated talk, if I understand correctly. We'll have here Atlas, so several upgrades ongoing and several pictures tested. So this is a classical test beam or electronics and building up, measuring. So there are hundreds of labs all over the world that are preparing for the production, so that the phase 2 upgrade is going to be hopefully a success. Okay, so I didn't do so bad in time. Then I hear from my summary and conclusion. We can have some discussion. I wanted to show you that Atlas is continuing to produce results for the full run 2 data set, preparing for, or actually already starting here now, run 3, preparing for combination with run 3. Standard model measurements are done over a wide phase space. You saw this plot. We have reached of about 5 to 10% constraints on the Higgs boson couplings by now, and many different beyond standard model searches in dark matter or long-lived particles and so on. So the run 3 has started. We started collecting. I mean, right now we are not taking data, unfortunately, but the problem is hopefully soon resolved. In total, we expect a data set until 2025 to be double of the run 2 data set. And as I also briefly touched upon, we have a very significant effort for the Halumi LHC upgrade, where in the end we want to do precision measurements of the Higgs boson and also have some sensitivity to di-Higgs production and many other measurements and searches. Okay, and with that, we'd like to thank you and point out that there are several other talks also that you would hear about Atlas and CMS results during this workshop. Thank you.
As you know, the VTS is measured by BS bar mixing. Is there any, now with so many tops produced, is there any way of a direct measurement of VTS?
Yes, yeah, thank you for the question. So VTS is an interesting parameter that we would like very much to also look at in top decays and trying to identify the particle as being strange. In the LHC environment, this is tough. Because while B tagging works excellently, charm tagging is already really at the border. So there's no generous strange tagging. There is an effort, no, there are efforts of trying to see whether you can say positively identify K short or lambdas or something. So there would be not a generic strange tagger, but so I can tell you that there are ongoing efforts. So people are looking into it. But it is difficult, and so I don't want to make any promises or any suggestions that really we are going to measure. But people are looking into it. That's definitely something that that seems appealing. Thanks for the question.
Okay, for second question. Yeah.
Thank you for your talk. On slide 34, when you've been discussing the heavy ionizing tracks, there is kind of access in the high PT region. On the right hand side plot here, yeah, it's kind of quite significant.
It's intriguing. It's a 3.3 sigma axis. So this is really, yeah, it's a cool thing. The problem is, as I wrote here, is like we're looking on one hand on the DDX, but then these particles should also travel slower than the speed of light. So we have a second handle. We look at what is actually the speed of this.
I just want to clarify, the signature is just one heavy ionizing track, right? And
this is, yes, it's single.
Single.
Yes. So every track is looked at. So there's a set of candidate tracks. So this is already high DDX. I don't remember the normal number. So this is all tracks are taken, and about I think the 5% highest DDX are selected, and then they're put like in this plot here, and then out of them the even higher. So I mean it's a tail somehow, and then you say this is the largest one.
I see. Would it include actually also kind of disappearing charge track if it's long and entering the calorimeter? Well,
so disappearing where? So sorry.
Well, there could be some charge track,
yes,
which entering calorimeter and then disappear. For example, charge particle decay to say dark matter and very.
Okay. Well, this analysis only concentrates on the track seen in the tracker. So that would be a different analysis.
This is tracker,
yes,
only tracker.
Yes, yes.
Okay, but this could include, because it would just be in tracker. Okay, well, we can discuss offline, of course.
Yeah.
Very interesting. Thank you.
Okay, going to sure that Jim would ask the question.
So going to that, there has been some talk, okay, beta's around 1, we accept that, but it could be a higher charge to give you the d by dx. And so there has been chat that it could be say a doubly charged particle. Is that ruled out by your data? I mean, you've been looking at this more than I have, but so it could still be fast, but have more charge.
So to be honest, I think this is a question for the coffee break. I have to check, in the sense that I don't know the analysis in that detail to tell you. I imagine, but I better check, or we discuss later.
My question is on the energy dependence of the Higgs cross-section. And I would like to understand if this analysis is optimized for energy dependence, or is it just a collection of cross-sections coming from different analyses with different cuts, different number of subclasses, and everything you see. Yeah.
This one?
That's right, on the left side. You see, the question is technical, you see.
Yeah.
It's just a collection of what has been done, you see, at a lower energy, or do you have the analysis which somehow optimizes only this aspect of how the cross-section rises as a function of energy, which reflects gluonic origin of Higgs?
Okay. No, this really is the analysis at different. Maybe there's more to the question than what I understand. I think
I understand. You see, so that's why I am asking this question. I would like to understand. You see, whether finally, after 10 years, you are able to, you see, go to the analysis in which, for example, for the gamma-gamma channel, you keep the same number of subclasses, keep the same cuts, and then you optimize only the aspect how the cross-section rises as a function of energy. Because it is only
but we are not, right? We're not doing this. We're not looking at how the cross-section, we are measuring the cross-section as a function of energy. So
that's right.
The rise is not something that we as an experimentalist are
you're absolutely right, you see.
Or whatever.
No, but you can do this measurement in the way in which you will see totally drop all the errors having to do with the step-by-step rise of the energy by having the same number of subclasses for events, the same cuts, and then you optimize the precision of this measurement. For me, this is important because it is only the Higgs production mode plus the boxes which probes this rise, which is given by the X dependence of the gluon distribution.
Yeah.
So I would expect some optimized analysis after 10 years. You see.
Let me see whether I understand your question. So you mean rather than looking at several data sets, 7, 8, and 13 separately, you would like to see them together and say, let's do an overall analysis.
That's right.
And have the same bins in all this. Yeah, maybe I should defer this question. I don't know whether the speaker after me can answer this question, whether this is indeed redone for the 7, 8, and 13. Can you give Lydia a microphone?
So it's not directly done, but it's indirectly done. So at each of these measurements, because they're done in different years and on a completely different data set, they chose to do an inclusive fiducial region, which is kept the same between all 3 measurements. So in that sense, it is the same measurement, but it's not in the same bins. It's inclusive in a specific fiducial region which is assigned for this measurement. So it's on an unfolded data set, which means that it's tried to remove all the detector effects already. So in that sense, yes, but it's always a little bit of there's an additional uncertainty assigned to how well you can do that, but yes.
But this is how you do that's why you do fiducial, right? You try to remove all the detector effects, and the detector wasn't the same. I mean, the detector isn't the same between 7, 8, and 13 dB, and the data taking, the triggers, and so on. So you try to remove it as well as you can. You go into the fiducial space, and then you are doing what you're looking for once you have the fiducial.
Yeah, it's in a completely inclusive bin. Yeah, it's not a sum over the.
But it comes, okay, so it comes from there, right? So you cannot talk it away. So it comes from there, and then, yeah, data is massaged in such a way that it's inclusive now, yes.
Okay, so let's move on to the next talk. So let's thank speaker again. So the next speaker is Lydia Brenner. And she's going to tell us about Higgs boson property measurements at the ATLAS and CMS experiments.
Yes, they're definitely uploaded. Okay. While he's loading the slides, let me just start by saying that I will try to not. So some of the plots that you will see in my talk have already been shown in the previous 2 talks, but I'll try to focus on some different aspects. Also, I will be talking on Higgs results coming from both ATLAS and CMS. But I am not in ATLAS, so I will do my best to also communicate the CMS results, but I will always have a bias towards the ATLAS results, just as a caveat. Online, or do you want to download them first? Second one. Yeah. Okay. Right. So I'm talking about the Higgs boson properties only. So that particle over there in the corner. So what is the Higgs boson good for? Well, in the standard model, it's the origin of the mass. It's responsible for the electrosymmetry breaking, but also it's a good potential link to new physics. So if it's the particle that couples to massive particles, then any new physics with mass, you could assume also couples to the Higgs. So in terms of searches for new physics, I'm going to only focus on that link. So we've already seen a nice overview of the timeline of the LHC itself and Higgs, but I'm going to just focus a little bit over on the Higgs timeline. So here, before the 4th of July 2012, you have we were still setting limits on the Higgs boson. So here we set a limit saying that if it exists, it has to be in the mass range of 115 to 130 GeV. So people started, although there's a little option there in that region, starting to get a bit discouraged. Then on the 4th of July, obviously, you have the Higgs boson observation. So you can see here the same plot that was in the first talk of today, where you see the peak on the Higgs to gamma gamma spectrum. Then we fast forward to run 2, and we get observation of the 3rd generation Yukawa coupling, so the top coupling and the bottom coupling. And now we're going forward to run 3 and high luminosity LHC, when we just celebrated our 10-year Higgs event, so 10 years since the discovery of the Higgs boson. So I just wanted to indicate a little bit what I mean when I say that we're going towards precision physics. So here on the left, you see the Higgs to 2Z bosons a peak from the end of run 1. So here in red, we see the Higgs peak lovely coming up and saying, yes, we have found this Higgs decay. Now in run 2, we see the same thing. And of course, Atlas decided to swap the color scheme around. So now the Higgs peak is actually no longer red, but the red is the background. And the blue, which was the background, is now the Higgs peak. So I tried to indicate here with a dotted line what the same number of events is. So the same number of events in run 1 is here, very much inside this background that is clearly not the Higgs peak, with a very, very clear, lovely Higgs peak coming up again over it. So now we can actually do some precision measurements, meaning we can really investigate this peak. Okay, it scrolled down a little bit. So I just wanted to say a little bit about some of the different production modes. So what you can see here in blue is the gluon fusion diagram for producing the Higgs. So you can see most of the Higgs production goes through there, followed by a vector boson fusion. And these were already indicated in the last talks, were used in run 1, predominantly in run 1, to look at the Higgs production side. Then you have some smaller parts, such as the associated production, PH, and the top production, TPH. So then, of course, the Higgs also needs to decay. So the large part here, the branching ratio, this one is the Higgs decaying to 2 B quarks. And you might wonder, if this is the biggest one, why isn't that the one where we discovered it, but came only in run 2? Well, that's because these are very difficult to measure in the detector. So then what other ones do you have? You have the Higgs to WW over here, which is the next largest. You have Higgs to ZZ in the top here, Higgs to tau at the bottom here, and so forth. Quite a lot of them. Okay, so what can we say about what kind of what's the Higgs boson landscape? What kind of properties can we measure from the Higgs? Okay, so we can measure the mass and the width of the Higgs. We can look at coupling properties such as fermion interaction. Well, that's new for run 2. We can look at inclusive and differential cross sections. Again, that's something we can do new. We can look at an effective field theory interpretation, was already briefly mentioned by a previous speaker. We can look at quantum numbers such as the spin and the CP. We can look at the self-coupling, so the di-Higgs production. And then, of course, we can look at rare, exotic, and invisible decays. Now, I wanted to say a little bit more about what it means to have a lot of particles. So in run 2, there were in the 139 of this bar, that is how much Atlas measured. We have about 7.7 million Higgs bosons produced. Now that's a lot. However, I wanted to just compare it with a few of the others. So in terms of top quarks, that's 275 million. But if you go to the Z boson, it's already 2.8 billion, or the W boson 12 billion. So in comparison to those, it's still not that many. Okay, so here we have the LHC ring with the Atlas and the CMS detector on it. Lovely at opposite ends of the circle, but predominantly having the same goal, measuring everything that comes out. So let's look at the first property. Let's look at the Higgs boson mass. Well, as was also already mentioned in our first talk today, there is one free parameter in the standard model, and that is the mass of the Higgs boson. And this is now among the most precise electroweak parameters that we've measured. So here on the bottom, you can see from run 1, the combined measurement of Atlas and CMS, which had an uncertainty of 250 MeV, approximately. Now, if you now look on the right-hand side here, you have, for CMS, you have the run 1 plus the 2016 dataset only for the Higgs gamma gamma and Higgs ZZ, and it's already surpassed that. That doesn't include, so that includes just 2 channels instead of all channels measured. For Atlas here, you have a single channel, Higgs to ZZ, for run 1 plus full run 2, and you get a very precise measurement. So now we get into this plus or minus 118 or, sorry, 180 or 114 MeV. So quite precise measurements. So let's look at the coupling. So for this, we combine all sorts of production and decay channels. And you've already heard here, we use this mu parameter to indicate the signal strength. So if the mu equals 1, that's perfectly standard model, and anything else is a slight scaling of that strength. So these are both from the 10-year Higgs event Nature papers from CMS and Atlas. So here on the bottom, the first 2 plots you see are from CMS. So here in the middle, you see the Higgs to mu decay, for example. So this is the 2nd generation coupling. It's lovely, it's added here. And on the left-hand side, you see all the different production modes from the Higgs, where we look at all the decays at the same time and then extract the production overall. And the same 2 plots are here on the right from Atlas. So at the top, you see the different production modes. So we can actually get a very precise production information from combining all these decay channels. And on the bottom here, you see also in the last bin here is the decay to mu, so the 2nd generation coupling. So this plot here, you've also already seen in the previous talk. So we combine all these production and decay channels, and you see in general, as long as all these dots are sort of on this diagonal, it means we're matching well with the standard model. So far, so good. And I just wanted to point out one thing here in the Atlas plot. You see here in gray, you see this added charm 1. So this is the limit on the charm coupling, which has been added. And for all the other points, you can actually see, if you look carefully, it's not very easy to read. You can see a colored dot, as well as a sort of a gray outline behind it. So the gray outline here is the same where we actually leave the charm coupling free floating in the fit, while the other ones, it's fixed. Okay, so then what else can we do while we're busy combining all this information? Well, we can look at, for example, the coupling to the vector bosons on the x-axis versus the fermionic coupling on the y-axis. So we combine it all into one parameter. This is this kappa parameter. So kappa parameter is again one of those scale factor parameters that was added. So everything being 1 is perfectly standard model. And this kappa squared approximately scales with the cross section. So what you can see here, if you first on the left-hand side from CMS, you can see in red, you can see the lines as were made during the discovery of the Higgs boson. Then in blue, you can see the full run 2 measurement. And then this is the run 2 one is in black. So you can see the increasing precision on this measurement. On the right-hand side, you can see an overlay, this is then from the Atlas side, of all the different decay channels. And what you can see very well here is that different decay channels also have different sensitivity to different couplings. So for example, if you looked at Higgs to WW, which is this light blue-gray or blue-greenish thing here, you can see that it's quite sensitive to, okay, bosonic coupling you expect because it's in the decay, but because it's got actually so much, there's quite a lot of Higgs to WW, it's one of the larger decay channels, you can get a lot of gluon fusion. So you actually got a pretty decent sensitivity to the fermionic coupling as well. Well, for example, the Higgs to ZZ is exceptionally good in the vector boson coupling because it's such a clean signal for Higgs to ZZ. There's very little background in that channel. You can also have a very good measurement of the vector boson fusion. And then all these combined get here in black, a nice little circle. Okay, so let's talk about the CP measurements. So we've already, again, heard something about this in the previous talk. So what we try to say is, okay, CP Higgs, a standard model Higgs is CP even under inversion. So if you look here, you have the Higgs decaying into, for example, the two tau particles, and you see an angle between these two planes in which the taus live. Now, if these two planes are parallel to each other, it's CP even. If they're perpendicular, it's CP odd. So in this case, we look at how well can we exclude the CP odd hypothesis. So here you see the angle. Well, we all use different, in the CP measurement, there's constantly different parameters that are used for the CP angle. But in this case, you see here from CMS and from Atlas, so both of them expect to measure 0 here, and you get a exclusion on the CP oddness of the Higgs. So that's for CMS here, 3 sigma and 3.4 sigma from Atlas. So then you can also look at the top or bosonic couplings. So here you see, for example, Higgs to ZZ, that's in red, and Higgs to, Higgs to multi, that's one, and then Higgs to gamma gamma and Higgs to ZZ in blue. And here you see the CP odd even coupling on the x-axis and the CP odd coupling to the top on the y-axis. And you have here the standard model expected is this diamond here, and the best fit is over there, but it's still very much compatible with the standard model. That's the CMS side. Here in the middle, you see the Higgs to gamma gamma from the Atlas side. So here you have the CP oddness measurement, which you expect to be at 0, which you get here in blue. You see the exclusion. And on the far right, you see the CP Higgs going to dB. So this is again the top coupling. So here we have the CP even coupling versus the CP odd coupling, where this is written there now as a cosine alpha versus a sine alpha. Okay, so then again, you would expect it somewhere here, and it is also somewhere here. Okay, so that's very nice. And that gives a disfavoring of the pure CP odd hypothesis for the Higgs top coupling at 3.2 sigma from CMS or 1.2 sigma from Atlas. There is actually an older measurement from Atlas, the TTX going to 2 photons, which also tries to measure this top coupling, which is a little bit stronger, which is from 3.9 sigma favoring the CP odd. Okay, then we get to these differential measurements we've already discussed also in the last talk. So we can do finer granular measurement for specific observables. And then we can measure a large number of distributions and compare with various predictions. So for example, here on the left, what you see is in black, you see the combination of the Higgs to gamma gamma and Higgs to ZZ measurement. And then in all these colored block boxes, you can see all the different predictions that were made. And as we've already mentioned, this is a differential analysis, which means that we try to go back to the particle level parameter space. But you don't, this is in the PT of the Higgs, but you can also look at the ET MIS, for example. And these kind of distributions then give an additional you can additionally infer new information from that, such as couplings that are not directly accessible. You could, for example, think of the Higgs-charm interaction. The Higgs-charm interaction, the charm also gives a contribution to the gluon fusion production loop, which would give a slight change in the spectrum of the PT of the Higgs. So you could try to access that indirectly rather than going to try and look at the Higgs CC directly. Or you can look at Wilson coefficients of an electroactive Lagrangian, which I'll come back to in a few slides. So that was from Higgs to gamma, gamma Higgs as a set. But here, for example, from CMS side, you see also the Higgs to tau tau. You have the number of jets, or it's from Higgs to WW, where you can also see a nice split where they try to show for the prediction the contribution of different production modes. You can actually look at many of these different distributions. So you can do the PT of the Higgs, however you reconstruct it. You can look at the rapidity, number of jets, the PT of a jet, the mass distribution of a dijet system, the angle between jets, or the ET miss. This is just not even all of them, but this is all some of the ones that are looked at. So then we can look at this anomalous interaction search with this effective field theory. So what do? We look at everything as if it's a point coupling. So if you have here the gluon fusion loop for the Higgs, we just say, okay, there's a point-like interaction. And then this standard model EFT is a high energy interpretation. What does that mean? It changes the Higgs boson properties due to some effects of new physics at a higher scale than what we could measure. And this is, for example, applied to the Higgs to gamma gamma differential analysis. So here you see some of these differential parameters that I just talked about in the Higgs to gamma gamma analysis. And you can see how they are different. So you have all the different dotted blue lines here for different values of these Wilson coefficients. From that, so we have this combination in Atlas for the Higgs results, the electroweak results, and the LEP results. This was already mentioned briefly. So here, everything is 0, it's perfectly standard model. Anything other than 0 for these Wilson coefficients means new physics. And you can see here on the right, you can see the different contributions, whether it's coming from Higgs in red, or from an electroweak measurement, or from the LEP measurement, depending on it's in green and in yellow. So you can see what measurements constrain it. What I like is that you can actually see that some of these parameters are constrained fully by one or the other. So using the LEP results actually gives a better sensitivity. Okay, so then what else can we do is we can probe the Higgs self-coupling. This was also briefly mentioned already. So it's essential in electroweak symmetry breaking that we also now measure the Higgs boson trilinear coupling. And this self-coupling can be either probed using the di-Higgs production. So for example, through a Higgs decaying to two Higgses directly. Then you have this coupling here, which is the self-coupling. Or you can have the single Higgs next to leading order electroweak effects, for example, by having a loop inside our vertex. So you see here on both sides, you have the kappa lambda, which is the self-coupling. So if we look at from CMS, it's a nice result, which is on this kappa measurement, which is again expected to be 1. So if we have a direct search for the di-Higgs production, you have the measurement over here, but the indirect interpretation, which is the single Higgs interpretation, so the contribution from this kind of a diagram, you see here on the bottom, which is nice to compare. So what kind of constraints can we put? So we can see here, you get the, okay, so these different ones are just whether it's the single Higgs or the di-Higgs or both. And you can put some constraints on this kappa lambda. So you can say kappa lambda has to be between -0.4 and 6.3. So we want it to be 1 for the standard model. It's not a very stringent constraint yet. This is just because I like comparing the same kind of plots between Atlas and CMS. So this is slightly older results, but the final result is pretty close to the Atlas one. So then we can go to high luminosity LHC. So we can look at some projections, for example, for the self-coupling. So here you have all the different di-Higgs decay channels, which you can add together. And you can see here in the black line, the projected high luminosity LHC kappa lambda prediction constraints. Here on the right-hand side, you see a very interesting, in my opinion, very interesting one. So this is the charm coupling on the y-axis and the bottom coupling on the x-axis. And you can see that now here you would actually be able to put a nice constraint on the charm coupling. So this would be from the direct Higgs to CC combined with this indirect gluon fusion measurement. So you would expect it to be over here at 1, both of them, and you would be able to make some sort of exclusion like this. So that brings me already to my conclusions. So what I would like to say is that we're at the start of a precision era in Higgs boson sector, where we go towards less than 10% uncertainties, which comes partially from the increase of, mostly from the increase of the of statistics, but there's also actually behind the scenes a lot of other things going on, such as improvement of theory predictions and methodology, which reduces the systematic uncertainty. Now, what we're doing is we're switching from the discovery to properties measurements using third-generation couplings, photon couplings, and couplings to W and Z bosons. And then in that case, we're looking at, for example, differential and fiducial cross-sections, but we're also focusing on rarer processes, such as measurements of second-generation couplings, and probing the charm-Higgs interaction and Higgs self-couplings towards the high luminosity LHC. We can focus on kinematic distributions and look at these effective field theory interpretations to find stuff at higher energy. Thank you.
Thank you very much for the very nice talk. Question?
Forgive me once more for technical questions.
Go ahead.
You see, for the measurement of CP properties, CP evenness or odds, or for example, the quantum numbers of Higgs, do you do the analysis now of the sidebands? You see, for those Higgs decays that are exclusive, like for example to tau tau, or for example to ZZs or BBs, can you go outside the peak and find out if you would be sensitive? What do you measure in the sidebands? Just to first find out, you see, in the old-fashioned way, how sensitive you are when you are going to the, you see, to the peak. So this was something that I was asking at the time that I was interested in Higgs, and this has never happened. And so my question is just the curiosity. Is it now happening that you do this analysis in such a way that you go to sidebands and you first check your sensitivity and then you go to the peak?
Okay, so we do some checks in the sidebands now. For example, on the CP. The problem is that the amount of misidentification in the sidebands is, especially for channels like Higgs to tau tau, is still so big that we don't get any significance or even cross-check for what the sensitivity really would be. In channels like Higgs to ZZ, it's a little bit better, but it's really added just as a sanity check, we call it, rather than as a measurement.
Just a question about the slide 12, where you present the accuracy of the latest combined Atlas CMS. Do I understand correctly that on the left-hand side, the discovery, it's the large contour related to the time when Higgs was discovered and coupling was not measured quite precisely? Okay. Now, okay, thanks. One more question. There is a standard model position and the current cross for boson Atlas CMS pointing that there was or the order of 2 sigma, but in both experiments actually slightly below. If you combine both, maybe you get higher, but it's like they're systematically below in kappa fermion on K fermion. Does somebody look in some particular channel to clarify what is related to? What exactly this related to?
That's a good question. So there's different couplings that go into the kappa F side, in the fermionic coupling side, and they are not all systematically below, but indeed on average they are, and they are not exactly the same channels that are below in Atlas and CMS. So we are talking about doing a new combination between Atlas and CMS to see if we can get any kind of significance out, but even the back of the envelope calculation of the combination would not be above 3 sigma, which means that we are not prioritizing doing that combination yet.
Thank you.
Have another question there?
I don't know if you refer to Higgs flavor changing couplings. You know, at one point, as you know, there was some rumors for H mu tau. I didn't see in your talk any limits on that, and it's such an important event. I mean, we should know what is the size of the upper bound on the coupling.
Okay, so that I have to say I'm not an expert in that one.
Okay.
So I know that there is the Higgs rare decays channel, which is looking into, among other things, this decay. And in the combined plot, let me see if I can. In this one, it's basically still so large and going off the side on both sides, like why we actually generally don't include the charm already here, that we don't include it in these summary kind of plots. But there is, I know there is at least in Atlas a dedicated analysis that is trying to measure that. It's quite a difficult decay channel though, mu tau. You have a lot of mismatching, which you have to, misidentification of the leptons, which you would have to correct for.
But you agree that it's a very important coupling.
I agree that it's important to measure it, yes.
Yes.
So we have a last question in the back of the room.
Just doing a naive back on the top of my head computation, you said about 8 millions of Higgs, and then I'm looking at the muon decay channel, which is about 3 orders of magnitude smaller than that, which give me a few thousand events for the muon. And then I see the uncertainty is 40%. Then I got puzzled because I'm expecting it to be a relatively clean channel. So where do you lose the statistical significance in the muon channel?
Okay, that's a very good question. So the problem there isn't actually measuring the muons. The problem is that there's an irreducible background from Zhao-Yan, which is incredibly large. So in the, let's see if I have I'm going to just use a very odd plot. Here at the top, you see the Higgs gamma gamma, but the Higgs mu kind of has the same sort of shape. So it's a small peak on a large falling background. Now, to model the background correctly, where we don't have quite good enough sensitivity, we get quite a large uncertainty from that, especially because we might have some mismodeling of that gives some spurious signal, which we can't get rid of yet. And we're quite conservative in how much uncertainty we give to that, to be honest, especially in Atlas. CMS is a little bit less conservative. But we say that basically because for every bit of that we don't know, we give an 100% uncertainty. That's what really drives up the uncertainty for Higgs mu.
Okay, so thank you very much.
Thank
you again. Okay, so we have a coffee break for 30 minutes.
It is my pleasure to welcome Professor Bucella, Franco Bucella, who is going to give us a talk on the Planck formula for gluon distribution in the proton. I will give you a 25. So when you see a 10 minutes, it's 25 plus 5. So when you see a this. To change Franco, in the pocket, no? Yes. And it's like there. Just to change. To go up.
And this
this to
okay,
advance.
this,
to advance.
This one to advance and this to go
backward.
backwards.
I thank you the kindness of the organizer invited me, despite I have a terrible defect that every year I become less young. Oh, then with my collaborators from Bari, I don't see them there, but maybe once there should be. I present this, I will try to transmit my enthusiasm by the fact that there was a very important confirm that the boundary condition for the Glap equation are fixed by quantum statistical mechanics. That simplifies a lot the formal, the parameterization, especially at large X, where the experience is not so great. What happened? Let's speak about the summary, in which, you know, QCD, which has been established almost a century ago, explains the funny behavior of the hadrons, for which we have confinement at large scales and asymptotic freedom at small scales. This is a consequence of the group theoretical equation. Then it was very important Parton model introduced by Feynman by more than half century ago to describe the scalar invariance of the binary scatter Slack, which was the proof which gives rise after to QCD. So it was very important that after some period in which quarks were simply mathematical concept, then they have a physical concept despite their confinement. After some time, the Glap, Doxischer, Grifo, Libot, Altarelli, and Parisi equation describe the dependence of the Parton distribution in the perturbative regime. Of course, there is a perturbative regime that requires that Q square is sufficiently large, small scale, and after you should know at the initial scale, and after this equation gives rise to the Parton distribution at every Q square. Then, from the basis of the observation of Feynman and other physicists, one has some idea on the boundary condition, especially on the boundary condition at large X, where you have less information from experimental. There were before two Japanese, Niagawa and Sisiki, but also Feynman and Field, that they observe that there are in the proton more d bar than u bar as a consequence of Pauli principle. This was an observation that I will show will be confirmed by experiments. In fact, there is a defect in the Goffert some rules. Some rule which says that the bar is larger than U bar, and also in the Rayleigh products in PP and PD, which is P plus N scattering, because the proton prefer to meet a neutron, because in the neutron there are more U bar, because there are less D bar in the neutron for spin invariance. Let's see if I'm. Opla, no? Come. The right. The sign of the beta function, which is well known, says that you have this theory, QCD, this is the reason which has been accepted, that goes from infrared slavery, where hadrons, for instance, baryons, are simply described by 3 quarks in a completely antisymmetric color configuration, but while in the region in asymptotic freedom, they are completely a different thing. In fact, they are incoherent, while a small was coherent. A set of quarks, gluons, and even antiquarks with a given probability, with some rule, part of some rule. The one for the momentum that says that all the partons take the momentum of the proton just in the direction where it meets the virtual photon in deep inelastic scattering electromagnetic, and also the condition for the proton that there should be more U than U bar, because proton and then more D than D bar. Once is 2, one is 1. Let me see. Let me see this. Oh, then since the Glapp equation gives the evolution, it's important to know from which the values which are not predicted, because non-perturbative QCD is a difficult to make with the lattice, but it's not so simple. And they usually took this form, which is A is B, 1 minus C times a polynomial. It's a primitive formula to say that with B and C positive, it begins to increase and after decrease. And there is also a polynomial to adjust. You know, the fact that to have the behavior x equals 0, x equals 1 is not a very good idea, because especially at the zero square, when it begins, where you put the conditions, they are away of the domain of Parton model, because Parton model x equals 0 means q square equals 0, and so large scale. X equals 1 is elastic scattering, and so we have the situation in which at q0 square, which is not so big, only a certain range of the x interval is good for Parton interpretation. Of course, with the increase in q square, this range becomes larger, but at the beginning is not. So it was an idea at the beginning to use this formula, but I see that while the part for x up to b is not so bad, this part u1 and xc is has nothing to do with the behavior at large x, and oblige the people that use this formula to introduce a lot of parameters. Then the method, the use of a polynomial is also justified by the fact that they write momenta, x n, p dx, dx, and then this momenta with the Glapp equation have the behavior simple. But anyway, I will show that following the idea by Feynman and the other people, which have proved, then should be a different behavior detected by quantum statistics. Let me see. Opla, yeah. Oh, see. No. Oh, so the problem is to find a distribution following the idea of Feynman and the other people. Also, Feynman was the inventor of Parton model, so some confidence on what he says. Also because the hypothesis that the the bar is larger than U bar has been confirmed experimentally. So a theorist or general physicist, when there is experiment which shows a property, should ask why this is the reason. Let me see if then they say that it's Pauli principle. They say there are two valence quark in the proton and only a 1D, so it's easier to make a DD bar than U bar. It is evident. But then one has to think that the Pauli principle has an effect only for quantum statistical mechanics. So you should use quantum statistical mechanics if you want to impose the Pauli principle as experiment suggests. Let me see, I left. In fact, they got some rule that should be 1/3 is less, and this is less because the bar is larger than U bar. And then if you take this ratio, this is always larger than 1 and increases. So then this is the reason that you have to use statistics. Let me see if I remember. Oh, but there is not only the prevalence of the bar and U bar to say that there is role of quantum statistical mechanics, but this is a correlation between the shape and the first moments of the non-diffractive, because you see that at small x there is a diffractive term maybe created by the gluons, but for the valence part of which dominate a large x, then there is this fact, there is this correlation. In fact, the fact that the ratio of Fnd to F2n to F2px, cioè neutron and proton, decreases in a certain region and decreases not a large x, but in a region from 0.2, 0.5 is a proof. It's like a Fermi sphere, that if you have more particles, you have more energy. So the particles which are more present in the proton should have a broader distribution. But this does not happen only for the unpolarized, but also for the polarized. So for the polarized, you have a correlation, a perfect correlation between the moments, the first moments, and the form of the distribution, which is broader. So another very important proof that you have to apply quantum statistics mechanics. In general, there is a reflex that one statistics which is variable the energy. No, but the reason why is the energy, because there is the rule that the sum, the total energy is given. This is the reason. Since instead the variable which appears in the part of model is x, the temperature, which makes the role of the temperature, and the potential should be adimensional parameters. I think that unfortunately this concept by my colleague, even by the theorists of elementary particles, it was not known, even by my collaborators, but I succeed to explain to them. As what I said before, that one should know that the variable should be x, and so also the temperature should be adimensional, just because there is not the energy sum rule, but the part of model sum rules. Let me see. Then in 202, 20 years ago, with Burelli and Sofer, we proposed there are, I want to put your attention on the form, because there is a diffractive term that is equal for U, unpolarized, equal for U bar and D bar, because otherwise the Goldwasser rule would not converge, because this is an exponential that makes infinite number of parts. But the important part is the part which is related to the valence and their antiparticles, as this typical expression. This expression has this property, this interesting property, that the denominator for x smaller, for the x bar is potential to x bar, which is the temperature, smaller than 0, is negligible. Instead, it becomes large for x larger than potential. So you have a distribution which increases for this is the x qx increases at a certain value of x, then the denominator from 1 becomes 2, and after goes to the Pound potential, to the Boltzmann potential. And then we have put to comply for data this factor which should not be there, x a q and the denominator, to comply for data. But we succeeded to explain these parameters by extending to the transverse momentum, and say that if a distribution is larger, is broader in X, is broader also in PT, and this justifies that. In fact, this is a good formula. This good formula has not so many parameters, because you have for the quark and the anti-quark two parameters, two parameters for the diffractive part of the temperature, but is the same for that. And then we have only the potential. So really a very economical form. But the important thing that also for the gluon, which is the important part of my seminar, we shall find the same temperature then for the quark. So this is a very important point to confirm the validity of the part of the statistical approach. 10 minutes. Yes, I hope I succeed. Thank you very much. For the gluon, because we have another important property which we have taken from Balerao, that it says that in the point Q0 square initial, then should be equilibrium with respect just to the processes which fix the Glapp equation. So emission of a gluon by a quark, a transformation of a quark in a pair of the gluon in a pair of quark and antiquark with opposite helicity. So we have for the equilibrium that the potential of the gluon is 0, and so instead of Bose-Einstein you have a Planck. No, and also we understand all the asymmetries in the C of the proton just for the fact that the potential of the non-diffractive part of the antiparticles is opposite. So you have delta bar positive, delta d bar negative, and explain d bar larger than u bar. So in a way, with a few parameters, we understand things one. But the important thing that I want to say is that while when you study deep inelastic scattering, then important things are quark antiquark, because gluons enter simply in the equation of the logarithm variation. When you instead study also the processes at LSC, which is a gluon machine, then you have more information for the gluon. And the fact that, as I will say, that when we study the gluons, the analysis of the distribution of gluons made by the Atlas collaboration, the base LSC and their results, all posterior to the one we did, we found that we can put the same X bar that we put for the quartz, for the valence quarks, which is very important because no other theory predicts that the behavior should be the same for a large X for the gluon for the valence quark. Let's see. Oh. Speak about the grid because this also this explains that the gluon are not polarized. Let me see. Oh, then in the work of 2002, we found the data. You see, the number of parameters is small. They have all the X bar and the potential, the physical meaning. And then we have this temperature X bar, which is about 0.1. And then we have also the term, the gluon and the diffractive term. And not so many parameters we expected for all these things. Okay. Oh, I spoke about that. The fact that this equilibrium condition predicts that delta D bar is negative, delta D bar is positive. They are smaller than the delta D bar minus bar, and also the D bar minus bar is smaller than delta U bar minus delta D bar. Of course, the second part is a different measurement, but the contribution of the anti-quark to the Bjork-Ansam rule is welcome because with only the quark we are not right. Quindi we think that when should be a test of the approach, when should be measured the isovector part of the polarization more precisely, also the three are satisfied, but also the fourth will be satisfied. Right. Oh, then the important thing that I just said before, that we write the form for the gluon we introduced in 2002, but then comparing with the more important data that the Atlas collaboration found by studying ERA and LHC. And then you see that you succeed with the same X bar found, which fixes the behavior of the valence particles around the potential and above with the same potential, and with the data for the GBG, which are very similar to the one found 20 years ago. And now we have a more precise. Look that if you just make the curves, they are very similar. This is very important. Let's see if. Yes, no, thank you very much. If let's see if the figure. This figure is describes very precisely Gaussian distribution, very precise, and we is bar fixed by the valence quarks, only two parameters, practically one because the gluon transport a certain part of the momentum, and while when in the expression found by the Atlas collaboration, of course, as everyone uses this polynomial expression, you have a polynomial AXB1 is 4 times a polynomial minus a prime xbi prime 1x c prime, a very complicated formula. I just wonder if you found from the radiation in the first moment of the university, the polynomial instead of the Planck formula. No one should have understood everything. Of course, this Planck formula is the one suggested by theory and requires a less number of parameters. I just anticipated, because I'm going toward the conclusion, that the reason why they use the polynomial because with the method of computing the momenta is easier with the polynomial. But since the momenta are important increasing n with the large value of x, if you, for the large value x, you have a stupid parameterization, let's say in this way, then you will have less precision. In fact, normally there is very less precision at large x because large x is predicted with the behavior near x equal 1, which is away from the domain of the part of the issue, and where there is very small information because a large x becomes very small probabilities. Instead, the parameters which fix the large x behavior in this approach are fixed by data in the region where deep in part of model is valid to smaller x, and when the parameters, there is a lot of data. So it's an enormous advantage that I didn't succeed up to now to convince the people who make find the Parton distribution. That's more comfort. Now let's go to the conclusion. So the conclusion, the agreement of the function of the Fermi distribution found despite per quanto statistico and with the one found by Hera is the important confirm of the validity of the approach. The view this another. Opla. Oh, the most time is to change the transparency. Oh, Madonna. What happens?
You want to go back?
No. Then, you know, for instance, this form is not good to describe the different partons, periodicity and flavor, while instead they change the ratio just in the range between the smallest and the highest value of the potential. Let's see if I succeed to make. Also, this general property of Dodson about the higher potential is a proof of the validity, especially it confirms that also the gluon have this property. And also it predicts the spin asymmetry. Almost finished. So I insist on the fact that the agreement with the Gaussian distribution measured just with the formula with the value found 20 years before simply from the deep inelastic scattering, while now we have all the information about the gluons, is I will say smoking gun in favor. I'm finished. Let me see, Madonna. No, thank you. Ecco, la conclusione importante. Help is needed for science which think that the content of this seminar is right, because unfortunately there is a tendency to ignore the consequence of this content. Thank you.
Thank you very much for this interesting talk. We have time for a couple of questions. Yes, please.
I have to go near because I have to see them out to understand them. My English understanding requires seeing them out.
Is it working? Yeah, okay. You want to convince us to use this form of the gluon, and you've told us that this fits very well to the older HERA data and the new LHC data, right? What you haven't told us is what data you fitted, how many data points there were, how you treated the correlated systematic uncertainties of the data, and what was the chi-squared for the fit.
The chi-squared is very good. I took the data was given to me by the Atlas collaboration, which analyzed data LSHC and the era,
Yes.
analyzed and found the numbers. So
Yes.
I put the numbers. I realized that are very good agreement.
Well, it would be more convincing if you showed us what the chi-squared was. Yeah.
The chi-square?
Yeah.
No, the chi-square, you know, in the paper which I submitted, that is very amusing, the not so fair replay of the referees. I saw, and I can show you the value of this chi-square. This value of this chi-square is very good and gives a certainty about 95%.
Look,
I have in
just
my...
if you want to convince people to use your form, you just have to get more quantitative about it. That's all I'm saying. Show it all in detail.
Because we took the data. We found the chi-square. We found the chi-square.
Okay, have you a reference for the paper?
You see, I am referring about the paper which I sent some months ago to physical regulators because I thought it was a very important paper where it's written everything. And I shall show you at the end because I didn't report down. There is this paper. The reply of the editor of this is too technical because I used the Planck formula which has been found in 1900, so too technical. The second referee, physical review, said, but you compare with the same data of 2002, while the paper is written very clear that one compare with the data, with the analysis of Atlas that I received all the numbers, they are done with the data all taken after. A third review I sent even didn't reply. So I suppose, anyway, since you like to see these numbers, I shall show you these numbers. No, I see that somehow I have an
Franco,
just.
I think you should continue the discussion. We are running late. Okay,
no.
Say what you want to say. But quick, no, summarize. Quickly, what you wanted to say.
No, what I want to say that I think the people that find the right complicated polynomials formula to describe data, very complicated, just lose their employ after one finds that a formula motivated by sound physical consideration is better. So for this reason, I don't want to be persecuted, but I understand the hostility.
Okay, I think there's. Is there any other question? Urgent question on this topic? If not, let's take Franco again and let me invite Jean-Marie Claire, who's going to talk to us about eta and eta prime, from eta and eta prime to the group.
Ecco qua, uno qua.
Thank you. Sorry. Okay, this.
10 minutes, 25 minutes, plus 5.
Yeah. So I don't need to keep time for the questions. Although I would very much. No. I mean.
But you still have the.
No. When you tell me 10 minutes.
Means that you still have.
Really 10 minutes.
It's really 10 minutes for your real talk.
Yeah, perfect. And there will be questions.
And then there will be further.
Good, perfect. Okay, I was going to ask you that because I was a bit confused. Okay. So do I use this? Yeah, it seems fairly standard.
Yes, sorry. And the pointer is in the central one.
Yeah, and
then right forward and
okay.
Yeah, he hasn't downloaded it yet.
Okay. Okay, thanks. No, this is a very I don't think it cuts. Yeah, good framing. Okay, I wasn't sure whether I should take the landscape or the standard size. Okay, the subject of globals, of course, is the thing which nobody wants to hear about. Essentially, we pretend that this is solved or we ignore it, and still it's a bit nagging, and we know that somewhere in the closet there is a skeleton there. And the reason is that globals are, of course, the first predictions of QCD. Don't read the text. Actually, I will just go back. The globals are the first prediction of QCD. you have heavily charged gauge bosons, and they are going to make singlets. Okay. And lattice gauge theory has also discovered them with different scales for various reasons, because they were fairly primitive in the beginning, then started to stop quenching and so on. There were attempts to do it in a kind of non-relativistic model with constituent gluons, which would be, I don't know, that's a whole problem of classification, because you have a massless particle and suddenly you want to make it a non-relativistic massive constituent. That's a strange thing. But the problem is nothing has been observed in a conclusive manner. And one way to say that is either they don't exist and have not been produced, but we don't believe that, we don't want to believe that, or they do exist, they are produced abundantly, and we are unable to identify them. And that's not too surprising, because the mass range is something above 1 GeV, below 3 GeVs for the lightest ones. And that's an area where you have a whole forest of hadronic states. And the whole forest is a kind of a moving forest, because this goes through partial wave analysis. And depending on the production experiment and so on, the results of those partial waves analysis can be very different, because, okay, if once a big wave is there, a new peak may appear as a dip and so on. So it's complicated. And for example, you will see there is a state which is called F01710, which is sometimes seen at 1810 and sometimes at 1710, and nobody knows whether it's the same. And they only see one each time. Okay. So that's a possibility. Since it's very slowly moving, I started getting interest in that in the 80s. It's a field I'm just revisiting every few years, every 5 years, say. Okay, good. Fine. There are several ways to do this. One most traditional way is to go according to the decays alone. You have a particle and you assume you can characterize it by its decays. Okay, that's a problem. That's a problem because the prejudice when you are dealing with gluons is they are going to be flavor blind. That means you call it flavor democracy, you call it what you want, but they are going to go equally in all flavors. And you should not favor kaon decays over pion decays. Okay, then you look a bit more closely and you realize that, oh yeah, but there is the wave function of the glue ball will be small because it's linked to 1.5 GeV to GeVs, and therefore probably it will have more overlap with kaons than with pions, which are so narrower. And then you get a completely distorted way, which is they are flavor universal, but some flavors are more equal than others, like the heavier flavors are more equal than others. So that's difficult because as long as we have not clearly identified one glue ball, we don't know how to quantify those kind of hand-waving things. It may also happen, and I think it's important, it may happen that multi-meson states are favored. For example, there is this elusive state, which is the sigma, which is seen in pi and so on. And you see it in partial wave analysis. Sometimes people don't see it. It's a broad state which goes into 2 pions. It's a 0++, and it's not stupid to think that those 0++ modes could mix with glue ball modes, which are also 0++. And therefore, this is another distortion you can have. And no, the first approaches, I'm still in the decay only mode. The first approaches for many years, for 20 years and more, have been based on one notion of chiral suppression. And that was essentially in a non-relativistic quark model. But in current language, this is easy to see. If you have something with lots of gluons, you have two gluons coming out, you go to some pseudoscalar. So if you go to a pseudoscalar or a scalar, a spin zero state, you do this. You do a box diagram with the quarks. You assume that the scalar is purely quarks. And this diagram will be zero unless you have a mass flip in the center. So it's going to be proportional to the mass. And therefore, all those models and a lot of works, notably by Close and others, were concentrated on this chiral suppression, and therefore taking kk bar larger than pi pi as a criterion. Now, of course, when you draw it in this way, this language, everybody is now conditioned to remember that this is precisely the anomaly diagram, and the anomaly diagram does not need a mass. It exists, the anomaly exists for massless quarks. And therefore, you can get this diagram with massless or very light quarks, and you are going to go into states which are actually, the anomaly is in the neutral, sorry, in the singlet channel. So you are essentially going to get this divergence of the singlet channel, which gives you a GG tilt turn, which is precisely a glue ball, pseudoscalar glue ball in this case. Okay, so that means that when you do your analysis, you must take this into account. And this is the second reason why this argument about chiral suppression doesn't work. And actually, it's a reason why eta and eta prime may be very good indicators. This will be my leitmotif in the talk. And how does this come about? For example, okay, this is kind of commercial because we have essentially used this to describe all the vector to gamma pseudoscalar and pseudoscalar to vector gamma, and using that formalism, it works very well. It's very good fits. One thing which can give you the hint is actually a remark by Gerstein. I don't remember his name, is S.S. Gerstein, his first name. Sorry? Sorry. Okay, and so he noticed that some states would go, he noticed this thing. I'm just, okay. When you look at the J psi decay, it goes much more into eta prime gamma than eta gamma. Now the decay we think is through two gluons, and therefore the idea that this comes through the anomaly, that's back in the 80s, and that's Gerstein essentially who did it. There is also work by Slavnov and others, and you can essentially account for it with the above formulas that we derived from the divergence. So this is another important point, is that you get two things from this. First, eta and eta prime manifest obviously like to mix with glue. I said eta prime, but okay, what it is, it's eta zero, and then eta prime are mixtures of eta and eta zero. So they both play. And also, this is the notion of a glue-rich channel. That means that looking at radiative decays of J psi's, you get a glue-rich channel, and you get a very clean one. There is another one which has been advocated, which is looking in the central production regions in fixed target or collider experiments, mostly fixed targets. And there also you should get some enhancement of
of a glue-rich state. So the idea, okay. So the idea, and we had already suggested that for the TDR of Compass, but don't worry, we are not going to stay in the past. We have data from March this year, which are important. And the idea is to look in the same time for a glue-rich channel and analyze the decays into glue-rich sectors. And actually, we'll see in the end that we can do all of that in one scoop. The first things which were seen, I think, in this thing where where resonances in eta and eta prime, which were seen at the GAMS experiment at NA15 at CERN and so on. And one state called G1590 is now called F0 1500. You see those are wide states, and it's not because you have a number on the PDG table that's the mass. And they also saw what could be an exotic, and we'll come back to this later, because that's where we have also some new things. Okay. This is just to remind of the masses of the states which are there. So the states F1710 is sometimes now identified as 1810. Okay. Now the problem when you want to do the analysis and to extend it to a large number of modes, you need to have some idea of the branchings. And one possible analysis which was done, and we have worked on that using, well, this is a very simplified model where you allow for these kinds of processes. Those diagrams we don't know. They are not Feynman diagrams. So essentially, they are kind of combinations of momenta and quantum numbers, and then you try to combine them, but you don't know how they would interfere. So it's a very messy fit to do that. And we also contributed to this fit, and you get the references are all at the end. And at that moment, there was a suggestion that of the three states, possibly the 1710, whatever its mass, sorry, was the most likely to be the biggest global mixture of the sets. Probably there are mixtures of quarks and so on, because of this ratio. And at that moment, that's about 5 years ago, 5-6 years ago, at that moment, the conclusion was, okay, what is happening? The conclusion is, if this is this guy, then we should also expect to see it into eta prime, just like we did for the 1500. Now, what is happening? This is the partial wave analysis of BEST 3, and I think it was in March this year. The references are in the end. And you see that the decay into J psi, the decay of J psi into gamma, of course, eta prime here, gives you a very strong signal here for the F0. Well, 10 to the minus 5, don't be fooled. Most of the decays of the J psis are not radiative. So that's the 10 to the minus 5 is the alpha constant squared, right? It's in the game. And here you see that the F0 1810, the 1710 is not even mentioned, is not at all, is basically not seen. Okay, it is seen, but it's a much smaller. It is seen, but it's a much smaller rate. And this is assuming that those two things. Now, for me, this is really the critical test, because this is precisely what we had been advising, is that you look, first of all, in a glue-rich channel for the production and in the glue-rich channel for the decay. And you actually do the product and you read it just right away here. So you have twice the global enrichment on this, and that makes the 1500 a very good candidate in this language. Now, what is difficult to understand is the other decays of the 1500. I take this from particle data, and you see that, okay, those rates are, okay, it doesn't seem so spectacular because eta is 6%, eta prime eta is 2%, and I'm claiming that it's going a lot into eta prime eta. What am I dreaming? Well, if you look at the phase space, well, you shouldn't take this naive phase space, but you realize there is basically no phase space for this channel, and it's still 1/3 of the eta. Now, if you take a naive phase space, you multiply by 20. Now, these are broad states. You have to do some modeling of the resonance, which of course you cannot do, and you try to extract a number. Now, you see that kk is not seen in an important way. Pi is seen, but especially 4pi is a larger mode of this decay. So this is definitely a thing which seems to be worth going further into, and the data are just coming, so they will be probably refined. Okay, another topic is exotics. And with exotics, you might think it's going to be easy because we know the quantum numbers of quark states. It's easy to work out if you remember what P and C are. And of course, the 1- state shouldn't exist. Whether it's an isospin singlet or an isospin triplet, it should not exist as a 2-quark state. So you say, well, one way to do it, you add a gluon, and of course, what was a scalar becomes a vector, and you get around this. You can get the odd parities, the unnatural parities, and a candidate for such a state would be quark-anti-quark gluon. Well, it's not the proof of a global state of a constituent gluon, because you can always mimic a gluon with a pair of quarks, except the decays will be different, but you can mimic a gluon, psi bar, gamma, mu, lambda, a, psi, and you have it. Now, what has happened recently, at the beginning of this year, the eta1 has been observed by BEST3. And I want to quote these authors because they are in the references, but they've done a lot of papers on this, very good studies, and they've also included review papers that you will find there. They argue that the eta prime is a characteristic of the hybrid nature because there is a QCD axial anomaly, what we discussed, enhancement. And this is, of course, when I saw this earlier this year, it reminded me that we had done precisely the same a long time ago. Stuart may remember that I was in Michigan at that time, unless he had already let us drop for Ohio State, right? There was this eta prime channel seen in GAMS, but the current knowledge from QCD sum rules was that this was forbidden. This decay was forbidden. We wrote a paper with Stefan Tita, I think, on that, and basically we had calculated the opposite. Now, the fact is that this state has not been seen yet by other experiments. And for the moment, best 3 will probably go into, best 3 will probably look into this with pi 0, but we must wait for some reason they have done the eta prime analysis, but not yet the eta or eta prime pi 0 analysis. So we will have also some, the prediction is that they should see it. Now, another possibility when you see the discrepancy is when you look at this forest of states and you try to make fits with mixing and so on, and it's messy. Another possibility is that when we analyze those states, we are missing a lot of signal, because these are very fine experiments. It took 40 years to get to the accuracy in gamma-gamma, in multiple gamma decays to get this out. And they can do 2 pi, they can do 4 pi. They cannot do 6, they have not done 6 pi for the moment, and you can go on. Pions are not that expensive, so you can throw a lot of them. So another thing to do would be to look for the J-psi, to look for the inclusive radiative decay of J-psi. You just plot the energy of the photon, and you see what is in the recoil. And you see how much of the recoil you can account for with the states you are assuming. So that's a thing I would like to see done. I don't think, as far as I can say, it has not been done by BEST 3. It was done in Clio, by Clio in 2008, and they did it by tagging the J-psi from a psi 2s decay into 2 pions plus a J-psi, and by the energy of the pions, they could tag the J-psi. So that's one thing. I'm not sure whether BEST 3 can do it, but okay. This is maybe, I'm finished, but this is maybe also a question of how much means one wants to put into glue balls. People have chosen to forget them because it was too bothersome, maybe impossible to find an answer. And that means there was no budget on that. The decays, the radiative decays of J-psi was done at SLAC with an apparatus which was then moved to Beijing. And essentially they didn't have, at that moment, the resolution in the photon detectors, which came later. For example, GAMS was a lead wall, which had a very good resolution in multi-photon detectors. And just the lack of investment in that has basically blocked, well, I don't know which came first, because there was no interest or because there was no investment, the hen and the egg, I don't know which way it went. Okay, here are the references. You'll find them, I'm going to read this, but really the work of those people, Cheng and Zhu, are very impressive for the moment. And the results from BEST 3 keep coming. But you see, it's something which has a cycle of 5 years or so. So, okay. Not the perfect thing for a thesis.
Is the possibility to classify the 1370 F0 and even the F0 1500 as the larger non-net tetraquark. For instance, for the 1370, this explains why it does not decay into pions while in 4 pion, because when you diagonalize the chromomagnetic Lagrangian, the one which allowed the Rugola, Giorgio and Grascio to compute sigma lambda and delta n, you find that for F0, 2 pion is not an open channel, instead the 2 vector meson is that. So there is also the possibility that they are classified as tetraquark.
Yeah, but that's the problem with glue balls and with exotics. You can always mimic a gluon in terms of quantum number by a pair of quarks. except you will in general have some flavor content unless you make it complete singlet. And therefore, there is always the dilemma of having that explanation. And to exclude that, you really need to go at all the possible decay modes and go through it. But the diagram with the two gluons going into eta prime, I think could be a hint for me. Because, you know, a state which, when you look at the 1590, sorry, at the 1500, no, you see that it goes 2% into eta prime, 6% into eta. You look at the phase space, there is 0 phase space to do that. And still, the mode is very important. So that means there is a very strong link in that direction.
I am a lattice QCD guy, and we have been studying globals for many different directions. And as you mentioned, the quenched QCD case, even we studied very intensively. And the global is around 1710, around that area was in quenched was a scalar global. But the trouble was it has a mixing. And it has a mixing with the SS bar or LL bar. And so it's not a pure state. We observed that it has a reasonable mixing with the similar quantum number, neutral quantum number, Frebel singlet, it has a mixing. But what you're suggesting is right now, I guess, is the basis for the mixing in the quark model needs to be extended even for the space of eta bar, pi, kk, all together. Is that what you are suggesting, or only including eta prime is enough? Or I want to get some intuition from you. And also, I have a second question about the F01710, F01810. Is there a puzzle in between them, or is it fully resolved right now to which one is, or is it still remaining as a puzzle in experiments or theoretically? Or?
Well, I just jumped back into this recently, and I realized that, for example, BESS gives you in general a table listing a particle by the name in PDG, the PDG mass and their mass. And it can vary by 100 MeVs.
I see.
And you know, these are partial wave analysis in a complicated system. And the particles which were announced in PDG were observed in very different modes. For example, the 1590, which I know a bit better, which is now 1500, was seen in pion fixed target collisions. And they had, in general, higher masses in those setups. And I think it's complications of the partial wave analysis. No, I'm not an experimentalist. I cannot test that, but you know, the sigma appears and disappears when you do partial waves analysis. No, the next point, indeed, the dream is that everything is solved by lattice gauge theory. That means including computing all the amplitudes. And in that case, I think it is important to include the eta and eta prime in the possible amplitudes. But probably in the case of lattice QCD, it should be done by including a GG tilde, the GG tilde part of the eta and eta prime. Now, those are not easy things, especially that we are essentially working already with 3 flavors, not 2 flavors. It's really difficult. And we can also go into multi-particle states, which is, I suspect that you see, when you go that there are more 4 pions than 2 pions, it smells bad for 6 pions, right? It's
4 pion, 6 pion, it's not possible for the time being.
No, I know.
Yeah, but 2 pion is possible. 2 pion, 2 kaons are possible to do.
I know, but your limitations are basically the same as the J-psi case. experimental ones. No, I know. And in the beginning, also people jumped. They said, I've seen a glue ball because they had seen a particle. They didn't know anything about it, but it was just at the mass predicted by lattice QCD. And that time it was 2.2 GeVs, I think. There was a lot of identification done by mass, but it's more tricky than that. I think it's a field which is moving. And I think what is despairing for me is that people have essentially been giving up, which I understand. You know, it's been messy. We have not had data. And obviously, it took 40 years for BEST to restart and reach the level where now they churn out papers with eta and eta primes.
Other question? Well, I have a very quick one, which may be totally unrelated if there are no further questions. Do you think this analysis, I mean, there are ideas that you may have gluon condensates, right? Yes. In the QCD. Do you think this analysis could affect such ideas or?
Well, in a way, the GG tilde is a gluon condensate. That's right. So essentially, yes. Well, you know, personally, I prefer to work because I don't know. I don't know how to do it better. I prefer to work by calculating an amplitude from eta or eta prime to go to GG tilde. There is another approach which gives you the quark content of eta 0, eta 8, and then add a glue ball state GG tilde, and they do a mixing of the three. Right. And in general, they find that there is not much mixing, but in the same time, you know that you go very much into eta eta prime. So that's okay. It's funny. Okay. Now, it might also be looked at for other machines because I don't see anybody but BEST to do this for monome. It can also look at in the epsilon decays, of course.
Right. Thank you. So let's thank the speaker again. Now we have two short talks. Not your phone. That would be too expensive. Thank you for your donation. And the short talks will be of duration 30 minutes plus 2 minutes of questions. So let me invite Dr. Ahmad, who is going to talk to us about observational evidence for new structure in J psi psi 2s mass spectrum at 13 TeV.
Okay. Perfect. So we'll talk about recent results from ATLAS and CMS, which are related to observation of new structure in J psi final state and also in J psi 2s. Not spending a lot of time on theoretical things. So I mean, these existence of these new structure in J psi, some calculation goes back to like immediately after the discovery of J psi, and there was the first calculation done for 4C final state even in 1981. And now there are also very much recent theoretical calculation. The studies are based on 4C states, 4B, or even 2B, 2C. Almost all have some controversy on existing of such states at threshold, but above threshold, more or less all are consistent. So mainly in this talk, I will focus on result from ATLAS. So the first one where is about observation of dicharmonium excess in fermion final state. It's a recent conference note by ATLAS based on full run 2, and then also a similar one from CMS, which is also using same final state and same channel. Okay, before jumping into Atlas and CMS, just quickly showing what LHCb has reported about 2 years ago. So they reported an observation of narrow resonance at about 6.9 GeV, where X decays to J psi, and then to 4 muon in the mass spectrum. You can see, and then 2 model data fit was provided in LHCb case. One, when there was no interference with non-resonance SPS background. So you can see here the data, the total background, which is the combination of single parton and non-resonance, single parton and double parton scattering. There are 2 Brett-Wigners which are here to explain this enhancement in the threshold region, and then a resonance around 6.9 GeV. A very significant one. So there was 2 possible fit models given by LHCb about 2 years ago. In both cases, they didn't claim anything around threshold because of some reason that it could be a mixture of multiple state, or even it's possible to have a feed down contribution in this region from higher state. But the claim was made for the observation at 6.9 GeV, a narrow resonance, and 2 model. So the first model was without interference. So this fits the data well, except this the dip, and then the interference model, which fairly well fit also the dip. So the reported mass is around 6.9 GeV in both cases. And then now a similar analysis has also been done by Atlas and CMS. So Atlas has, both are based on full run 2 data. So Atlas has about 139 inverse femtobarn done with the standard blinded signal region strategy. The background is modeled by simulation and also data driven. So simulation is done using Pythia 8 for the 2 dominating background, which is the prompt production of J psi. The first one is the most dominating one, is the single parton scattering, and then the double parton scattering, which you can look here in purple and pinkish region. And then the non-prompt comes from BB bar. And then also there is a very slight background coming where we have fake muons. This picture shows the control region where the delta R between 2 J psi is more than 0.25, which is not the signal region. So this shows that the SPS and the data in the control region, which is the dominating background, fits well. Then here is the mass for muon, the final variable which is being fit. So you can see the expected background from different channels and the data in the black point. So there is clearly an enhancement in the data around threshold region. So if we fit this with the model here, so we have where we have 2 Brett-Wigner near threshold region, and then one which is around 6.9 GeV. So interference is allowed between the signal region, which is here shown in the green. So two solutions are shown here. So this has 3 resonance, 2 Brett-Wigner around threshold and 1 around 6.9 GeV. They only showed the result for one of the model. The second LHCb model is not shown because of the bad quality fit. So the significance for the 6.9 GeV resonance is around 10 sigma, and the feed down, which is I'll show on the next slide, coming from J psi psi 2s, is also included in the systematic. So quickly comparing with LHCb, if you look at the fitted mass and the width, it's consistent with 6.9 GeV of LHCb results. So now quickly showing so J psi psi 2s final state, where we have two fitted model, one with one resonance around threshold, and second one around 6.9 GeV, and then another one at 7.2 GeV. So with the one resonance model, the significance of 6.9 GeV excess in this final state is 4.3 sigma, and in 2 it's 4.6, and there is also an hint of excess at 7.2 GeV using this channel. Okay, now jumping to the CMS. So CMS also did a similar analysis based on full run 2 data, also used a blinded signal strategy. Here I'm listing some of the main selection, which is quite similar with Atlas, and also the simulation of background samples also using, at least the signal is based on same generator and also the background. Okay, now quickly showing the results from CMS, where we have this total fit of background shown in the green. So this threshold region is included in the background due to some of the reason I mentioned already. And then there are Breit-Wigner shown here around 6.9, 6.7, 9, and 7.2 GeV. Then now comparing side by side the CMS fitted result with LHCb model. Here we have excess around so comparing with 6.9 GeV and the same model which LHCb reported, the results are compatible between LHCb and CMS, while CMS have this an additional kind of shoulder in the threshold region which helps to separate the first resonance around 6.7 GeV from which is different from the LHCb data. And then the similar model comparing with the LHCb where they allow the interference between signal and non-resonant SPS. So comparing it with the CMS. So the parameter for X6900s are consistent, but there is a large amplitude and natural width for the Breit-Wigner one in case of CMS. So these are not the best fitted results from CMS, but I'm showing just to compare the same model between LHCb and CMS. There are also some more models which are under study, but the best fit model from CMS so far is this one, where we have a Breit-Wigner 0, which is included in the background near the threshold region, and then the 3 Breit-Wigner to describe the excess at 6.7 GeV, 6.9, and 7.2 GeV, and the significance for all of 3 are is 6.5, and this one is also reported by LHCb and Atlas. The significance, this is the most significant, the significance is 9.4 sigma, and then similar to what Atlas seen hint in JSI-2 as around 7.2 GeV, and the excess is 4.1. So the CMS results for 6.9 GeV is consistent with other 2 experiments, and also reported 2 additional excess. Okay, coming to the summary because I'm finishing time. So so the significant excess has been seen in JSI final state. The results are consistent between CMS, Atlas, and LHCb for the 6.9 GeV. It's reported by LHCb first about 2 years ago, now confirmed by CMS and Atlas at the same time. The best description from Atlas is by 3 resonance, 2 near threshold, and 1 excess around 6.9 GeV. The model, the best fit model is with interference. There is also excess seen and a hint seen at 6.9 GeV and 7.2 using Atlas data for JSI-2 as final state, but this still needs more data to explore. So the CMS also found a similar structure consistent with Atlas and LICB for 6.9 GeV, but also reported excess for two different mass point, 6.6 and 7.2 GeV. Of course, more data is needed to understand all these excess separately, like measuring their properties. But of course, we are entering into an era where the more results would be coming soon. So I thank you for that.
Thank you very much. So we have time for a couple of questions. Yes.
Yeah. What is the sensitivity of the experiment to find resonance in eta C at a slightly smaller total energy?
For eta C probably, I don't know. But for upsilon final state, it's in process, yes.
Because one should expect, if you find the two vectors, one should expect the resonance lighter, which goes into absolute term.
Yes, yes. But these are like very fresh results coming this year on only at ICHEP. I hope more would be coming in different final states soon.
Other questions? Yes.
Maybe I should know the answer to this working on an HCB, but I don't. I missed it. When you show this interference model, it seems to affect the yield of the resonance, the actual yield, a huge amount. I noticed you quoted the yields for CMS, but you see the fit actually affects the yields when you include the interference. You go back to the LHCb result. Just wondered if you, right, look at those two, left and right.
You mean the yield of 6.9?
I assume the red curve is the yield. With the interference, it really affects that. Look at the left.
Sorry, I didn't get the question. So
Right.
this model is with interference, yes.
Yeah, with interference, right? But the signal, if that red curve is a signal, it's twice as high as the one on the left.
Yes.
Right. So I don't know how you reconcile what the yield is. The CMS showed the yield without interference. I showed the CMS results. You showed the numbers of events within but it seems the interference does affect the production. Significant. Yeah, significantly. And it's just an interesting feature. I just noticed it.
Okay.
Yeah. Thanks. Okay, so let's thank the speaker again. And let me invite now Diana Diana Piatzeva, who is going to talk to us about quartic couplings and vector meson scattering. So I will give you 5 minutes, which is real 5 minutes, so you have 30 minutes plus 2 questions.
Okay, so it's great to see all of you here. And today I'd like to tell you about the recent results on the measurements of quartic couplings and vector boson scattering in Atlas on behalf of the Atlas collaboration. So vector boson scattering, which is usually studied in the electroweak processes with 2 bosons and 2 jets in the final state. is of interest for several reasons. First of all, it facilitates tests of the electroweak symmetry breaking, and moreover, it's sensitive to standard model quadric gauge couplings and possible anomalous quadric gauge couplings. So it's a sensitive probe of the BCM physics. And this talk is dedicated to the electroweak Z nu gamma JJ production. So this analysis is public from today. And it's important because the Z gamma as well as ZZ final states are sensitive to the neutral QGCs, which are absent in the standard model tree level, but can be induced by BCM. And the choice of the neutrino channel is motivated by its higher branch ratio compared to the leptonic one, and also better background control than in hadrons channels. And all results are obtained using full run 2 data from the Atlas experiment. Okay, so for this analysis, the high energy phase space region has been chosen as it's sensitive to a QGC. And first of all, the selection optimization procedure was done to increase the signal significance, which is defined by this formula and depends on the number of signal and background events. Here you can find the definition of the used Z gamma inclusive region, which is close to the fiducial region. And also there are several control regions which are used for the estimation of background yield, and also control region for the checking of the mismodeling, as well as the signal region. So for our signal that nu gamma JJ electroweak process, there are several backgrounds which are listed in descending order. The greatest contribution is from the Z nu gamma QCD process with the same final state, but with the different interaction. It's estimated using the signal region plus control regions fit to data, as well as the W gamma process and the TT gamma process. Also, there are several backgrounds with misidentifications that are estimated by the data-driven techniques. The misidentification of the electron as photon, which is estimated by taking probe method. Then there are 2 backgrounds such as missing transfer energy, misidentification as jet, and misidentification of jet as a photon, which are estimated using 2-dimensional sideband methods, depending on the 2 variables. Also, there is a pileup background when photon and Z boson are produced from the different proton-proton interactions in the same LHC bunch crossing. The effect is negligible. And also there is ZLL gamma process with a small impact, so it's estimated via Monte Carlo. Here you can find the table of the systematic uncertainties, and you can see that the largest impact are from the theoretical uncertainties of the Z nu gamma JJ QCD and electroweak processes. And to subtract the signal from background, the maximum likelihood fit was used, and the BDT classifier was created with the TMVA package for Z nu gamma JJ electroweak and QCD processes, as well as WL gamma JJ and TT gamma JJ processes, and it was trained in the Z gamma inclusive region. So maximum likelihood fit uses the BDT classifier response distribution in the signal region, and the MJJ distribution in the Z gamma QCD and W gamma control regions. So the signal strength and the normalization coefficients, as well as the event yields, are estimated in the fit of the observed data. Here you can see the event yields for the old control and signal region. So here in the table, there are results for the parameters of interest for the current analysis, and also for the previous analysis and their combination with the previous analysis. is the observation for the same process, but with the orthogonal ET gamma phase space. So it's from 15 to 110 GeV, while this analysis has ET gamma that is greater than 150 GeV. And so the results are the observed and expected significance were obtained, and they are 3.2 and 3.7 sigmas correspondingly. And also, what about the combined result is 6.3 and 6.6 sigmas. Also, the fiducial cross-section was predicted with the MET graph at LO with analog QCD corrections and scale uncertainties computed with VBF and LO. So here you can find the result is 0.98 plus minus 0.02 plus minus 0.9 plus minus 0.2. So while the observed fiducial cross-section is 0.77 plus 0.34 minus 0.30 femtobars. So there is an agreement with the standard model prediction. And what about the anomalous quadratic gauge couplings? Searches for new physics in VBS processes is based on the model independent approach, which is called effective field theory. And it parameterizes the BCM physics contributions in this Lagrangian, which consists of the standard model part and BCM part with dimensional 6 and 8 operators. And while the dimensional 6 operators contain QGCs as well as TGCs, dimensional 8 is interesting because it contains AQGCs and no TGCs, so only these operators were considered in this analysis. And also there is a list of Wilson coefficients. Here you can find it for FM couplings and FT couplings. And the last two of them are unique as they can be probed only by the neutral quartic vertices. As I've already told you that only in Z gamma and Z processes. So to preserve unitary at high energies, the clipping technique was used. So the anomalous signal contribution is get to 0 for MZ gamma that is greater than the cutoff scale value. So there are several regions with the cut of 4 TeV. So with unitary part and not unitary, and the values were obtained taking the previous point before the one where the limit dependence crosses the unitary bounds, and ET gamma thresholds were optimized to have the highest sensitivity of the analysis. They are different for these unitary and not unitary cases, as the cutoff removes the events with the high ET gamma. So here are the observed and expected limits for the non-unitarized and unitarized limits. And the results are either competitive with or more stringent than those previously published by CMS collaboration for Z gamma JJ, W gamma JJ, and the boson JJ analysis. For Z gamma JJ, it's because of the different channel. So it's for the neutrino channel, which is more sensitive, and also because of the statistics. So the conclusion, the measurement on the new gamma JJ electroweak production is presented. It's with ET gamma threshold that is greater than 150 GeV and full run 2 dataset collected by the Atlas experiment. So the dominant backgrounds were estimated using a simultaneous signal region plus control region, speed to data, and data-driven techniques. Also, the maximum likelihood fit over the BDT classifier distribution was used, and the signal significance is 3.2 sigma for the observed and 3.7 sigma for the expected values. So it corresponds to the evidence for this process in boosted photon regime. The measured fiducial cross-section is 0.77 plus 0.34 and minus 0.30 femtobars. It's in agreement with the standard model predictions and at analog and perturbative QCD. And the signal significance of the combination with previously published Atlas result is 6.3 and 6.6 sigmas. The limits on accuracy set on if the dimension 8 operators are either competitive with or more stringent than those previously published by CMS, and the constraints on the T5, FT8, and FT9 operators are significantly stronger than the results previously published by Atlas and CMS. So thank you for your attention.
Thanks very much for this very nice talk. Questions? Yes.
For this dimension 8 operators, you showed the results for these mixed and transverse operators, but there is also a scalar one, S0 and S1. Did you take them into account, or do you have any sensitivity to those?
Sorry, to take into account what?
This S0 and S1 operators, the scalar ones.
No, because they are can't take into account the QCD, the gamma QCD process. So they were excluded.
Okay.
Further questions for Dr. Katy-Biancheva? Yes.
Thanks for your talk. My question is, your limit in data, for example, on slide 10, when you have this plot, can it be interpreted, well, in the phenomenological studies? I mean, or in other words, if we apply this set of cuts, for example, right? Can we use this limit? What set of cuts did you use? Or did you use the, say, neural net analysis, or just a fixed set of cuts in your analysis?
We use the fit, and yeah, just to take this last bin, where the here you can see maybe these limits where the contribution is greater.
Okay, but what kinematical cuts did you use? Do you have a list of cuts did you use in your analysis? Or
for fiducial cross-section, for example.
Okay, so.
Sorry. Yes.
Okay, I see. Did you use any rapidity gap cut for?
Rapidity, no.
Which is characteristic to vector boson fusion. I didn't see it, but okay.
No.
Okay, you didn't use rapidity gap. Okay. Okay. Thank you.
Okay, so let's thank Dr. Katy-Biancheva again. And let me now invite Zbigniew Vas, the last talk of this session, who is going to talk to us about new physics signatures of interfering background.
Okay.
I'll give you 10 minutes, real 10 minutes warning before the.
Okay. So I would like to say a few words about. Just a moment. About theory being used as a tool for experimental things. And I mean, if you want to compare data with theory and you do not have some fabulous new signatures, which are the huge peaks in the middle of nowhere, you have to worry about how to disentangle signal from background. And if you want to do so, there is a question how many things you need to take into account of those things which you are not interested in, to see the sticking out the signature of something new. This is particularly novel now when we have the new techniques where we look at multidimensional distributions, because which is becoming available due to machine learning techniques, where of course questions of systematics and backgrounds are even more painful than in the past. There is a question what needs to be taken into account. Obviously, on experimental side, one has to take into account detector acceptance, what is the phase space which will pass into the observables. On the theoretical side, what kind of the higher order or modeling of structure functions needs to be taken into account. Then because of complexity and interrelation in such cases between effects which comes from theory and experiment, the usual way of making comparison is using Monte Carlo and only simulations and only sometimes semi-analytical integration. So how to divide the task, how to combine the results at the end. It's not easy. People are looking at their own corners of work and would like to push difficulties to the other people working desk. So in this context, I would like to use two examples of small phenomenological and software projects which I was asked to prepare for Bell 2 data analysis in context of new measurements of new physics interactions. So if you want to make such comparisons, it's good that your Monte Carlo program is constructed on the basis of phase space times matrix element structure. Then phase space is better to be exact, and matrix elements, of course, can have approximations. So you localize all your approximations in matrix elements. Then a lot of techniques can be used. And also it's important that even if you use matrix elements which are simplified, you know exactly what this simplification are. So you know exactly your imperfect matrix element. If you do such things and you have the small contributions from new physics, you must first avoid degrading of what was done for basic standard model calculations and simulations. Because if you mess up something, you may easily think that you are doing something new physics, but in fact, you are doing some managing of errors. So you want to have new physics things on top of well-established tools for standard model interaction. I will use as an example the KKMC Monte Carlo for E plus E minus to tau plus tau minus with tau decays and with multiphoton Bremsstrahlung. That was the tool which was used a lot for lab times. It will be used hopefully for future FCC experiments as well. But at the moment it's being used by Bell 2 collaboration, and there is a precision tag for this program established by conditions of work there at the level of 1 or 2 per mils. And I want to present results from the two papers on first of imprinting into the Monte Carlo simulation new physics process resulted with exotic scalar or vector states into previously simulated sample. It's important that you make this correction because you need to worry about effects of higher order QED corrections, and also you don't want to lose the tau decays, which are important. And another thing which I want to talk is about implementing with the weights into such events anomalous magnetic or electric dipole moments, because there is some interest that this might be the signature. So experiments want to have a tools to evaluate size of it. So start of such work for dipole moment is to have matrix element. You have to have, it will never be the same convention as for your basic Monte Carlo, but you want to have it somehow in the same convention, is to have the matrix element for standard model and for standard model plus new physics. When you want to implement something, you want to have something. And that's what I've used for as a first step for dipole moments implementation into the KKMC event sample with the help of event weight. It seems trivial, but one has to keep in mind technicalities. It's very easy to damage if you do something too quickly. So there is a question about the reliability proofs of such techniques if you implement new matrix elements which don't fit into the scheme of QED exponentiation of factorization in QCD. You may make mistakes. So one has first to verify if the new added matrix elements are at least roughly matching this, what is used as the foundation of the structure of the program. So otherwise you may easily break the structure and design principle of your standard model process. That is particularly important if the new physics effects are interfering with the standard model amplitudes. So what were the conditions of work for KKMC Monte Carlo? I was lucky, and that's why I could do it, because KKMC Monte Carlo is done on the phase space parametrization. It helped me a lot that I've spent some years of working on that. And then matrix elements for QED was done as kind of the model, which consisted of results of calculation from QED from first, second, and sometimes third order matrix elements. And it was, phase space was always the same, but the matrix elements were different. So adding new matrix elements to this was quite naturally. I didn't need to do the huge effort into phase space parametrization in things related to exponentiation, relating cancellation of virtual and real corrections. This was done before, and I was using this solution for new physics as well. In this case, it was dipole moments. To make correlated samples, I've used event weights. So I would not modify the series of generated events, only every event would get extra contribution. So that's the principle of Monte Carlo. You have to divide things into part related with tau per production. I wonder if it's a pointer as well, probably not. So I have to press the middle. The middle. So if you do the matrix element for tau per production, because taus are extremely narrow, so you can divide phase space into part relations to tau per production, decay of first and second tau. The same you can do between Pauli mat orthogonality for matrix element if you have four kind of the things. One is cross-section for matrix element average over the spin for the production, for the decay of the first and second tau, and then you have the spin weight which correlates the two things together, and that's what will manifest also the new physics. The new physics effect have to be calculated as correction of this and of that. These two things stay. So this is matrix element. This is for cross-section, for production cross-section. That's relatively easy. From technical point of view, this is more complicated because this weight, which relates what this kinematical configuration would have if it was having new physics added or no, not depends on the production and on the decay as well. So this kind of the things, these are the vectors which comes out from the matrix element of tau decays. They are the same whether it's standard model or not. Nevertheless, you have to take it from inside of the Monte Carlo program. So you have to know how these two things are defined. And because of that, we take out of KKMC these values of these polarimetric vectors. And we also have to use the routine which boosts this any vector from tau rest frame to the laboratory frame. We will need it later in the rest frame of taus as in the calculation of this anomalous dipole moment implementation code. But it's best to go through the rest frame. So in anomalous mode calculation, it can be done, frames can be done with approximation, but boost of KKMC takes care into account presence of all photons and things like that. So that's, it's little technical things, but it can it can mean loss of precision if you don't do it. So also important is that we take only these polarimetric vectors. So the solution works for all tau decays, and there is about 30 of them. So one is lucky that one don't need to distinguish which one is being used. So I could profit from collaboration with Alexander Korchin from Kharkov, and he calculated for me this spin correlation matrix for 2 taus. This is at the Born level, but we could use kind of the simplified kinematics. So the photons which are present in the event could be properly matched into effective beams and outgoing taus for kinematic construction for calculation of it. And we used, there was a question how to cope with these dipole moment measurements. So typically people started as usual with tau decays to pi neutrino because this is the easiest to interpret. But in fact, any channel is having the same maximal tau spin dependence, but in case of pi neutrino, all is contained in pion momentum. In other cases, so you need to pion momentum and neutrino momentum as well, which you have somehow to reconstruct. But I've used other channel and only part of spin dependence. I mean the channel where both taus decay to pi, charged pi 0 and neutrino. So I've used it as a test example and to play and to extend possible solutions and to demonstrate that one can use other tau decays. Of course, because tau decay vertex is not used, in this case, it has different systematics. And what I could see the same kind of the distribution in the coplanarity angle. You build 2 planes in the rest frame of the visible tau decay products. And this coplanarity depends on whether it's electric, magnetic, or combined dipole moment. So it's good to have, thank you. So it's good to know that the phenomenology picture is very much the same as for CP Higgs measurement which was shown for Atlas, but similar techniques can be used for different purposes and in different experiments. This is very much idealized observable. I would not call it optimal. It's just to demonstrate how the things work, because the most important is detector uncertainties. Of course, the real phenomenology will be done by the experiments. So that was one type of application where we want to add into the Monte Carlo new physics contribution on top of something which is of high precision. And the critically important was not to try to destroy precision of standard model prediction and add with the weights extra physics process, which could be added better or worse, but their precision was not so critical. So another thing which people wanted to have, it was kind of the emission of dark photons or extra scalars associated with tau pairs. And for this, I've hacked our Monte Carlo program photos for generating Bremsstrahlung in decay of resonances. So maybe my time is going to the end, so I will go very quickly. We took the matrix element Monte Carlo program of MatGraph. We've made the simulation of the for fermion final state, tau tau E plus E minus, where E plus E minus was coming out from dark scalar. And then I was generating events from KKMC without, first without tau decays. And I was checking how it will compare with this if Photos was generating extra E plus E minus pair, but not from QED, but from narrow resonance, which could be vector or scalar. And that's what I was doing last year here during evenings in Corfu, because that was when I got a question of it on it. So what is important is how Photos Monte Carlo works. It works as phase space modifier. So you want to use n body phase space point to get n plus 1 point phase space. So what you do, you take n body phase space and some parametrization of it to get variables which later on you put into phase space parametrization of n plus 1 body phase space. So you reduce back n body phase space point into configuration of some cos thetas and phi angles. You add extra for the photons, and in this way you get tangent space for n plus 1 body phase space. And you do, so this is formal mathematics. You just parameterize new phase space with the help of variables in some parameterization of previous one. And so you have to remove in this weight of all phase space Jacobians of n body phase space and put instead the new one. And later on you do the same for the matrix element. Of course, a lot depends on T. T has to be optimized and it has to match the structure of singularities of enhancement due to infrared or collinear configuration. So it's not as trivial as I said. It took me, well, many years and mistakes to achieve. And explanation like now I did many years after making the program. So this is the weight. You can see that weight consists of this lambda 1/2 factors related to removing of part of Jacobians from n body phase space to n plus 1 body phase space. So when we played with the matrix elements, we got some benchmarks, and in this we could go for 4th fermion final state, tau minus type tau plus E minus E plus. We got distributions which were matching. So Photos applied on 2 tau plus tau minus configuration was making tau plus tau minus E plus E minus configuration with good precision. But on top of it, we had tau decays. If it was dark photon, that was the end of the story, because that was spin 1 particle. I treated it roughly as kind of the Bremsstrahlung, so the spin correlation didn't have to be changed. In case if it was dark scalar or pseudoscalar, one had to make rotation of the decay products of one of the taus to match kind of the idealized simplified matrix element for the spin of it. So that's about the project. So the numerical results are just illustration. The real work will be done by experiments. But this is good to go like that for new physics. One can do like that for other processes, for other new physics signatures. So if somebody would be interested, I could offer help and get also in touch with Bell 2 people. So the point was also very technical. If you provide the tool to the experiments and they need to do dirty technical work for half a year, they will not be particularly happy. But in this case, because I knew that they have other things to do than to worry about structure of programs. So in case of this case, there was no need of even libraries recompilation. So even sample was not modified. The only thing what I had to do is to get an access to internal routines of KK Monte Carlo and to internal data, this H polarimetric vector. I could do it easily because I am co-author of KKMC, and also KKMC was written in Fortran, so all variables and routines could be accessed. If it was in C++, then it would be probably private variables of some class. And one has to keep in mind that this kind of the objects should be in the category of so-called friends of the class. So some accessors to these routines should be given. The problem is that if you design the programs, you don't know what you may need in the future. I would never think of this kind of the application for the first 20 years of my work on Monte Carlo programs for this process. For in other case, we applied the Monte Carlo program for written in C++ to generate pairs. So it was not in software of Bell 2. It could belong to the user program. So there was no need to test the new version of the software. And this was easy to do. Also, there was no need to interface. The program could be run on top of events. So you just take events from the data file and you calculate for those events modification. So you change some for vectors, but you don't need, and also as this is tiny change, only few events are changed. So you save a lot of CPU, especially if you have many models. So that's about this. What I was not talking about is how to deal with amplitudes. So you have to do a lot of about gauge invariance and then comparisons to separate amplitudes into parts. And some of these parts could mimic the structure which is in new physics. And that's why this kind of application were possible in my cases. So that's the strategy of the work. I think I've run away of time, so I will not go into it. And so the point is how it's very important how spin amplitude is calculated and how they are implemented into the program, so one can understand the structures. So, for example, if it's Kleist-Stirling technique, it's very important to assure numerical stability, but also to be able to play with parts. So in case of KKM, so that's for the construction of the program. For the next new physics processes, instead of playing with formal spin amplitudes, analysis, division it into parts, I was just simply using comparisons with MATGRAPH and checking which kind of the educated, hopefully educated guesses were the best. Of course, it does not need to be done for Bell 2 only. It's possible to extend to other experiments, and I was thinking of such and trying to apply such application for LHC, FCC, and also it's very friendly, this kind of the weight approach for machine learning techniques, which we will not be able to avoid in the future, because then you can play better with signatures of multidimensional nature. And also in case of taus, when you have to pick up effectively 300 times 300, 30 times 30 configurations, it's good to have some computer to do work for you. But systematic errors and misunderstanding of mathematics underneath the tool, it's the foundation. And I would like to stress once that one of the most important in my talk was this, what means this minor modification of the code. It has to be minor for, not for you, for the author of the projects, but for experiments which are using, which have a lot of politics, tests, validations on top of the programs. So if you can plug in your modification into main user program, it's fine. If you have to make little change here and there, then it's far more difficult for them to accept. So that's all. And
thank you very much for this very nice work, and congratulations for your many years of essential contributions to phenomenology. We have time for one quick question or comment. I have a very, I mean, not quick, probably, I don't. If you want, for supersymmetric field theories, this can be extended easily, or?
If the spin structure of the new amplitude is similar and at least follow this, what is in the main process, that's straightforward. So yes, actually Photos Monte Carlo program was built in case of kernels, in case of the tau decay to pi neutrino on the basis of amplitudes which were calculated for supersymmetry. So I've used input from supersymmetry, and but this comes to some subjects maybe we can discuss in the evening.
Thank you. Thank you very much. If there are no further questions, let's thank the speaker and all the speakers of this session. And we will resume now. You are breaking for lunch. We'll resume at 4 o'clock.
to this really afternoon meeting. So we will start. The first talk is going to be by Stanislav Kacik, who is going to give us a nice summary of the recent CMS result.
All right, so thank you everybody for coming timely to this session. The others are probably still flying in. And I wanted to start like all my predecessors here in the morning session with thanking organizers for the invitation and giving the opportunity to come and join such a renowned workshop, which is well known and provides a very good and useful hub for the community to nurture interactions between theorists and experimentalists. So I will give you a personal selection of the results from CMS. There are just hundreds, if not to say accumulated number of presentations is exceeding already 1,000. And I'll be talking about CMS, which is located along the diameter from the main campus, and our Atlas colleagues, although we are 15 kilometers apart, we have a common platform, more than one, to talk to each other. And such platform is created by the LHC working groups, which unite not only the two big experiments, but also LHCb and ALICE to communicate different techniques, gain experience in each other data analysis, but also to better understand what is being done under the hood, and provides quite spectacular, very well statistically analyzed combination measurements. So I selected the results which are recent from the complete data set from run 2. And you will see throughout when I'm guiding you what are the interesting features which I personally selected for this presentation. So the apparatus have been seen in expanded view for a while, but just very briefly for those who have not visited the cavern or saw it in a close position, that calorimetry and tracking is inside solenoid 3.5 Tesla, the largest solenoid in terms of volume, not the value of magnetic field, which does exist. Outside, we have muon chambers where we identify the muons, and then there's a central part which has 5 concentric rings, and the forward and backward regions are complemented with end caps for catching up the muons, and also in the end caps we have end cap calorimeters. So that's probably enough as an introduction. And I also wanted to say that we really praise the people who are behind the LHC. We just say, you know, luminosity delivered at this level and that level. But since there was today this historical perspective, I can't resist to point to this LHC specification bar here, which is set at the value of 10 to the 34. This is what was in those documents which Louis was presenting. And as you see, what has been accomplished towards the end of run 2, by the end for the 2018 run, was twice the specification. So spectacular performance, and we would like in every forum, every conference, every talk, extend our gratitude on behalf of us and every experiment to thank people behind the control of the machine for such spectacular performance of the machine. On left bottom, one of the technical challenges here with so many interactions per crossing is the simultaneous interactions, which we call pileup. Here you see the evolution from 7 TV operation when we had the pileup of 10 overlapping interactions up to 38, 40. This is the average, so it's Poisson distribution. You can easily guess what's going on in details. These are the profiles over the years. And we developed techniques which were quite comfortable now to reconstruct on the average 40, our interesting high PT physics among 40 events of pileup low PT. Here you see how this data set from run 2 was accumulated over the years. This is 2015, this is 2018. The machine delivered at 0.5. Those numbers of deliver are different between Atlas and CMS. 164, we were able to record 151. Gives us the operational efficiency of 90%, which is quite high performance of the detector. So what you see, and you already saw them coming in, are the results with the full data set and partially, which many new results, new channels are opening up as the integrated cross-section is rising, and we're gaining the precision. So now the LHC experiments become precision machines. We used to say that only E+ E- collisions are clean and we can reach precision, but you will see throughout that we're reaching quite spectacular precision on some of the measurements also coming from the LHC. So I will expand a little bit on the Higgs, although in the morning you remember that Lydia gave us an overview of the Higgs portrait coming from Atlas and CMS. I found some things which were still complementing what was shown earlier. So there will be no repetition. I'll try to keep to minimum. We have a measurement which just hit the print, before ICHEP on the new limit on branching fraction of B sub S to mu mu. And interesting electroweak measurements with the top, its mass, cross sections, and we're exploring fully without any limits the searches for physics beyond the standard model. So this is not a schematic, but a picture of the CMS experiment in expanded view, open before closing in for the data taking. So it does exist. It's filling the cavern, and what this fish eye ball will bring, time will show. And as you know, we will have several decades of running under different operating conditions and surprise ourselves and everybody in the field with hopefully spectacular measurements. So my talk comprises 4 parts. I will talk about the Higgs. I will show you the interesting measurements within the realm of standard model and see what does not agree with the standard model in searches for those new hints of physics beyond the standard model. And then I'll tell you a little bit about what to expect afterwards. So everybody is looking at the historical perspective, trying to grasp the passage of time. So my metric here is 2 pictures from the PDG from 2012 around end of June, where this is the entry corresponding to the description of the Higgs. Only 2 weeks later, 2 weeks later, to add an addendum to the online edition of the PDG, saying that there was a seminar and both collaboration declare a discovery. 10 years later, you see we don't only have 1 page. This is the portrait or passport with the fundamental measurements after 10 years of running. This is edition from this year. And we have a few more pages of information about the Higgs and the limits, etc., etc. So there is a great work on behalf of both collaborations, Atlas and CMS, and a few thousand of people who are working very hard to analyze the data and get the best out of physics. The 10th anniversary was celebrated with 2 articles that were mentioned before by Atlas and CMS. There is 1 volume of Nature dedicated to celebrations. And also there were special seminars organized, 1 at CERN, 1 at Fermilab, and many other universities were inviting other scientists to share the excitement of that anniversary and remind that we exist and our program is rich and provided a lot of new and interesting measurements in our field. There are new rare measurements which require additional statistics, which I listed here. I'm not going to read it off. I only wanted to mention that you see this is quite sharp. We know what the minimum of the Higgs potential is. And now are investigating the things which are still blurred, which are driven by the new parameters like Higgs self-coupling or quartic coupling, of the Higgs, which will probably bring that edge to the focus next time in 10 years when we're going to give another celebratory presentation about the Higgs measurements. The Higgs does exist. Here you have a summary of the mass peaks, as we just call them in the jargon, in the bosonic decays. Here is the fermionic decays. That's what we reconstructed. It was shown already before, and it's nothing special, except that you see that in every decay channel with the full statistics, we see nicer or emerging bumps, which we're interpreting as the existence of the Higgs in those channels. So the flash view of the Higgs biometric measurements or information is the combination, which doesn't have to be very recent. I found it that it's enough to point to the combination of the mass measurement between ATLAS and CMS, which is listed here. We know its width. There was a very nice suggestion from theorists after the discovery how we can access the width. I mean, direct measurement has some experimental limitations. However, if we compare the Higgs to ZZ on-shell and off-shell decays, then this ratio is proportional to the width of the Higgs, and that's the method which was used to determine its width. It's now probably a little bit better, but this is an earlier measurement. We know its couplings, and I will expand on that. And we know its spin structure also, that the fits are preferring the 0+ compared to every other combination which is possible. So that slide you already saw in the morning talk, but if you look at the column which marks 1 corresponds to the standard model. This is a normalized strength of the signal at the production. Everything it's in a column line up around the standard model. And now the game in town is just to shrink as much as possible the uncertainties to really figure out if this is a snake shape or a straight line. And in either case, we will give us some information which we can use later to interpret. On the right-hand side, you see the decay end of the interaction. So all the decay modes to fermions and bosons have also been measured, and the same thing. I will talk about it more now. The 10%, 10-15% uncertainties on those couplings, we hope that we can, in 20 years, reduce to 3%. But so far, everything agrees with the standard model within the uncertainties. Here, there's a spectacular linear dependence as expected in the electroweak symmetric breaking model. And we see that even we have now calculation of the Yukawa coupling and the bosons, the fermions, even the mu made up here. So electron is somewhere down. It's a long way to go. You see here the ratio. What is amazing, if you just try to read from tea leaves, that if you look at the pattern of ups and downs around 1 between ATLAS and CMS, which we're not allowed to do, this pattern is the same, right? They all fluctuate in the same direction. Here you see the accuracy of for the bosons, and there's a different scale since we have quite a nice sample of W's and Z's, and accuracy on this measurement is much better than the precision on the other states. The work continues, and we would like to have everybody by the end of run 3 within the 5%, 7% measurement, and then before heading into HL, LHC running with updated detectors. On the right-hand side, you saw it before. We were wondering, does it pay off to combine with ATLAS and CMS? Definitely yes. You also see some time evolution from the discovery time, what we have at the end of run 1 and what is now 10 years after. These are the numbers, but also on this slide, you will see the evolution in time. And there's one more point. So we have a series of studies with the existing configuration of the detector, scaling only the uncertainties by the statistical, by the luminosity and statistics. And you see that towards the end of the LHC program, we expect to see 2-3% accuracy on the measurements of the couplings. So I mentioned Yukawa coupling. It's coming from the production vertex. There's another decay type, decay and one looks at not decay, sorry, the interaction. And when you look at the TT bar H production, which gives us another way of complementing way of measuring the Yukawa coupling. However, there is a sign ambiguity, and that's why there's so much interest in TH, because TH, through the interference of the amplitudes between the boson fusion and the radiation of the Higgs of the top line, will be able to establish the sign of the Yukawa coupling. An important measurement. So far, we have a combined results on the combined analysis of TTH production and TH, and we see a very small hint of a bump with the with those significances 1.5, 1.4 sigma observed when we expect 0.3. So I'm not there yet. We need to wait for the data set coming from run 3. This normalized strength for the TH, we still can perform maximum likelihood fits, gives us the number, which is 5.7 plus or minus 4, still some time and some work to do to have it closer to 1. When we talk about the decays, we have certain decay channels. I didn't name them. I think by now we all know. And interesting thing is to see, is this all? Are we missing something? So that's what we call Higgs to invisible decays. There are two categories. There are particles for which we're looking for, like neutrinos or charginos, which might be coming around the Higgs. And then there are also particles which we don't look at, which can be created, and we're not looking for them. So when we then consider the topologies where we have a heavy object against the Higgs, or recoiling against the Higgs, then we can make a generic analysis and find how much room we have for things which would explain the observed rates. And here we're at the level of 10-13% expected, 14% or 16% observed, where we claim that at that level we're not missing anything, but you see that the uncertainty is quite high. We also look at exotic decays of the Higgs, like leptoflavor violating decays. I'm not going to discuss all the channels. There's a nice analysis here, and the total for the combination number for the Higgs decaying to mu tau, we're not leaving a lot of room. Here you have the observed limit and the best fit for the branching fractions. That's an alternative violating decay with the electron and the tau, and no excess is observed in the data. We can also look at those non-standard lepton violating Yukawa couplings, which intermediate possible decay of this type, not conserving the lepton flavor. And here you have the limits that are consistent with less than per mil levels. So one Higgs in the final state, we're happy 10 years ago. Now we're looking for 2 Higgses in the final state. And here's a collection of summary of decay channels, where we look at the topology with a pair of BB bars coming from 1 Higgs. This is very well understood decay channel. And then associated with a pair of Zs, gammas, taus, and BB bars. Of course, we know very well that the decay to 3rd generation has the highest rates that maximizes our statistics. And you can see that if we look at the limit on the cross-section strength of production rate for a pair of Higgs normalized to what we expect from theory, we're at the level of somewhere around 3. Here it's a time evolution, which we included in the Nature publication. So I'm not going to talk about what we knew at the end of run 1. This is 10 years after end of run 2. But again, we have a nice set of documented analysis and results, which indicated if we wanted to see 2 Higgses produced in the final state, we will have to wait well into the end of the run of HLLHC. So far, everything is consistent with some hints. We develop the techniques. Also, we believe, which was not yet assumed, that as I mentioned before, those projections into HLLHC assume the performance of the current CMS detector, and many things will be improved with increased performance, and hopefully we will see something before we accumulate 3,000 femtobarns. Another look at the in physics information which we can derive from observation of 2 Higgses in the final state is a 2-dimensional correlation plot between normalized Higgs self-coupling and the we're looking at the dependence of the cross-section as a function of the Higgs self-coupling, and it has this is what is being expected when we look at the dependence on the cross-section as a function of the coupling compared with the theoretical expectation. You see that there are many amplitudes in entering this calculation. There are different interferences which then produce this shape. If we look now at the standard crossing of what is being predicted by theory into what background fluctuations are allowing us or not, then we exclude quite nice region within this limit of -2 to 7 of the ratio of this coupling to the standard model. On the right-hand side, this is the quartic coupling, but not of the Higgs, but this is a vector boson scattering with the quartic coupling to the Higgs, a pair of 2 Higgses, similar type of analysis. Here, the interferences are just in the opposite direction. And we see that we're eliminating the 0 value. We're already excluding the 0 value for this coupling of 2 V's into the H. Nice result. So both collaborations, Atlas and CMS, are very proud to discover the Higgs and perform many challenging and declare early on analysis which are impossible, but with experience and new machine learning tools, we're able to handle them and show you the results which I selected for this presentation. We also know that one area of measurements is relying on the precision, which we are getting with the increased data sets, but also alternative set of interpretation when the Higgs might help us not only to elucidate the electroweak symmetry breaking, but also to look into the physics beyond the standard model. It can be a portal to new physics theories, and this will be the bread and butter program for research with run 3, in addition to direct searches for physics beyond the standard model. So a few words about the top. We're monitoring and making quite challenging and precise measurements of the top cross-section. This is the total cross-section and its evolution as a function of energy. There is also an entry point for PP bar. From the Tevatron, there are 2 lines corresponding to separate calculation for PP and PP bar. The entry points starting from the beginning, the early point when the collision just happened, there were very clean events, no overlap. There was a nice measurement of the total cross-section at 5, followed by 7, 8, and now 13. And that's our latest addition to this set of measurements from lepton jets, which quite advanced machine learning techniques, which gives us this mil. It's 1%, less than 1% measurement. Here's the summary. This is the latest edition. We wish that let's wait for the update of the previous measurements and new ones with new channels based on 137 femtobarns. Like this is the first one on this plot, and we hope that we might see quite interesting pattern here soon. The other parameter which is quite important for the standard model and electric parameters is the top mass. The limitation in the top mass measurement was modeling and jet energy corrections. So here we have 3 updates, 3 different analyses, 3 different channels. When we handle the uncertainty on the jet reconstruction by constraining the jets, looking at the hadronic decays of the W and introducing in the overall maximum likelihood fit a constraint of the mass, constraining the 2 jets into the mass of the W. This really helped, and we came up with a total uncertainty on this measurement of 400 MeV. The second measurement is what we call pole mass of the top. We know that top decays before it hadronizes, and there's always some modeling what we are really measuring. Is it Monte Carlo mass? Is it pole mass? But pole mass is defined as the one in the propagator when we look at the total cross-section or differential cross-sections, and then can be unfolded. And that's what was done here. There are still some large uncertainties. This is a combination of statistical uncertainties and theoretical one. But we hope that that number can be shrunk. As you see, there's a third one with boosted jets. The error is slightly larger. The systematics is different. When you look at these 3 new additions, and I mean, overall, there is an agreement between the mass measurements, not only among measurements coming from one experiment. We have Tevatron combinations, and then there's a world combination as well, including Atlas. And you see that it's all regular, and somehow we settle on its value. The game in town is now to convince everybody that those uncertainties are defendable. Our partners across the ring have agreeing with this, and other way, and vice versa. And then we can come to those who are using the information about the value of the mass of the top to their further studies and predictions or development of other models which will try to explain to us what's happening outside the standard model. Sorry. Now, we're looking also at the associated production of pairs of T's with vector boson, with bosons, not only vector bosons, but bosons. So here's a summary from 2021. There is a new addition. So this set of measurements, when you see TT gamma, TTZ, TTW measurements, and now we did update the measurements of TTW with this high precision full data set measurement, including the partial, the W's split into the charge. And the numbers are listed here. The precision is quite impressive. Everything is consistent with the standard model. We also had, shortly before ICHEP, finish an analysis of B sub S, B sub D analysis decays to two muons. Here you have a nice display of a nice event with 2 muon candidates, quite clean. Sorry, the information of about the rest of the event is quite clean. So 2 muons, it looks like a simple analysis, and it should not be very challenging, although remember that this is a typical event which was selected only for demonstration. The other have a lot of pileup on them. So here's the results. So let me remind you, I was talking before the talk with Neville from LHCb. That's our previous update, which is combination of Atlas CMS and LHCb, and that's the branching fraction which we published 2 years ago. with the accuracy of about 0.4. And here is an updated analysis with the new MVA, which is multivariant analysis methods, and additional handling of the backgrounds, the decay in flights, which contributed for the time at the time of this conference of this measurement, irreducible backgrounds. It was all handled and improved, and then we have our final measurement from this data set, which is listed here with the accuracy of less than, of 0.4. I mean, there's some systematic measurement. This we handle by looking at and comparing the J-psi-K and J-psi-phi decays for normalization. If there's anything non-perturbative, it's being wind up in that ratio of the decay coefficients. And that's B sub D, which it's still a larger uncertainty. Everything is compatible with the standard model. So the hope was that, if we found something which is, if we measured that branching fraction and found a number which was much higher than the level of 10⁻⁹, it will be an indication that there is new physics, which can only alter it. But you see here that fortunately or unfortunately, we went down with the precision and were reaching the expectation from the standard model, which was listed here. So let me move to part 3, which is searching for direct production of new states. So what else have we seen in the data? I should reverse the question, what are we still missing? So we all look at it with the help of theorists saying, bringing different suggestions. A meeting like this are quite fruitful in bringing new ideas. But so far, we're making as many measurements as possible, driven by different motivations, different interests. An important thing is that we're trying to catch up with the precision which we can reach with a given data set. So what I picked up for today is 4 examples of some results with Suzy. Although there is another dedicated talk here, so I'm not going to spend time on it, and only just show you the summary, and then the specific information in more detail will be provided by the other speaker. I have a list at the end of my talk. I will try to look for searches for more exotic decays of the production appearance of additional Higgses here. What can we see in the resonances of vector bosons, or searching for the per-produced HH, and then some other exotica, which is here. So as I am emphasizing here, there is big difference and advancement in the techniques which we're using. It's not only a better understanding of the detector, but also the statistical methods which we're using are more and more sophisticated. We're entering now massively into machine learning techniques, including even the deep machine learning, which includes image recognition and all sorts of new enhancements, which industry already took away from us, all those neural nets algorithms which we're using for last 30 or 40 years, and advance it even more. So now we're learning from them how we can use the most advanced deep machine learning technologies, and we're quite successful in applying them. So that's the result. So the results which you see, is a result of our close interactions with those who advance those techniques for us. So as I mentioned, I'm not going to spend too much time except flushing. Nobody likes it, but you see here electroweak production of charginos neutralinos, and this is the strong collared Suzy with the gluinos and squawks. And trust me, I didn't prepare an animation here to show you an evolution of how this area which is excluded evolves from 7TV, but maybe even before discovery, it will be nice to see what is the status of elimination of the regions or areas in the phase space of Suzy parameters before we find something. But I don't think that's easy to make, but maybe we will, one day we will do it. And there is a summary plot. This one is from iChirp, well, you can't see anything here, neither do we. So it means that we don't have any discovery for SUSY particles, but everything is now still consistent with standard model. The analysis which we are conducting are now continuing with so-called simplified models with very simple final states, relatively simple interpretations, and this continues until we start seeing some bumps and hints, and maybe this will trigger more detailed tuning of the parameters used for specific verification of one or another scenarios. But the phase space, you know very well, especially those who are working and developing SUSY, that it's quite broad. So are there other Higgses which we might see in the data? So what about another neutral Higgs? So we just conducted a search, like searching for the standard model Higgs, this time for a generic neutral Higgs, which might be produced in either gluon-gluon fusion or with the association of single or pairs of DBs. And the final state has divided the case into the taus. The taus are decaying leptonically or hadronically, and then we have B taggers with deep B tagging algorithm. That's a new addition to the tools which we are using. And we look what is happening in the range of 60 GV to 2000 or 2,500, no, 3000. It's a log scale. So here's the summary. So on the left-hand side, you see gluon-gluon fusion. On the right-hand side, you see the associated production of this hypothetical model to the B. This is how the branching fractions were entering here. So it's the limit. Oops, sorry, I'm just pressing the wrong button. So the yellow and green plots are telling us this is the background-only hypothesis. The dots are the measurements, and what you see here, we just have a pretty nice limit set in this quite broad mass range. And there are two bumps. Now we're just looking at the bumps. Everybody's interested what it's ringing, and we're showing those pictures without any hesitation. Now, so there is one bump with around 3 sigma local significance at 100, another one at 1.2. So we'll keep watching with independent data set from around 3. On the right-hand side, we don't see anything smooth behavior, and we're setting an upper limit on the cross-section times branching fractions. We also have some limits within the context of SSM for additional Higgs bosons, and this limits are set to 350. Another search which we conducted is looking for a Higgs decay into a pair of Ws. This Higgs, it's heavy, it has quite broad width. So we're considering the two production mechanisms, the gluon fusion and the vector boson fusion. And so, as I said, with the mass, the width of the Higgs changes, it grows. But this is a repetition exactly of the same type of analysis which was done to look for standard model Higgs decaying to 2Ws. And several scenarios were considered. One of them when there is no VBF, everything is dominated by the glue-glue fusion into the phi. And the other one which said it is only production mechanism is through the vector boson fusion. And then there are two other alternative, an alternative approach when the parameter is set to float in the fit, and the fit tell you what it is. And another one which one can assume that the ratio of the glue-glue fusion to vector boson fusion is like in the standard model. And that's what you see on this last plot. So the limits can be set, as we can see, looking at the crossing of the observe limit and the prediction with a particular model of production. And then we, again, looking very closely with magnifying glass for the case of the VBF is dominating, this not dominating, it's the production channel which is responsible. There's no glue-glue fusion component. We see that there is some bump around 650, as I'm mentioning. Those objects are quite broad. And in the same publication, there are some additional limits within the context of MassSM and 2-Higgs tablet model. So our search for new Higgs objects are more and more sophisticated. That's another one when we're looking for not one new object, but two resonances X decaying to either a pair of two Higgses or a Higgs with association with another resonance Y decays into BB bar and gamma gamma. We can interpret, thank you, we can interpret the results either in the context of search for the radion. You have two different hypotheses about the coupling of the radion. And there is a red dotted line here corresponding to the coupling of radion at 6 TeV. And we can eliminate radions with masses less than 600. Here it's more visibility for the graviton. You can just see which area is being excluded. On the right-hand side, we're looking for the alternative for this hypothesis when we have a Higgs and the Y produced. That's the summary on this plot on the right-hand side. When and along this axis, you have the mass of the Y. Different curves correspond to the different values of the X. The limits are derived. Everything is consistent with the standard model, except there's one point at 650 GeV, where at the mass of around 90, we see a bump with those significances globally and locally. So we will keep watching that area quite closely. Another one of interesting searches for alternative Higgses is looking for charge Higgs. They are motivated. So here they interpreted those searches in the Georgia Mahachak model. It's quite popular among not only LHC experiments, but also people who are working on the NLC and ILC are using that model because it has very interesting spectrum of particles and phenomenology. One addition of one triplet really gives you a spectacular spectrum of particles. Here we look specifically for charge Higgs or double charge Higgs decaying into a pair of two W's, so W and a Z. Again, we derive the limits. We are also eliminating in this two-dimensional correlation plot certain values of the parameter SH. This is the ratio of the vacuum expectations value between a doublet in this model and a triplet. And this is not allowed. Everything above this curve is eliminated. So what is left within this model are these values of the parameter SH as a function of mass. I brought this measurement here because we all remember very well the excitement about CDF announcement of a new precision measurement of the W mass. There is, I think, a dedicated talk in a few days by Oshtosh about the measurement. However, following that announcement, because there is some tension in the electroweak fits, there were hundreds of people, hundreds of papers, or hundreds of people releasing papers with interpretation. One of them was done by John Ellis and co-workers. The reason I selected this paper is because I like this scheme to use SMEFT. Many of us use SMEFT. We're all trying to test one operator at a time. We select the order of dimension of this operator, 6 or 8 or whatever it fits, always one operator at a time. Few papers discuss what is the interrelation between dimension 6 and dimension 8 and energy scales. But what John did, they also, and the collaborators, they did global fits to all dimension 6 operators, which may be responsible for modifying the radiative corrections to the mass of the W. I'm sorry, radiative corrections which will modify the mass of the W. However, they made one step forward, and that's what I like here, that actually they make a connection of a specific dimension operator, dimension whatever, 6 or 8, in this case is dimension 6, with specific models. And that's me who was working on some calculations or measurements of limits on higher dimension operators in the vector boson scattering. was always missing. What is the next step? I have a limit on the dimension 8 operators. How do I use it in the physics, or how you will use those limits? And what John did said, okay, now this they identify 5-dimension 6 operators. They said, they are related to this characteristics of the models. It was not a sophisticated decoupling analysis across all the models, but there is one of those parameters and one physics scenario when if you had psi triplet in this 3-level single field extensions, that's what they did, but it's generic, it's simplified, but it's stimulating and guiding. And what you see here, while I was talking, we already read that the limit on the Higgs charge, exclusion limits on the charge Higgses is around between 2000 and 3000 GeV. John is looking for something in this particular scenario, which is closer to 3. So within around 3, we can just close the close the gap, and then perhaps say that this type of extensions is excluded from the data. For me, that's a nice way of enhancing all this establishing the limits for higher dimension operators, but that's my opinion. Now, in the resonances of vector bosons in the final state, I have to, so we don't see anything except, there is again bumps. This is looking for, gravitons, heavy spins, radiance, again, in the highly boosted reconstructed decays with the vector bosons with one superjet. As in its new algorithm, superjet is a jet where we don't distinguish two-jet structure coming from a decay into two quarks, but we identify it as a fat jet, and we understand its systematic and jet energy corrections for the superjet. So the limits are I listed here. There's one bump, or two bumps actually, 2.1 and 2.9 with these significances, and you can just look at it. Another interesting search is for leptoquarks. Leptoquarks gain again or regain popularity when it came to explaining the B anomaly. So that motivated a lot of analysis. And this is one particular analysis which concluded with the limits and the different scenarios for scalar leptoquarks, vector leptoquarks as a function of their mass in the T-channel exchange and the pair or single production. And then we see around 2 TeV an excess in the T-channel exchange, which has quite high cross-section. We will be looking at it. Here's the summary. As I said, we don't have to read everything, but there is a link in the copy of my talk where if you are interested, when the new results are becoming available, you can just click and see if there are any new results being added. And there is this particular event. So as the run started, one of the first analysis which was completed and published was the dijet spectrum. So we look at two dijet combinations looking for dijet resonances. This time around, we did the following. So we're not only looking for dijet resonances, but quadruple jet resonances, and that's what it is. In the 2017, at the end of the dijet analysis, we found one interesting event when we started to study the kinematics, and we all looked with magnifying glasses if everything is done correctly. In 2018, there was a second event showing up. So then we are plotting here the 4-jet mass as a function, not as a function, sorry, 4-jet mass correlation with the dijet mass, and this is where the 4 of the events are laying. And then there are those 2 spectacular events at 4-jet mass at 8 TeV. These are the ones which are included here in the slide, and the dijet mass of 2 TeV. And we perform proper analysis. You see there is some correlation, so there is a different phase space used for optimization and calculating the limits. And you see that we see 2 bumps also here at the positions which is marked in the non-resonance search and the resonance search. And you can have a look. Sorry, I have 1 minute. a very interesting thing. So I don't want to go into the, what is the model for the resonance, but it's briefly listed here. It brings the hypothesis of a dipole, but it's a quite generic analysis of 2 jets versus 4 jets, and then we can use all sorts of interpretations. But the one which we picked for the publication is listed here. And again, I think this is something which is being observed by both collaborations from the very beginning, and with each new update there is always something interesting to pop up, or every year of data taking. So this is 2017, this is 2018. To run 3 maybe bringing something else. So a summary of all the exotic searches, those which I picked and those which I have not selected, you can see here, with the same caveat that you can just link to the summary page. What's next? So this plot has been shown. So what I want to add, that we're now in the beginning of run 3 running. We expect to see 450 femtobars of integrated luminosity. The run will stretch until the end of 2025, followed by a big, long shutdown of 3 years of finishing up run 3 analysis and installing the new detectors, with the expectation that we will take off in 2029. So that's long-term plan. Run 3, the highlight. So far, you see here that in a month, this is end of July, this is end of August, we already accumulated 10 femtobars. And you see that there is a steady delivery of luminosity. This is the peak delivered luminosity. Machine works extremely well. Those gaps here are the scheduled maintenance periods for the machine. They don't last usually more than a week. Machines schedule them periodically and ahead of time, so that's nothing unusual about it. And then integrated luminosity per day, you see that we're still, this is the semi-log scale, it's still increasing, but we're getting a delivery of 1 picobar. Sorry, this is the integrated a day. So that's what it is. Now the scenarios for running, I already mentioned this 1 till 10. So to conclude, so we performed many analyses and concluded with very nice number of interesting measurements. So there is a lot of food for thought for everybody. And so far, there is, sorry. No sign of anything new coming up, although those bumps, which maybe I put too much emphasis on that, but we all want to share the excitement. That's, I think, if we don't say something, then we will be asking, we saw that plot where you saw that bump of 3.8, what is it? So now we're just not staying shy from sharing the excitement. If we understand the analysis and the results, we're just publishing it and showing. So we have many improved limits in those searches. I don't know what one can conclude in terms of restricting possible phase space of parameters for the future model building, but that's why we're here to discuss. And the open questions which were identified before still exist. There's 5 praxes, which everybody knows by hand what they are. I don't need to repeat them. And there's more to come. So as I said, I gave you only the flavor. It was my personal selection for this presentation. There are 3 more talks which are covering CMS results. So I think 2 of them are Atlas CMS combinations, and there is one which is, no, sorry, they're all combinations. Thank you very much. So there's not another CMS talk. Thank you, Atlas, for identifying the speakers. Sorry. And that's the link to the page which gives not the public results, but in their preliminary version. So if you want to see the papers as they approved and either on the way for publication or approved in the context of some conferences, that's the link. Thank you.
Thank you very much for this interesting talk, a lot of material. So any questions or comments? Yes, please.
Yes. In page 25, you showed
3.5, you said?
25.
Oh, sorry.
25. You mentioned about the standard model, but the standard model, the calculation of that is highly non-productive. So how do you, what kind of a standard model calculation are you using there?
I don't remember the reference in my head, but I can check it for you. I mean, it's public, sorry. I mean, for me, standard model prediction is uniquely defined. We all agree in the standard model without neglecting everybody's contributions. So I will check specific to answer your question. I don't remember the reference here. Thank you. But I will be more concerned about the uncertainty rather than the value. If you're saying that one group has this number and another group has a different number, and it's outside the uncertainties, then theorists or standard model, how to say, participants in those calculations have to talk among themselves. This is not the first time it happens that we might be coming with alternative interpretations. Very good. So it's not the case here. So that uncertainty has a chance to be used as a reference. How much work we have to do in order to come close to that uncertainty, for example. That's the next goal for this analysis with the new data set. There was another question, I think.
There is another
in the back
question by Professor Frampton.
Can you say, excuse me, can you say anything about the searches in same sign leptons of CMS?
Yes. So there is, I don't think that there is an analysis of searches in same sign leptons, which came to the state of a presentation of a comprehensive presentation at a working group, which will say we're ready to go for pre-approval and approval. This is to best of my knowledge. And it's not that collaboration defines a program. Each PI or principal investigator has his or her students and postdocs, and they define the physics program and analysis which they would like to involve. So even if somebody says, I have a brilliant idea, like maybe yours, to look at the same sign dileptons, still we need to find a group and students and critical mass to conduct an analysis. And as far as I know, as I said, for me, the criterion to answer your question is, I don't recall seeing the comprehensive description of an analysis, which is a requirement before we go into the pre-approval and approval process of any given result. So maybe some people are still working and it's in some state of concept or something, but so which means that I don't expect that we will see a result published soon or shown soon. Sorry, that's a preview. Yes, but it's in the context of same sign WW. And for example, in the beginning, we identify this search for WW. The motivation was to look for electroweak production of WW. And we established it with 2015 data. That's where the first limits on the double charge Higgs came. It was just a byproduct. So you can look at the WW final state. You can then interpret it as, let's look at the limits for producing double charge Higgs, or you can calculate dimension 8 limits on dimension 8 operators, right, in this process. So those results are published. I thought that you wanted to look, sorry, you were asking me about the same sign leptons inclusive as a physics result, but we can talk about it later.
I'm a bit confused because Atlas has produced a paper last March, which was inconclusive because they couldn't apparently get to a high enough invariant mass. I think they reached 1.08 TeV.
Okay.
but my understanding from talking to CMS, for example, Verdi, is that CMS could go to at least 2 TeV or perhaps even more in the invariant math. So is it just not being able to find people who are doing it? It's a bit puzzling.
Yes,
to me.
those who work at universities know how difficult it is to identify a graduate student. Everybody else, including those who work for the national labs, also will tell you how difficult it is to find postdocs. Yes, there is a problem with personnel.
Yeah, probably last comment or question there.
There's a quick question about the ATV full jet events. So in the full jet events, they must be very high PT objects. Did you look at the structure of these jets? Maybe this full jets comes from the bottom to tops, whatever, kind of boosted, highly boosted, or it just identified as normal fat jet.
These are the two.
Yeah, well.
So they are not BTAC, because all the information which we collected, it's presented and described in the publication. So they are not BTAC. Sorry, there's none of those 8 jets has a B jet. That's what I wanted to say.
And they're quite narrow. They're not kind
And
of.
they are quite narrow. They are not super jets.
Yeah, that's what I mean.
Yes,
Thank
so
you.
they are not super jets.
Thank you.
Okay, thank you. I think we can thank the speaker again.
Thank you.
And we move on to the next speaker. So the next speaker is Janusz Bluza, who is going to discuss standard model precision measurements.
Thank you. Yeah, okay. Anyway, it's an opportunity to thank you, organizers, for inviting me. I'm first time here, and it's very nice place to be. Close that. Okay. It's above a little bit up. No, up 4 more. Here. Oh no, it is this old one. Or is this up? Yeah. That one. Okay. Yes, thank you. Okay, thank you very much. So I will talk about precision. In to large extent about standard model, and usually people are starting about precision when it's with Tycho de Brahe and Kepler, when both made possible to understand how what are laws connected with planets. And this is something what is also important in particle physics, of course, and sometimes it is triggered by experiment, sometimes by theory. It is my own list. Of course, you can have different, but what was triggered by experiment to theory, I think it is like a muon discovery and J-psi, which changed paradigms much. And then G-2, G- electron and muon anomalous magnetic moments. And also very important is parity symmetry violation, where I just wrote that this year you can find a nice talks connected with 100 years of anniversary birthday of Young. And on our side, theory is also like we have a third generation which somehow triggered experiment to make experiments to discover tau and top, and of course scalar Higgs-Engel boson. Itself lab SLAC LHC is connected with standard model corrections very much. And I have no time, but in backup slides, I gave some pedagogical examples from TASI lectures and from Fred Jägerlener, where it is shown that first, without corrections, we are far away, many sigmas from experiment, and also oblique, so-called oblique corrections are not enough. So we need also vertex boxes and so on. And of course, it was a very big, nice work by Weltman, where he shown that rho parameter is proportional to MT square, and screening theory with Higgs mass. It was all theory driven, which came to the lab studies. And finally, precision is now also with neutrinos, masses, mixings, orderings, CP phases, everything is so beautifully going into precision. So in future colliders, especially I will talk about E plus E minus, theory and experiment are so much involved that again will be probably a very big connection between them. But sorry for Greeks colleagues, the first thinkers were not like Tycho de Brahe and so on, and or Greek philosophers, but it was already 30,000 years ago where people start to abstract things, making some modeling. And here is some Abdi Blanchard-Bon example where it was somehow first time projected into what is going on sky. And it was probably the first lunar calendar. So precision is somehow in line of what mankind and people want to do. So about discovery strategies, I also put here some nice texts from Feynman, who, because what we are measuring is usually want to find these anomalies. This is one way, indirect measurements or direct. And once Feynman said that it would be interesting to see if they falsely, experimentalists, if they falsely record that there exists a certain BAM or an oscillation in a certain curve, then all theories would just jump into that to find what is it and so on. So yeah, we must be very careful with that. But anyway, I've chosen only two things to talk about Z-pole precision physics, and maybe also I have some time to connect it to how to connect this precision studies on Z-pole with neutrino physics. More with technical things about precision physics will be in the next talk. So not covered in this talk is everything about E plus E minus connected with other measurements, not Z resonance, but with WW, top quark production, or Higgs production with association with Z, which are also very debated in linear colliders or circular colliders, E plus E minus issues, because we want to have a very good accuracy and how much we can do here. And also I will not cover LHC and so on, but fortunately here already was a lot about precision. Here I just taken some slide from Sotnikov last CERN workshop in June, where it is summarized how sophisticated things at LHC are already done in terms of loops, so effects of radiative corrections and multiplicity, so legs, and here you can find many things connected with pure QCD or electroweak and mixed electroweak and QCD things. So it is really great, and how it develops. So needs for precision in the future. What motivates me to do it is basically this plot for future colliders, which are circular FCC or ILC or CLIC or CEPC in China. And all of them has a huge luminosity, and especially at Z resonance, the production will be great. It will be 10 to 12 Z decays, it is estimated. So that is why we are calling it Tera Z physics. And if we compare it, for instance, with LEP, the total Z decay production was 17 millions, 10 to 6. So we see we will have something like 6 or more. So with such statistics, we will have a great precision to do. And here is another slide which summarize what kind of physics we can do. And this is not only about precision with electroweak 6, but it's also through decays will make a lot about taus and big quarks and so on. So so many things can be covered in this, what sometimes it's also called Higgs factory or electroweak factory or even BC tau factory. Okay, so Tera Z physics, what I mentioned, is a breathtaking experimental precision. What we should have if such colliders will appear. And here I would like to focus on one, just because short time, decay width and mass of the boson. And now present error for the decay width after LEP is still 2,300 MeV. So so this is sorry, keV. So 2.3 MeV. And in future, it is supposed to be only 25 keV, or something like 2 orders of magnitude better. So this is incredible improvement. And behind that, always precision studies must be done to fix, to match this experimental precision to this. So how to do it? Of course, we must do a lot of in theory also to get into such precision. And fortunately, we have already many things, and the legacy of LEP is very here important, where we have very complicated thing when we go into terms of, but it is of course not LHC. In LHC, we heard this morning that already 3 billions of, almost 3 billions of Z were produced, and billions. So it's a much more than it was at LEP, but precision is not that, because E plus E minus is somehow much more clean concerning background or so on. Here we have only something which we have to care about, additional photons or pair emissions or some additional QCD, which we can easily or relatively easily understand. And of virtual things which we have here, of course, we have Z resonance, which is the most important, but we have to understand how Z resonance goes with our possible also particles, maybe Z prime. Also some corrections, which are not only vertices, because vertices can decouple, but we have also boxes. So we have so-called non-factorized terms. We cannot factorize this vertex from that vertex by when we have boxes. So this is everything very complicated. And also Zbyszek Wąs was talking about KKMC, which makes possible to also Monte Carlo generator, KMC and others can extract all these things which we have around and get something what is clean and in terms of form factors. So what we want to have is so-called electroweak pseudo observables, clean vertices where we can put our, compared to our theory, what we have here after this as extractions. So for instance, unfolding of QED, so removing all the photons which we don't want to have connected with vertex, we already change results very much. It is known from left. And this is only one example of how important is such studies of all corrections which we have here. Also, it is important to understand this resonance, how it goes, what is in background, what we can put in the background, and what is really in a resonance connected with the Z. So all of this is quite complicated because we have a process which has fermions with photons, and we have to extract it properly to get into only Z physics. So everything is quite complicated. And so this is a scheme, how we do it after unfolding all the rubbish which we have around connected with QED, QCD, or whatever. We are getting some vertex and which we try to improve. So the thing which we are improving is now at the 2-loop level, and we already completed it. And now we go into 3-loop, and it will be next talk. So here are examples of definitions which we have for all these things. And here again, if we make it more accurate with a vector and axial vectors, we come to the definitions through that. And that is why we can add more and more loops, corrections, and in terms of all these things and see what's the result. And the results are like that. But for decay width, as I told you, current so-called theoretical intrinsic error is 0.4 MeV, and in future it will be 0.1 or so 100 keV or even better. And this is without 3-loop calculations, and also parametric errors are very important, and we can see what is their meaning, and the most important are electromagnetic alpha and strong, and other parameters will be covered here. So everything gives still below what we should have for future colliders, and it is much work to do it, because for instance, when we completed recently 2-loop calculations, we went down from 0.5 to 0.4, but we should go to 0.1. So definitely we need 3-loop calculations, and also schemes dependence is very important, because for instance, what we calculated to the end at 2-loop gave us a result at the order of 0.5 MeV, and the errors which were intrinsic theoretical errors which were predicted without this calculation was 0.1 MeV. So you see, the result which we got in calculations was much bigger than what was, let's say, in some prophecy or some hand-waving way estimation. So this is really important to make the correct exact calculations to get into the point. So how to decrease theoretical error? We have to calculate this. And here I've shown estimations of how to make possible way estimations for missing 3-loop or other calculations. As I said, it is a kind of hand waving. For instance, we can compare with orders which we already know and make geometric series and calculate everything. And that is why we can expect that it is something like 0.4 MeV. But the point is that when we know all of these calculations at the 3-loop, usually or 3-loop, here are examples of estimation for 3-loop and 4-loops. When we do it, we will go to a much lower error, because each of these error is at least with 2 digits. So we will basically go in below what we expect. So this is the present status of estimations. We need to calculate 3-loop results and some of 4-loop with QCD and electroweak mixed involved to get into precision, which will be which will match future demands by colliders like circular colliders, especially at Z boson, FCC or CEPC. And methods and tools, we have now many of them, and especially recently was made the differential equations method, which will be also shown example of calculation in Krzysztof talk. So I have no much time. How much I have? 5 minutes. So only saying how to now connect it with one of aspects like neutrinos. So anyway, BSM is, I like it when Weinberg once said that in my life I have built only one model. We would like to have also something beyond that, also one model, but we don't know which one. And at least what we know from many things in history, we know that now we have something like effective number of neutrinos which is below 3. And it is also very interesting that it's usually below 3. It was always like below 3 in accuracy. So it is even some theory which is simple saying that if we have a standard model and left-handed neutrinos, then the number, and we have some additional right-handed neutrinos, so they will mix, and always we will have a number of neutrinos less than this number of left-handed neutrinos. So if we have 3 left-handed neutrinos, it means that this effective number should be less than 3. And you know, we have this standard model 3 times 3 UPMNS matrix, and it is somehow non-unitary if BSM is here. So we can then study how much it is non-unitary. And for instance, here it depends on mass scales of a non-standard scale which we have of additional neutrinos. And here is example of ranges which we can estimate. You see, they are not so big, but they are non-zero. So some mixing are still possible, of course, for non-standard models. But how to connect these studies with BSM models? Usually we are talking about coupling and non-decoupling. If here it is nicely shown example, if we have some new scale and the masses of new physics is around the standard model, let's say they are much mixed between them, and then we have non-decoupling. And but also in non-decoupling we can have something what in precision is different from the standard model. Here is an example where we study how it can be in some specific model. And for instance, if we have some additional gauge boson, so then a correction to the standard model is not like mt square over mw square, but it is driven by the heavy scale here. So it can be quite different. Delta rho parameter can be quite different from the standard. So it is not always like that. But fortunately for standard model physics, we have it quite the same. We can make the connection and make subleading effects adding to the standard model. So if we calculate 2-loop, 3-loop standard model, we can then fit it with non-standard physics nicely. Here is some from Ruiz, Richard, who nicely shown that actually if we have Dirac or Majorana neutrino, what is important and worth maybe Nobel Prize is to establish if it is 1/2 factor here, because if it is Dirac or Majorana, but saying seriously, we can make a lepton favor violating decays of Z boson, and then we can both calculate Dirac or Majorana. In Dirac case, we will have flavor violating, and flavor violating we can just compare with what we have in precision physics, and this is what we are now working on. Okay, so my summary is more or less like that Z-pole physics was essential in the past and will remain the bread and butter for precision particle studies if future E plus E minus colliders will come to reality. And then we have a lot of nice things to do, and there are many challenges. And for instance, what I try to stress, we have to know the knowledge of free loop electroweak and mixed electroweak QCD results leading for loop. We have to know QED interference effects and non-factorizable corrections in the Z physics. We should adjust Monte Carlo generators at least at 2-loop to BABA, because it is important also to extract again a number of neutrinos, and challenge to improve input parameters remain, and so on. So with Z physics, I think it is not some kind of theory which goes with lab, but it has a very nice opportunity to be interesting point and very sensitive to new physics models, because we have a reference, we have standard model which we can accurately calculate and measure at Z-pole. That is why non-standard physics with heavy states in virtual indirect processes or lepton flavor violating in such huge statistics as Z physics can give us the big opportunities to work on. Okay, thank you.
Thank you very much. Any questions? The speaker? Yes.
Just one question to your last line, where you strike through multi-loop numerical programs. So what do you mean by this, and why do you think it's a disadvantage to have those or use those? Because just in case we calculate within the standard model, including electroweak standard model, the difference to BSM physics is we know all the values of the input parameters. So therefore, in this case, it would make even more sense to me to use, for example, numerical evaluations for the known input parameters once and for all, tabulate the results in tables or whatever.
Yeah.
And we do not need to evaluate them over and over again by having analytical tools. So why is
yeah, so this numerical, which I'm thinking is purely connected with virtual only. So that is why I was fast, but these programs which are now connected with differential equations, it is just how to calculate multi-loop corrections. They are now at the level that numerically it is not any problem, and they are now even very nicely automated with AMFlow, for instance. This is the new program which came this year, and we already studied, and it will be example how it is so fast that it will be almost possible, as you said, maybe even used in live calculations, connected maybe with Monte Carlo and so on, even if you make. So it was only remark on virtual, yes. For Monte Carlo and other analytic also will be all time will be very important. I left analytical, especially here, will be very important. But for numerical studies, at least for Z physics, Z-pole, it seems that these programs are really very good already. And in some next years, probably when people will do it, it is a big chance to compete somehow most of these things. If of course, groups will be stable and so on.
Okay. I guess we will stay in the same subject. So the next speaker, let's thank the speaker. So, yes, the next speaker is Krzysztof Grzanka, who is going to be more precise to discuss Z boson decays in next to next leading order 11.
Okay. Can you hear me well?
Okay. No. Two pound. Yes, this one. Yeah. And to the start, maybe it's in the middle, so it would be off to start. Okay, yeah, I know, and it works. Okay, so yes, so we will stay in the same topic, and yes, I had a really good introduction. I wanted to thank Janusz for making this really huge introduction for me, and also for organizers to having me here. Okay, so the outline of my talk will be also a few words about the standard model corrections to electroweak pseudo observables and what is the present status. This is partially covered by Janusz, and I will somehow just briefly add to it. Then I will tell a few more words about what is the task to go to this free loop level for these standard model electroweak pseudo observables, and why was it hard and maybe it's not. And this will be already in the numerical calculations and what methods and tools we have, and some examples of these calculations, and then I will summarize. So going back in time, this is all, for the NNLO calculations. These are a list of, let's say, references and years when these calculations were done and published. And so these corrections are starting in the beginning of this century. So it's already like 20 years from beginning to the latest corrections, which were in around 2019-18. And so it took like 20 years, and now we want to head to free loop, and let's hope it will go somehow. Well, and we also have this leading fermionic free loop contribution already calculated in 2020, and this is what we are at now. And so for the higher order corrections, so first let's have a look at this table generated with TiZet, which is a good program because it helps us to it makes us possible to see how big are the corrections and what is the effect on the pseudo observables. So here in this table we have some gamma z to new width and the complete width of the Z boson. And what we have here in these columns is different corrections included or not included. So 1 to 5 is the jump from 1995 to 2017 corrections to hadronic vacuum polarization. And this is from first column to third column, and this is concluded in the last column here. And so we can see that for the E plus, E minus, so for the leptonic decays, it's not much. So it's at the level of 10, 20 keV, 1, 2 keV actually. And for hadronic and for the total, it's a bit more. And the other, sorry, the first delta here, it was this column, and for this 6 to 8, so the second and third column comparison is the inclusion of these corrections from 2004 to 2019 for the two-loop electroweak calculations, and we can see also that it makes some big difference, let's say. And why is it important? Because we are improving with these corrections, and as Janusz said, that it's important. First of all, because we have these new experiments coming that will need this precision, and secondly, it constrains the new physics. So it constrains the phase space for new physics simply, and that's why it's important. And for the input parameters, we also see the dependence on top mass. So if we take some range of top mass, we can see how big is the influence on the electroweak pseudo-observables simply. And we can see that from the top mass, we really get quite a lot of contribution to W decay and so on. For the Higgs mass, we can also see what is the contribution to its process and observable. And so moving to free loops, how big is the task? So here is a table with comparison of how many diagrams were involved in process like Z to BB bar in 1 loop, 2 loops, and 3 loops. And so this is already a bit, let's say, lower number after some exclusions and so on, like written in the caption of this table. And what we get from this is we can see how much more diagrams we have, like 120,000 instead of 1,000 for 2 loops. And this is a lot of diagrams to calculate, and also the integrals get much more complicated. And let's say as the first step to these free loop calculations, we start with free loop self-energy integrals for Z and W decay. And going to the methods and tools, so this is like the same slide that Janusz shown already. So these two first methods, Mellin-Barnes method and sector decomposition methods, were used for 2 loop calculations with success, and this gave us the full correction for 2 loop contribution. Then, but we tested it, and it's not enough for the free loop, and either we would need a huge increase of efficiency for this method, which is probably quite hard, and either this or another method that would help us with cases that we cannot really tackle. And thankfully, this method of differential equation somehow made its appearance again, because it's not like the newest method, but it gets a second life, I think. And so with these package defects, it came into life again. And there are these packages already available, this IMflow and Seaside, and also the method that I will discuss that we used for our calculations. All based on differential equations method. And so for the 2 loop calculations, the accuracy for the single integrals, single diagrams, what was needed is it was 10 to minus 8 for each integral, or the worst could be, let's say, 10 to minus 6 to achieve the final result with accuracy 10 to minus 4. And for the free loop, we again need to have at least these 8 digits or 10 digits even. So huge precision of these integrals. And as I said, sector decomposition plus Mellin-Barnes method doesn't fill everything. And even for the self-energies, it's like 20% or 50%, let's say, of integrals that we can get. We can calculate, and not always even to this accuracy that we need. And so going to the calculations, we have some free loop integral for the Z decay, and this is in Minkowskian kinematics, so in physical region. This is done with Parsec deck, and we can see that, okay, it gives us smaller of 10 to minus 10, it is fine. And we have some integrals that are really fine with Parsec deck or any other program. then we can have this Mellin-Barnes method that we can see in this for this integral already bisect has like 3 digits, 3 decimal digits. So let's say 5 digits accuracy, which is also not enough. But then this MB method, Mellin-Barnes method, comes into play and gives us better result, and it already gives us the result that is fine for us, let's say. And why is it maybe a word of information? Why is it important that we are in the physical region? Because let's say the easy explanation is if we take s equal 1 here for this integral, this is just a part of this integral. In Mellin-Barnes representation, we get this s here in the factor in the integral, and if it's positive, then this is negative, and it's changing signs, leading to instabilities in the calculations. This is one of the reasons why it is difficult to calculate. And in Euclidean region, we are pretty much safe with 10 digits for most of the integrals that we need to calculate, but it's unphysical, and then it makes problems. But speaking of this differential equation methods, we lately published a paper on what we can do with these differential equations. And so how it works? It works like we calculate a set of boundary conditions, which are master integrals, and we can calculate them in Euclidean region, which is much simpler, and we can get much better accuracy. And then we, with defects, and we can export simply these results from, let's say, s equal -1 to 1, from Euclidean region to Minkowski physical that we want to have the result in. And this is without a big loss of accuracy on the transport. And so here we can see that for this two-loop box diagram, we already have quite good results. But there is also, for this first example here, we can see the comparison of bisect deck, which gives us like no accuracy at all. And it took like a lot of time already to get with this imaginary apparat. We get like this 2 digits accuracy, and it's okay, but it took like a week on the computing machine. With our method, it took not much time, let's say half a day or something like that, to get like 10 digits, and this can be improved by calculating boundary conditions with better accuracy, which can be done either with bisect or any other method. And with AMFlow, which is also one of these new differential equation methods, based on it, we can get like 15 digits in 15 minutes on laptop, which is insane. And as Janusz said, it can really help us calculate them fast. And so to summarize, there is a great progress in development of methods and tools due to this differential equations method. And this gives us good hope for the free loop calculations, that we can really complete them. And one important take from this talk is also that knowing really precise the standard model, we can have this good, let's say, starting point to search for BSM physics, and we can constrain the new physics parameters and so on much better, having more firm standard model for estimations. And that's all. Thank you for the attention.
Thank you very much for this nice, precise, and well-timed talk. Any questions for the speaker? Yes, please.
Thanks. You've described how you treat virtuals, and what do you do with real corrections? How do you handle them?
We don't. I don't know if I understand the question. Can you?
because those diagrams will have infrared divergences,
Yeah.
which are cancelled by real emission diagrams.
Mhm.
So you need some methods of handling infrared divergences at two-loop level.
Yes, so okay, at two-loop level it's solved, and at three-loop level it's still work to be done because it's more tricky. Going to next order, it's more tricky, and so this is mostly for till now it was mostly done by illustrators, and yeah, so this is probably I mean he's mostly working on that.
Okay, thanks.
Thank you. So I see no other questions. So let's thank the speaker again. And now we move to the last talk before coffee break. So the next speaker is Daniel Milne, and we change subject to QCD instantons at Hadron Colliders.
Thanks. I'd just like to thank the organisers for giving me the opportunity to give this talk, which is based on these two papers with my supervisor, Valia Koza, and collaborators. To briefly outline the talk, I'm just going to, first of all, try and persuade you that instantons are interesting. Going on to calculate the cross-section we would expect to see at a Hadron Collider, such as the LHC, and then going on to discuss search strategies. So first of all, motivation for this talk. Instantons are a prediction of the standard model, and are one of the very few theoretical predictions which haven't yet been experimentally observed. Observing the instanton would give us a better understanding of non-abelian gauge theories, as they're a ubiquitous feature of non-abelian gauge theories. And according to our calculations, the cross-section is quite large, and so gaining a better understanding of the instanton would give us a better understanding of the QCD background, which we see in the LHC. They're also related to the vacuum structure of the standard model, as well as appearing in all sorts of beyond standard model theories, such as SUSY and all sorts of others. So just start off, for anyone who's not familiar, although I'm sure most people are, to briefly explain the instanton. There are topologically protected configurations of the gluon field, leading to a vanishing field strength tensor, which gives us multiple degenerate vacua. Instantons are always treated in Euclidean space, so we have to Wick rotate. After Wick rotating, by considering that we want this vanishing field strength tensor, we end up with maps from the 4-sphere to SU3, which topology tells us are characterized by the integers. And so we have an infinite set of vacua characterized by the integers -1, 0, 1, 2, etc. And the instanton is then the configuration of the gluon field, which tunnels between adjacent vacua. This integer is called the topological charge, or the winding number. And so the instanton has winding number 1 and shifts you up vacua. The anti-instanton has winding number -1 and will shift you down vacua. And I show here at the bottom explicitly the form of the instanton. X0 is called the center of the instanton, and rho is a constant called the scale of the instanton. So the main process which we would see in Hadron Colliders, if we consider the gluon initiated process, which will be dominant due to the saturation of the parton distribution functions, we produce NF. NF is the number of light quarks. So we produce NF pairs of QQ bar, NF QQ bar pairs, and an arbitrary number of gluons in the final state. The fermion content here is determined by the ABJ anomaly. As I'm sure everyone's familiar with, the chiral current given here is not conserved in QCD, and one can prove that the divergence is given here. And after integrating this, we get that the violation of the axial charge is twice the number of light flavors times by the topological charge. And since the instanton has topological charge 1, we must violate it by precisely 2 NF units. calculate the cross-section, we use the optical theorem. Given that our final state is largely determined up to the number of gluons, the total cross-section is equal to the cross-section of the process I showed on the last page. And so when we take the complex conjugate and calculate the matrix element as required by the optical theorem, we end up with an instanton anti-instanton configuration, which we have to compute the action of. This enters into this formula here in this exponential coming from the path integral, e to the minus action. We also get appearing in this exponent this term, which comes from resumming initial state radiation and the interaction of gluons propagating in an instanton background. This term is particularly important because we get e to the minus rho squared term, which cuts off this integration over rho. So as you can see, we integrate over instantons of all sizes and all separations and configurations in the gauge space. And prior to the addition of this term, this integral diverged and we had an IR problem. So including this term is crucial. And here we also get a factor appearing from the fermions in the final state. We can compute this integral numerically and we get these numbers here. On the left, we have the partonic center of mass energy. In the middle, we have the average number of gluons which would be produced at this energy, and the cross-section in picobars, the partonic cross-section, that is. I've cut off the table a little bit early here because one can show that the cross-section blows up a little bit at low energies. And if you go down to about 20 GeV, say, then if we were to calculate the hadronic cross-section, it turns out that this completely saturates the total proton-proton cross-section at the LHC, which is clearly rubbish. So to solve this, we include a small virtuality in the initial state, consistent with data of about 3 GeV. And this introduces a factor of e to the minus q rho into our cross-section calculation, rho again being the size of the instanton. And this stabilizes the calculation quite nicely and allows us to go to much lower energies. So here's the same information, including this 3 GeV virtuality in the initial state. Now that we've calculated the cross-section, we want to try and detect the instanton at the collider. It's not apparent from the formula I showed earlier, but again, one can show that the final state of the instanton is spherically symmetric. There is no correlation between the different there's no correlation between the different momenta, and so we expect a spherically symmetric distribution. To aid us in searching for this, we want to try and use shape variables. Primarily, we use the transfer sphericity. So we define here the transfer sphericity tensor, which is a sum over all momenta, defined in this way. And then we define the transfer sphericity variable here, where lambda1 and lambda2 are the two eigenvalues of this tensor. The transfer sphericity runs between 0 and 1, where it's 0 for highly collimated events and 1 for spherically symmetric events. So looking for instantons, if we want to try and look for instantons in the LHC, it's very difficult because the usual Atlas and CMS triggers are not very sensitive to instantons. If I go back a couple of slides here, you can see that the instanton cross-section, although this is partonic rather than hadronic, the same holds true, it falls off very quickly with energy. And so we're dealing with low energy objects with approximately order 20 particles in the final state. And so each particle is only going to have momentum of order 10 GeV. The standard Atlas, and we have no leptons in the final state either, so we're restricted to using QCD triggers, hadronic triggers, jet triggers, that sort of thing. And each particle has order 10 GeV, like I say. And so the standard Atlas jet triggers, where you need a single jet of transverse energy greater than 360 GeV, or multiple jets of order 50 GeV, is just not sensitive to instantons. There are, of course, lower energy jet triggers than this, but they're heavily pre-scaled. And so the Atlas and CMS jet triggers are not very good at looking for instantons. One could potentially use minimum bias data. So the minimum bias trigger in Atlas essentially accepts all events and is usually run at a low lower luminosity and is used for calibration, that sort of thing, rather than data analysis. But we found that if you looked in this minimum bias data and applied these cuts, here I've found thrust, which is another shape variable. Definition is not too important, but is higher for more spherically symmetric events again. And if we use the full minimum bias data set of 337 inverse picobarns, we found that we could get the signal over square root of background around 50, showing that we have good statistical sensitivity. And because the tevatron was low luminosity and lower energy, the triggers were much less severe. And we also found that there's good potential to discover the instanton and tevatron analyses. We could also try and look at events with large rapidity gaps. So, for example, where one of the protons emits a pomeron, and the initial state gluon then comes from the pomeron. The reason why this is a good kinematic regime to use is because we're trying to suppress the QCD background. The QCD background can fake an instanton signal through multi-parton interactions, but when we have a large rapidity gap, each of these interactions comes with a factor of the gap survival probability, which is approximately 0.1. And so the large number of multi-parton interactions required to fake the signal is highly suppressed because of this. So if we look at low mass instantons going down to a partonic center of mass energy of approximately 20 GeV, and we demand high multiplicity final state, so more than 20 charge tracks, we demand that the sum of the transverse energy of the charge tracks is greater than 15 GeV. I should add that this is only looking on the opposite side to the gap. So in asymmetric pseudo rapidity interval, we used pseudo rapidity between 0 and 2. And we also veto the presence of charged particles with a high transverse momentum because that's unlikely to come from an instanton. I'll talk more about this veto in a second. We obtain very good sensitivity. Here I show a couple of plots. On the left side, we veto any particle in the range of pseudo rapidity between 0 and 2 of 2 GeV. On the right-hand side, we veto in the full pseudo rapidity between -2 and 2 of 2.5 GeV. So on the top, we plot transverse sphericity, and in the green, we have the instanton signal. In the red, we have the QCD background, and you can see that the instanton peaks significantly to the right of the QCD background, as expected, and also a significant excess of events. On the bottom, we plot the number of neutral kaons, which we suspected might also be a good variable to use because we always have this SS bar in the final state. It's a bit tricky to see here, but the peak is slightly to the right of the background for the instanton. And again, we see we have a large excess of signal events compared to background. Finally, just to summarize, instanton processes are a good further test of the standard model, predicted in the standard model, but not yet observed. All analyses we looked at were not sensitive to instantons because instantons are low energy, whereas the triggers are usually looking for high energy particles. So therefore, we have to use minimum bias data or possibly tevatron data. And we found some good kinematic regions where we have sensitivity to the instanton. Thank you.
Thank you very much for this nice, interesting and clear talk. So we have questions.
In the QCD background, usually which has a topological charge, is not only instanton, but there are various other objects which can exist in non-perturbative field equations. So in your case, how do you distinguish instantons with the other classical objects with the topological charges?
Okay, so yes, it's non-trivial. We can't do that particularly easy, but one way of doing this would be to look at variables such as sphericity, which where we expect the instanton to be spherically symmetric, perhaps compared to other topological objects where we may not expect such a thing.
In addition, the difficulty is instanton has a typical size. There are small instantons and large instantons. There are lots of variations in the instanton size itself. And in your model, you might have some assumptions about the size of the instantons. How do you obtain it?
So in calculating the cross-section, we integrate over the instanton size. So, that is less. The cross-section we calculate accounts for all sizes of instantons. In generating the Monte Carlo events here, we did use the average size of the instanton, which we calculated. So that's possibly something we would need to look into. It's true. Yes, sure. Yeah.
I believe there is another question. Yes, over there.
Kind of similar because from what I understood, you have a background which is basically a lot of jet with relatively low energy. That's your signal. So I'm assuming you're computing something similar for the background, but how do you exactly compute your background?
The background here is just taken from the is generated with Pythia as standard low energy QCD processes.
Okay. Do you have uncertainty on it? Do you know? I mean,
we don't, I'm afraid. This was more of a proof of concept. We just want to see if there was any chance that something could be done. Obviously, a full analysis would be needed if there was going to be an experimental search.
okay, thank you.
Okay, let's thank the speaker and all the speakers of the session. So now we have a coffee break and we resume at 6:20.
like to come to the reception tomorrow should sign the list, which is outside the room. Okay. So the first talk of the session is by Kazuki Sakurai, and the title is Testing Bell Inequalities in H2 Tau Tau Process at the ILC.
Okay, thank you very much. I'd like to talk about the test of the Bell's inequality in H2 Tau Tau at lepton colliders. So this work is still in work in progress, and these are my collaborators: Muhammad Al-Takash, Fabio Martoni, Kentaro Mawatari, and Priyanka Lamba. Okay, so as you know, in classical mechanics, the components of the angular momentum Lx, Ly, Lz take continuous real numbers. But a striking fact found in the Stern-Gerlach experiment is that measurement outcome of the spin component is either +1 or -1 in the h_2 unit. Okay, and let's consider the following experiment. So Alice and Bob lives in different galaxies, very, very far away. And in between, we prepare lots of spin 0 particle delta. And those delta particles decay into spin 1/2 particle alpha and spin 1/2 particle beta. And Alice takes this alpha and Bob takes beta, and they measure spin Z component. And because we have lots of delta, we repeat this process over and over again. And as we know, we know what the result very well. So Alice and Bob each will find some random sequence of +1 and -1. For them, the result is completely random. But of course, because of the angular momentum conservation, their results are completely 100% anti-correlated. So these are some possible sequence of plus and minus. But if you take the product of the spin Z of alpha and spin Z of beta, you always get -1. So this average of the SZ product is always -1. Okay. So what would be the most natural explanation of this? So since the result of the spin is either plus and minus, and you don't know which one you get, but the result is different. So this probably means the state of alpha and beta particles are different in each decay. And the result looks random because maybe you don't know the exact state of the alpha and beta particles in each decay. So in this situation, you can always introduce some hidden variable lambda, and we can write that in the ith decay of delta, the alpha and beta particle state can be labeled by lambda I. So I is the particular decay. And we can explain the result by saying that, okay, for some region of lambda, the spin of alpha and beta is +1 and -1. And for some other region of lambda, it is -1 and +1. And this blue lambda and pink lambda appears 50% chance. So this completely explains previous result. Looks very okay. But the explanation in quantum mechanics is very different. So in quantum mechanics, we say, even though the experimental outcome are different in each time, we say that the state of alpha and beta particles are exactly the same in every delta decay. And it looks like state takes this spin 0 singlet state. So this plus for the first level is for the alpha particle spin, and second level is for the beta particle spin. And these are the superposition of two possibilities. And before Alice's measurement, Bob's outcome is undetermined. So we cannot, by the way, in the previous explanation, one important fact is that the state of the alpha and beta is already determined. The spin is already determined prior to the measurement. in the quantum mechanics case, the result is not determined before the measurement. And before Alice's measurement, Bob's outcome is completely undetermined. But once Alice makes measurement, then the state collapses into one of those states. And the second argument, because of this collapse, it is guaranteed that Bob's will measure opposite spin of Alice. And after the Alice's measurement, Bob's result is completely determined. So this is very weird if you think about it. And the origin of this bizarre feature is entanglement. And in general, in this two-particle spin system, the general state is a superposition of 4 possible states. And so this is some general state psi. But for some special case, the state of alpha and state of beta can be factorized in this way. And if this is possible, then the measurement of Bob's measurement doesn't influence at all about Alice's measurement. So nothing weird happened in this case. But in general case, you cannot factorize in this way. So then, this, if you cannot factorize, then the state is called entangled. And this spin zero singlet state is one particular state, one particular entangled state. And in this case, the previous weird thing will happen. And Einstein, Podolsky, Rosen didn't like this quantum mechanical explanation. And they say the following things. So physical observables must be real. This means their values must be predetermined before or irrespectively with the measurement. So this seems natural assumption. And physical observables must be local. This means an action in one place cannot influence a physical observable in a space-like separated region. And as we saw previously, the quantum mechanics violates both local and real requirements. So that's why EPR didn't like this. And it seems very difficult to experimentally discriminate quantum mechanics from the general hidden variable theories, because as we saw previously, both can completely explain the previous experiment. But John Bell came along and he derived a simple inequalities that can discriminate quantum mechanics from the hidden variable theories. This is called Bell's inequalities. So let's look at what he found. So this is the same situation. We have Alice and Bob, and we have spin zero particle decaying into alpha and beta. But this time, Alice and Bob will measure the spin component in different directions. So Alice prepare measurement of this direction and that direction, alpha, A direction and A prime direction. Bob will measure B direction and B prime direction. And those 4 directions are different. And experiment consists of 4 sessions. And in the first session, Alice and Bob measure, Alice measure A component and Bob measure B component of the spin. And we calculate this correlation. And in the second session, Alice still measure A component, but Bob now measure B prime component. And in the third session, Alice measure A prime and Bob measure B. And in the fourth session, A prime and B prime. And finally, we calculate this particular quantity. And this quantity is called CHSH quantity. And in hidden variable theories, this spin correlation can be calculated by the integral of the hidden variable weighted by some probability density of lambda. And it is very straightforward to show that this RCHSH cannot be larger than 1. And I do not go into the detail, but this is very simple derivation. Maybe you can have a look at the slides. So it is very easy to see that in hidden variable theories, you cannot violate this inequality. So this inequality is called CHSH inequality. This is one particular Bell's inequality. But in quantum mechanics, let's take this spin zero singlet state. Then it is easy to calculate this spin-spin correlator, and you can easily show that this correlator is given by the inner product of two unit vectors of this component. So then CH/SH variable can be just replaced by the inner product of those four vectors, four unit vectors. And then if you take A and A prime in the right angle and B and B prime 40 degrees tilted, then those products will be 1 over square root of 2. But only for this A and B prime, you see that the opening angle is more than 90 degrees. So you get minus 1 over square root of 2. So this minus cancels with this minus sign. And the result will be square root of 2. So this square root of 2 is larger than 1. So this quantum mechanics violates Bell's inequality. So we can check by measuring this RCHSH, we can check whether nature is in quantum mechanics or hidden variable theories. And you can see that the state violates Bell's inequality is some special region of entangled state. Okay, and as you know, violation of the classical bound or Bell's inequality has been observed in low energy experiments. Traditionally, these experiments are done by the photon pairs. So the first measurement was 1969, and the recent one is 2015. And we have a 5 sigma confidence of the Bell's inequality violation. We have also entangled proton pairs, and also we can see the Bell's inequality violation in the K0, K0 bar and B0, B0 bar flavor system. But the Bell's inequalities and entanglement have not been tested at high energy regime of TeV scale. So the question is, can we test these features at high energy colliders? And just recently, this question was addressed. So 2020, we have paper about entanglement in TT bar pair, and 2021, we have the Bell's inequality test in TT bar pair, and we also have some study in H2WW. And in this talk, I want to test H2 tau tau. Okay, but at colliders, there are some new complications. So obviously, we have some entangled spin state to particle state, but the spin state is not necessarily always this spin zero singlet state. And also, initial state can be a statistical ensemble of different pure states. For example, we have GRU pair product, GRU initial state contribution and QQ bar initial state contribution. So we need some new mathematical device, and this would be the density operator. So if you have statistical ensemble of the quantum pure state, so in this case, we have pure state psi k with probability pk, and we have lots of different quantum pure states. And then we can construct density operator by taking this k times bra weighted by pk and sum over k. This is density matrix. And if you have a basis vector, you can also construct density matrix. And then density matrices satisfy the following condition. So rho should be Hermitian, and trace is 1, and rho is positive definite. And nice thing about this density operator is you can calculate the average of observable O very easily by taking trace of the O times rho. Okay. And in particular, in this biparticle system, we have only 4 basis vectors, plus, 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 minus, minus, plus, and minus, minus. So the density matrix is 4 by 4 matrix because we have only 4 independent bases. And 4 by 4 Hermitian trace 1 matrix can be expanded by 2 independent Pauli matrices like that. So rho can be parameterized by real number bi, b bar I, and Cij. Okay, so Cij is 3 by 3 matrix because there are 3 Pauli matrices. And the interpretation of b, b bar, Cij is very easy. So bi is just the average of spin I component of particle alpha, and b bar is for beta, and Cij is the spin-spin correlation of I component of alpha and j component of beta. So spin-spin correlation is very important for the Bell's inequality and entanglement. So Cij is very important. Okay, and okay, let's skip that. So if you have this density matrix, entanglement can be more easily formulated. So if the state is separated or not entangled, then the density matrix for alpha and beta can be factorized in this way. And if you take the transpose of beta particle, then if you take transpose, this density matrix is still Hermitian, still trace 1, and still positive definite. So this means this is still valid quantum state. So the end product of this low partial transpose is still trace 1, Hermitian, and positive definite. So if you find some negative eigenvalue for this low partial transpose, then you can say definitely system is entangled. And for the biparticle system, this is actually the necessary and sufficient condition. And in terms of b, b bar, and Cij language, this entanglement requirement boils down to this equation. And this one can be tested if you can measure C. Okay, and so how can we calculate the density matrix in particle physics? So the density matrix can be calculated, related by the matrix element in this way. For the TT bar final state, we have to sum the initial state with this Parton luminosity function. But for the Higgs to tau tau, initial state is just one state, so you don't have to sum the initial state, so it's easy to calculate. So it is easy to show that the tau tau spin state after Higgs to tau tau is actually a triplet state, and the C matrix is -1, 1, 1 diagonal. Okay, so but then how can we experimentally measure C matrix? So let's suppose the decay of alpha particle into L plus X. And we measure L at rest frame of alpha. And then the decay distribution should be written in this way. And S is the spin of alpha particle at the rest frame. So, and X is some real parameter between -1 to 1. But for the tau decay or top decay, X is 1. And if you have 2 taus, then actually the distribution of Li times Lj is related to the C matrix in this way. So if you measure the distribution of Li, Lj by fitting the distribution, you can measure Cij component. And also using this L, the direction of the decay product at the rest frame of the particle, you can also directly calculate the R, C, H, SH variables in this way. Okay, so let's look at the simulation. So I look at Higgs to tau tau at lepton colliders. Why do I use lepton colliders? Because at LHC we have a background from Z to tau tau, which is much larger than the ILC. And so for ILC, this is the signal and background is very, very small. And also we have to measure the direction of the tau decay at the rest frame of tau. But this is challenging because tau decays into neutrino. And in order to reconstruct tau momentum, we have to reconstruct neutrino momentum. And this is very challenging at LHC. So our process is like this. And we have to reconstruct neutrino momentum. So we don't know these three components. Sorry, we have 6 unknown parameters. But luckily we have 2 mass shell conditions for the tau, both taus, and also 4 energy momentum conservation. So this conservation is accessible only for the lepton collider, because for LHC, we don't know the center of mass frame of the parton, because not proton, but partons are colliding. Okay, and so to do the calculation, we take the basis. So first we go to the rest frame of the Higgs, and we define the 3 direction K, R, and N according to the tau direction, and perpendicular to the tau direction on the beam tau plane and perpendicular to that plane. And we reconstruct tau momentum, and we go to the tau rest frame and measure the direction of pi plus and pi minus. And then we calculate RCHSH directly. And also we extract Cij component by fitting Li, Lj distribution. Okay, so let's show you the result. So we assume that E plus E minus colliders with 240 GeV and 5 inverse Atban. And we generate events with mud graph and perform 100 pseudo experiments to estimate uncertainties. So this is the result in the parton level analysis. So we can measure RCHSH. So this is the result, and this is the uncertainty. And obviously R is larger than 1, which is good. And Bell's inequality violation can be tested at 5 sigma level. And also this is, if this quantity is larger than 1, this means system is entangled, and entanglement can be observed much larger than 5 sigma. Okay, now let's turn on the detector resolution. Then unfortunately, everything is screwed. So R is now 0.7, which is less than 1. And entanglement measure is also less than 1. So we have to do something. So we included the information of impact parameter because tau is a little bit long-lived. So after you reconstruct tau momentum, we check the consistency between the tau direction and measure the impact parameters. So out of those information, we can reconstruct the likelihood, and we can sort of correct the effect of the detector smearing. And including this information of impact parameter, including also the detector resolution, these are the result of our simulation. So we can test Bell's inequality violation at 2.5 sigma level, and we can test entanglement larger than 5 sigma level. Okay, so this is everything. So I said that the high energy tests of the entanglement and Bell's inequality has recently attracted a lot of attention. And tau-tau pair from Higgs to tau-tau form the EPR triplet state and maximally entangled. And we investigated a test of the test at high energy lepton colliders. And because the background is much smaller and tau momentum reconstruction is possible. And assuming these variables for the lepton colliders, we can test Bell's inequality and entanglement in a good precision. Okay, so thank you very much.
Okay, so now we come to questions. Please.
I liked a lot your exposition, your interesting result, but I would be very surprised if entanglement is valid at a certain for certain cases and then is not valid in other cases, because either quantum mechanics is good or hidden variable is good.
Yes, but I think the system is, in this particular case, tau-tau pair is always entangled, but it's just detector resolution which we cannot tell. So, as you say, the quantum mechanics probably is always right, but it depends on the capability of the measuring it.
Thanks. I agree with the previous question, but maybe a follow-up question can be, if you measure this, let's say, entanglement or verify that the system is entangled, you have, of course, verified something new or at least something unusual in the context of collider and particle physics. Does this automatically imply that this measurement is kind of particularly sensitive to a certain kind of new physics, a certain kind of new phenomena which we have not thought about, or did you think about this?
Okay, yes. Yes, so one thing is that this is just another test of standard model, but one thing we can offer you is that, so we say that tau-tau pair is spin 1 state. This is actually because of the parity of the initial state. So so this eta is -1. So if you start from the parity even, you end up with L equal 1 state. But if you start with parity odd, then you will end up with L equal 0 spin singlet state. So by measuring this correlation matrix, you can tell whether Higgs is CP even or odd. And you can also test the, you can actually generalize this formula for the non-mixed CP even odd mixture, and we can actually measure the CP angle of the Higgs to tau-tau.
So I was wondering a bit about the uncertainty. So the uncertainty is just statistical and some kind of systematic you put there. It's not actually related to the 100 pseudo experiments you did in MAGRAPH, or is dominated by this?
This is statistical uncertainty only.
Okay. And the statistical uncertainty you got from MAGRAPH, they're really small and negligible, and it's all working fine?
Yes, statistical uncertainty from MAGRAPH is probably small, very, very small, okay. But just statistical uncertainty from just luminosity is not very small.
Okay, would it be possible to do it analytically as well? Because I mean, in principle, I guess the extra Z doesn't matter. What matters is that you have a Higgs that decays into tau, right?
Yes.
And for this part, can you not do the computation analytically to check the result?
So everything is actually matters, because if you don't know the momentum very accurately, then you also don't know the Higgs momentum very accurately. So okay. It is necessary to measure everything in very detail.
Okay, because you measure it in a different frame and not in the Higgs rest frame. That's what matters.
Yeah.
Okay, thank you.
Rojas, and it is Atlas inner tractor upgrade in view of LHC, and it's 15 minutes talk plus 5 minutes of discussion.
Might be a little longer than 15 minutes. I'll do my best. Can you hear me fine? I guess so. Thomas, please. How's it working, the remote? It doesn't work. Okay. So hello, everyone. I do realize this is a pretty technical talk for an audience which is mostly theory-oriented. So I'm going to do my best to be simple, not simplistic. And of course, we can discuss if you have questions. So I'm going to discuss about the Atlas inner tracker for the High-Lume LHC. This is an upgrade, which is planned, as Marcus presented this morning. This is planned for the High-Lume LHC. The High-Lume LHC program is very rich, as you can imagine. First of all, the estimated luminosity is expected to be 3,000 or even 4,000 inverse femtobarn in an operation of 20 years, up to 2040. The highlights of the program, of course, it's on the Higgs boson properties, more statistics, so we can have better information on the couplings, the mass, the width, the self-coupling even, we may have access. We can have increased precision for the electroweak sector measurements, all the rare processes that are very low in the cross-section, like the vector boson scattering, tri-boson, all the rare processes. And of course, more statistics we can have. We can do direct searches for beyond standard model physics, dark matter, exotic searches, long-lived particles, and so on. We're going to have huge statistics, right? So this will mean that we have very strict tests of our physics models, and we can do even indirect new searches. By comparing what we measure with the theory. We can do very fancy stuff like differential measurement. We can implement EFTs and so on. And by deviations, we can have hints about new physics. So this is an example of the projection of the High-Lume LHC for the Higgs couplings. And you can see that they are all below 4% or even smaller for most of the cases. In the uncertainty. And for the self-coupling, I know a lot of people are asking questions about that. As we said, we might have some access to that. So if we combine Atlas and CMS results with 3,000 inverse femtobarn, we found that we have a 4 sigma sensitivity. And this is the result from Atlas only. If we do a combination of all the more sensitive Higgs, di-Higgs channels, we can have a 40% uncertainty on the single strength. So we cannot discuss about the discovery, but there is a sensitivity. And from my small experience from LHC experiments, older people should know better than me. I have seen that most of the cases, all the projections we were doing in the past, we end up doing better when the experiment counts for various reasons. So yeah, we might do better when we have the High-Lume LHC, who knows? Okay, so the timeline about this is the LHC and the High-Lume LHC. We are here at the moment, 2022. We just started round 3, right? So we have 3 years of data taking, and then there's a long shutdown, and then the High-Lume LHC will start in 2029. As I said, we should take data up to 2040, even better, even more later, we'll see. And we're going to have a lot of harsh LHC conditions, in particular for the luminosity, the instantaneous luminosity. We're going to have an increase of a factor of about 3 to 4 with respect to what we have now. The pileup, which is very important in LHC, will increase even to 200 interactions per bounce crossing. We're about 40 on average at the moment. And as I said, the statistics, the integrated luminosity at the end of the High-Lume LHC, this is very important at the end, will be around 3,000 or even 4,000 inverse femtobarn, which is a huge number of statistics. This is how it looks at TT bar event with mu equal to 200. You can see the total mess of tracks in the collision point, right? So the combinatorics are crazy. Yeah, and this is why, exactly this is why we need to upgrade the detectors, okay? Marcus presented that very quickly, so I'm not going to spend a lot of time. We're planning some upgrade on the muon chambers, in particular in the innermost part of the muon chambers. There's going to be a new timing detector at the forward region for the suppressor pileup, the high granular timing detector. We plan upgrades of the calorimeter and the muon chambers, mostly on the electronics and the trigger part. And I would say the most important, a very biased comment, the most important upgrade is the new inner tracker, which is called ITK. This is what I'm working on and what I'm going to present. And the characteristics of this new tracker, it should have higher granularity, reduced material budget. It should be radiation hard, of course, because there's a lot of radiation involved. We need to have faster readout. And of course, the target here is to have a tracking performance, which is at least as good as it is at the moment, or even better if possible. So what is the inner tracker? It's already, of course, approved. It's an all silicon inner tracker, everything silicon, that goes up to pseudorapidity to eta smaller than 4. At the moment, I remind you that the tracker goes up to 2.5. So it is like a big upgrade in the forward region. This will help us to improve against pileup. There are two main parts of the ITK. The outermost part, which is the strips. You can see here the blue, or you can see even there. This is composed by 4 barrel layers in the center part, and there are 6 end caps per region, left and right. And then for the pixels, which is in the innermost part of the ITK, there are 5 barrel layers. You can see them here, and then there is a lot of inclined discs and vertical discs. I've put here some performance numbers. I don't want to read them. You can read them yourselves. Maybe just to highlight that we're gonna have 9,000 modules. A module is the, how can I say, the detecting device of the tracker. And you can compare these numbers with the current pixel system. So you can see, do I have 10 or I spoke for 10 minutes? Okay, very good. And you can do the comparison of the numbers to realize yourselves how much more sophisticated the new detector is going to be. I'm going to focus not only on ITK, but in particular on the pixel detector. This is where I work at the moment, and I have more, let's say, familiarity with this part of the detector. But before talking about technical parts, one slide on the material budget. What is the material budget? Is really the matter that we have in the inner tracker that is not active, it's not detective matter. It can be the cables, the supports, the cooling stuff, and all these things. And you can see how it looks like in run 2. This is in function of eta, and it is expressed in radiation length on the material. And you can see there's a big peak at around 4 or 5, while here, be careful, the scale in Y is different. We are mostly at the peak at 2 with respect to 5 or 6. So we have much less material, which is very nice. This is happening because we have a more sophisticated cooling system. I don't want to go into details. We have ultra light carbon frames for all the loading, the structures. And there is some very innovative way of powering the detector, having modules in series, so we have less cables at the end of the day in the detector. The tracking performance, like I said, we want to have the same performance or better with much harsh LHC conditions. So first of all, we have finer granularity, as I said. So this will mean that we can cope with higher occupancy of the detector. Okay. Reduced material I discussed already. That means less multiple scattering, less conversions for the calorimeter that comes after the tracker. We have big pseudorapidity coverage, increased number of layers, so we have more hits per each track. And as you as I showed, we have a lot of tracks, so it's very important to have a lot of hits per track to resolve the combinatorics. So for instance, here you see that for the middle part, the minimum number of hits per track is more than 9, but the average is around 14 or 15. And if you go to the forward region, we have even more hits per track. So that's, it's very good in order to be able to do the tracking efficiently. Okay, now I'm going to the more technical part. One slide on the strip detector. The strip, as it is the outermost part of the ITK, there are 4 barrel layers, 6 plus 6 on the other side, and discs. The dimensions are pretty big, I would say, 6 meter long, 2 meter wide. We have 17,000 modules of strips, which means 60 million readout channels. About the electronics, we have 3 flavors of front-end readout electronics based on each feature, let's say, of the electronics. And the production status at the moment is more advanced than Pixel because it's a bigger volume, let's say. The sensors and the front-end electronics is already in the production, while the modules, the final devices, are in pre-production at the moment. This is the only slide I have on the strips, and now I'm going to the pixels. So one slide on the layout. This is, so if I zoom in here, we see this image here, which is the pixel layout. It is composed by 3 parts. There is the outer barrel, the outer end cap, the more forward, and the inner system, which has a central part and a forward part. What I would like to highlight here is this inclined geometry, which is the first time, as far as I know, in an experiment for a tracker that is implemented. So usually what we had was either horizontal or vertical modules. For this very first time, both Atlas and CMS have inclined modules, and this was found to be better in terms of having less material and be more efficient because the forward tracks here will cross the modules in a perpendicular way. I say that in simple words. It's a bit more complicated than that. What I would like to see here is, okay, some numbers about the number of layers and number of disks for each of these 3 parts. Here I've put some photos of the structures, because when I say, you know, inclined modules, barrel, or end cap, it's actual modules, I'm going to discuss about that in a while, that are placed on some mechanical structures. Okay, this is, we used to call it a stave, now it's called a longeron. This is for the barrel part, and this is rings that we put at the 2 end caps, let's say, of the detector, and we mount our modules, the detecting devices on them. The building blocks of IDK Pixel is the modules, as I said several times already. So we start with the first part of it, which is a bare module. What is a bare module? You can see it here or here. It's a piece of silicon where we have our pixels, the detector, which is BAM bonded, let's say assembled, connected to our front-end chip electronics. Okay, this is done in industry. And then we have the Flex PCB, which is a small piece of printed circuit board that we glue. Literally, we glue, as we do in the elementary school, on the bare module where the sensor is, and then we wire bond the Flex, the yellow part here is the Flex. We wire bond that to the electronics, to the front-end chip. We have 2 types of modules. A quad module, it's 4 chips that is BAM bonded to one silicon sensor. 95% of the modules are quads. And then we have triplet modules, 5% of those that are 3 single bare modules connected to the same Flex, which is housing 3 modules. The chips are very, very thin, 150 microns. This is the first time it's happening without precedent. And the sensor also are extremely thin, 150 microns or 100 microns on the layer 1. Which also contributes to have very low material in the material budget, as I said. This is a slide I added really last minute. It's a photo story of how we do the assembly of a module. And I took the photos in our clean room in Orsay. We're using a very simple manual tool, which is called jigs. You can see them here. So in the one part, we place the bare module, and the other part, we place the Flex. We apply vacuum, you can see them here. So those 2 are glued and they don't move. And we come with a mask that we call stencil that has some holes. We place the glue, very simple stuff. We place the glue here and we come with a spatula and we scrape down. And then this is the pattern of the glue that is on the Flex. And then we do the sandwich, the mating of the 2 jigs. And this is after 8 hours, we have a Flex, which is glued on a bare module. It's as simple as that. And this is how we're building the pixel modules for IDK. One slide on the readout chip. What I really like here is that this was a collaboration between Atlas and CMS to have a common readout chip for the future tracker. And I think this kind of paves the way of how the R&D should be done or will be done in the future, given the scale of the experiments. the main characteristic is that the readout size should be identical to the pixel size, so it's 50 times 50. Initially, we had the first prototype, which was called RD53A for this front-end chip, the same for Atlas and CMS, with 3 flavors, and now we are going to the final one that has, which is very radiation hard. I put here the numbers, and it's really very efficient and has a very high trigger rate and hit rate. So the current status, I have 3 more slides. The current status, we have finished in Atlas and CMS the prototyping by assembling simple modules with RD53A, the initial version of the chip. We have built around 200 modules among 20 sites, and we have finalized all the procedures for the assembly and the testing. Going to the final detector, the process is the following, the status is the following. The bare modules are currently in the pre-production. Pre-production is the phase before the production for which we have to produce 10% of the total production. And this is done entirely in the industry. And we were hit a little bit, well, not a little bit, we were hit a lot by COVID and all the problems we have with the pixel and the silicon that is missing worldwide everywhere. The Flex PCB, the design is finalized and the order will be placed, shown in the vendors in order to start the pre-production. The module assembly and testing will be done mostly in ITK sites. We are 20 sites, France, Germany, Italy, UK, US, Japan, Norway, Southern Switzerland, that we are now have developed the experience on how to do that. And the loading on the supports I discussed a while ago will be done by 4 sites for the Pixel. Maybe I can go very quickly because I have 1 more minute. So here's the highlights of the prototyping with RD53A. Just in a few words, we tried to stress as much as possible the system, like thermal cycled the modules, irradiated them, take them to the test beam and try to see if we have a drop in efficiency, if we have losses. We haven't found any issue. We're very happy. This is an image of a quad module with, this is the powering happens from here, and this connector here takes the data out to the DAC system. We also work on the loaded supports. This is a very nice photo of a ring for the layer 1, I believe. So we have we have quads here, and these are the triplets, and we're building this infrastructure in order to be able to thermal cycle the full tractor now and make sure that there is no problem, nothing's breaking or whatever. We're testing the serial powering, which is a novel way of power the pixel detector. We have done that on irradiated modules, non-irradiated modules. There's no damaging effect, and we are building, some of those are already built. It's 1 more slide. Demonstrators, real demonstrators that are small copies, let's say, of the detector, so we can test the cooling, the mechanical performance, and all the details. Last slide, it's about the timeline of the Pixel. Yeah, it's really the last slide. So in about 2 months, we will submit the final chip, and then we go to the production, the same for the Flex PCB. In 2023, by January, we should start the pre-production of the modules. It's 10% of the production. And then the 2 consecutive years, 2024, 2025, are the important years for the production of the ITK, in particular the Pixel. So by 2026, where we have the long shutdown 3, we should have everything ready. So we start the loading and the integration of the modules to the detector itself. This brings me to my summary. So Atlas is building a new tracker. It is called ITK to face really the harsh condition of the LHC. I'm not going to repeat them. It's a fully silicon tracker with the strips and the pixels in the most innermost part. And the important message here is that we have finished the prototyping with the first version of the front-end chip, and now we're starting the pre-production and the production. Thanks a lot.
So thank you very much for the talk. And now session is open for the questions. So please.
Just wondering, in practice, how do they change the tracker in Atlas? In CMS, you can open the slides and get the tracker out. In Atlas, how do you do that?
You mean how?
I mean, how do you remove the whole one and put the new one instead, right?
I'm not sure on the exact procedure. I guess what will happen is that most likely, you know,
You remove everything on the side?
yeah, the end caps will move on the side, and then we go inside and we place the tracker.
That there is space to, I mean, the Atlas Cavern is full, right? So how do you?
There is
There is a bit of room still left.
Yeah. I mean, I have here the dimensions of the tracker. So yeah, the SCT, which is large, the largest part is 6 meters. Okay. So it's not 20 meters either.
Yeah, still. Okay.
Yeah, but that was less long. No, it's the pixel. Yeah. That was about 2 meters or so. Yeah, whatever is inside here, it's super tight. So I can tell. Yes, it's already being delayed. The last 2-3 years, it was delayed for about 2-3 years. But I don't think we have a lot of margin left for more delays. What I was discussing this morning with a colleague is that most likely, if we are not on time, we will start thinking, unfortunately, on the scoping parts of the detector. I hope we won't arrive there, but it has happened in the past. It might have happened again.
Okay, thank you.
Yeah, there was a question there. Okay. I'll be around. Super.